Section 21 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga, pjk.scripps.mit.edu/pkj. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 4, of the Progress of Chemistry under Paracelsus and his Disciples, Part 3. To attempt to refute these wild notions of Sylvius would be loss of time. It is extraordinary and almost incredible that he could have regulated his practice by them. And it is a still more incredible thing, and exhibits a very humiliating view of human nature, that these crudities and absurdities were swallowed with avidity by crowds of students, who placed a blind reliance on the dogmas of their master, and were initiated by him into a method of treating their patients better calculated than any other that could easily have been devised, to aggravate all their diseases and put an end to their lives. If any of the patients of the Iatro-Chemists ever recovered their health, well might it be said that their recovery was not the consequence of the prescriptions of their physicians, but that it took place in spite of them. It is a very remarkable circumstance, and shows clearly that mankind in general had become disgusted with the dogmas of the Galenists, that iatro-chemistry was adopted more or less completely by almost all physicians. There were indeed a few individuals who raised their voices against it, but what is curious and inexplicable, they never attempted to start objections against the principles of the Iatro-Chemists, or to point out the futility of their hypothesis and their inconsistency with fact. They combated them by arguments not more solid than those of their antagonists. During the presidency of Riolan over the Medical College of Paris, that learned body set itself against all innovations. Guy Patin, who was a medical professor at the University of Paris and a man of great celebrity, opposed the chemical system of medicine with much zeal. In his Martyrologium Antimonii he collects all the cases in which the use of antimony as a medicine had proved injurious to the patient. But in the year 1666 the dispute relative to antimony, and particularly relative to tartar emetic, became so violent that all of the doctors of the faculty of Paris were assembled by an order of the Parliament under the presidency of Dean Vignon, and after a long deliberation it was concluded by a majority of 92 votes that the tartar emetic and other antimonials should not only be permitted but even recommended. Patin, after this decision, pretended no longer to combat chemical medicine, but he did not remain inactive. One of his friends, Francis Blondel, demanded the resolution to be cancelled, but his exertions were unsuccessful. Nor were the writings of Guillemot and Menjot, who were also keen partisans of the views of Patin, attended with better success. In England, iatro-chemistry assumed a direction quite peculiar. It was embraced by a set of men who had cultivated anatomy with the most marked success, and who were quite familiar with the experimental method of investigating nature. The most eminent of all English supporters of iatro-chemistry was Thomas Willis, who was a contemporary of Sylvius. Dr. Willis was born at Great Bodmin in Wiltshire in 1621. He was a student at Christ Church College in Oxford when that city was garrisoned for King Charles I. Like the other students, he bore arms for His Majesty and devoted his leisure hours to the study of physic. After the surrender of Oxford to the Parliament, he devoted himself to the practice of medicine and soon acquired reputation. He appropriated a room as an oratory for divine service, according to the forms of the Church of England, to which most of the loyalists of Oxford daily resorted. In 1660 he became Sedleian Professor of Natural Philosophy, and the same year he took the degree of Doctor of Physic. He settled ultimately in London, and soon acquired a higher reputation and a more extensive practice than any of his contemporaries. He died in 1675, and was buried in Westminster Abbey. He was a first-rate anatomist. To him we are indebted for the first accurate description of the brain and nerves. But it is as an iatro-chemist that he claims a place in this work. His notions approach nearer to those of Paracelsus than to the hypotheses of van Helmont and Sylvius. He admits the three chemical elements of Paracelsus, salt, sulfur, and mercury in all the bodies of nature, and employs them to explain their properties and changes, but he gives the name of spirit to the mercury of Paracelsus. He ascribes to it the virtue of volatilizing all of the constituent parts of bodies. Salt, on the other hand, is the cause of fixity in bodies. Sulfur produces color and heat, and unites the spirit to the salt. In the stomach there occurs an acid ferment, which forms the chyle with the sulfur of the aliments. This chyle enters into effervescence in the heart, because the salt and sulfur take fire together. From this results the vital flame, which penetrates everything. The vital spirits are secreted in the brain by a real distillation. The vessels of the testes draw an elixir from the constituent parts of the blood, but the spleen retains the earthy part, and communicates a new igneous ferment to the circulating fluid. On this account, the blood must be considered as a humour, constantly disposed to fermentation, and in this respect it may be compared to wine. Every humour in which salt, sulfur, and spirit predominates in a certain manner may be converted into a ferment. All diseases proceed from a morbid state or action of this ferment, and a physician may be compared to a wine merchant, for like him he has nothing to do but to watch that the necessary fermentations take place with regularity, and that no foreign substance come to derange the operation. At this period the mania of explaining everything had proceeded to such a length that no distinction was made between dead and living bodies. The chemical facts which were at that time known were applied without hesitation to explain all the functions and all the diseases of the living body. According to Willis, fever is the simple result of a violent and preternatural effervescence of the blood and the other humours of the body, either produced by external causes or by internal ferments, into which the chyle is converted when it mixes with the blood. The effervescence of the vital spirits is the source of quotidians. That of salt and sulfur produces continued fever, and external ferments of a malignant nature produce malignant fevers. Thus the smallpox is owing to the seeds of fermentation set in activity by an external principle of contagion. Spasms and convulsions are produced by an explosion of the salt and sulfur with the animal spirits. Hypochondriacal affections and hysteria depend originally on the morbid putrefactions of the blood in the spleen, or on a bad fermentescible principle, loaded with salt and sulfur, which unites with the vital spirits and deranges them. Scurvy is owing to an alteration of the blood, which may then be compared to vapid or stale wine. The gout is merely the coagulation of the nutritive juices altered by the acidified animal spirits, just as sulfuric acid forms a coagulum with carbonate of potash. The action of medicines is easily explained by the effects which they produce on the nourishing principles. Sudorifics are considered as cordials because they augment the sulfur in the blood, which is the true food of the vital flame. Cordials purify the animal spirits and fix the too volatile blood. Willis disagrees with the other iatro-chemists of his time in one thing. He recommends bleeding in the greater number of diseases as an excellent method of diminishing unnatural fermentation. Dr. Keren, a celebrated fellow of the Royal Society, was another English iatro-chemist who attempted to explain muscular motion by the effervescence of the nervous fluid or animal spirits. It is not worth while to notice the host of writers, English, French, Italian, Dutch, and German, who exerted themselves to maintain, improve, and defend the chemical doctrines of medicine. The first person who attempted to overturn these absurd doctrines and to introduce something more satisfactory in their place was Mr. Boyle, at that time in the height of his celebrity. Robert Boyle was born at Young Hall, in the province of Munster, on the 25th of January 1626. He was the seventh son and the 14th child of Richard, Earl of Cork. He was partly educated at home and partly at Eton, where he was under the tuition of Sir Henry Wotton. At the age of 11 he travelled with his brother and a French tutor through France to Geneva, where he pursued his studies for 21 months and then went to Italy. During this period he acquired the French and Italian languages, and indeed talked in the former with so much fluency and correctness that he passed, when he thought proper, for a Frenchman. In 1642 his father's finances were deranged by the breaking out of the Great Irish Rebellion. His tutor, who was a Genevese, was obliged to borrow on his own credit a sum of money sufficient to carry him home. On his arrival he found his father dead, and though 2 estates had been left to him, such was the state of the times that several years had elapsed before he could command the requisite sum of money to supply his exigencies. He retired to an estate at Stalsbridge in Dorsetshire. In 1654 he went to Oxford, where he associated himself with a number of eminent men, Dr. Willis among others, who had constituted themselves into a combination for experimental investigations, distinguished by the name of the Philosophical College. This society was transferred to London, and in 1663 was incorporated by Charles II under the name of the Royal Society. In 1668 Mr. Boyle took up his residence in London, where he continued till the last day of December 1691, assiduously occupied in experimental investigations, on which day he died in the 65th year of his age. We are indebted to Mr. Boyle for the first introduction of the air pump and the thermometer into Britain, and for contributing so much by means of Dr. Hooke to the improvement of both. His hydrostatical and pneumatical investigations and experiments constitute the foundation of these two sciences. The thermometer was first made an accurate instrument of investigation by Sir Isaac Newton in 1701. This he did by selecting as 2 fixed points the temperatures at which water freezes and boils, marking these upon the stem of the thermometer, and dividing the interval between them into a certain number of degrees. All thermometers made in this way will stand at the same point when plunged into the bodies of the same temperature. The number of divisions between the freezing and boiling points constitute the cause of the differences between the different thermometers. In Fahrenheit's thermometer, which is used in Great Britain, the number of degrees between freezing and boiling points of water is 180. In Réaumur's it is 80. In Celsius's, or the centigrade, it is 100, and in Dr. Liesel's it is 150. But my reason for mentioning Mr. Boyle here was the attempt which he made in 1661 by the publication of his Sceptical Chemist to overturn the absurd opinions of the Iatro-Chemists. He raises doubt not only respecting the existence of the elements of the Peripatetics, but even those of the chemists. The first elements of bodies, in his opinion, are atoms of different shapes and sizes, the union of which he gives origin to what we vulgarly call elements. We cannot restrain the number of these to 4, as the Peripatetics do, nor to 3 with the chemists, neither are they immutable, but convertible into each other. Fire is not the means that ought to be employed to obtain them, for the salt and sulphur are formed during its action by the union of different simple bodies. Boyle shows, besides, that the chemical theory of qualities is exceedingly inaccurate and uncertain, because it takes for granted things which are very doubtful and in many cases directly contrary to the phenomena of nature. He endeavours to prove the truth of these ideas, and particularly the production of the chemical principles, by a great number of convincing and conclusive experiments. In another treatise, entitled The Imperfections of the Chemical Doctrines of Qualities, he points out in the second section the insufficiency of the hypotheses of Sylvius relative to the generality of acids and alkalis. He shows that the offices ascribed to them are arbitrary, and the notions respecting them unsettled, that the hypotheses respecting them are needless and insufficient, and afford but an unsatisfactory solution of the phenomenon. These arguments of Boyle did not immediately shake the credit of the chemical system. In the year 1691, a chemical academy was founded at Paris by Nicolas de Blegny, the express object of which was to examine the objections of Boyle, which by this time had attracted great attention. Boyle's experiments were repeated and confirmed, but the academicians, notwithstanding, came to the conclusion that it is unnecessary to have recourse to the true elements of bodies, and that the phenomena which occur in the animal economy may be explained by the predominance of acids and alkalis. Various other publications appeared all on the same side. In Germany, Hermann Corinius, the most skillful physician of his time, opposed the chemical theory, and his opinions were impugned by Olaus Borrichius, who defended not only alchemy, but the chemical theory of medicine with equal erudition and zeal. Toward the end of the 16th century, chemists thought of examining the liquids of the living body to ascertain whether they really contained the acids and alkalis which had been assigned them, and considered as the cause of all diseases. But at that time chemistry had made so little progress, and such was the want of skill of those who undertook these investigations, that they readily obtained everything that was wanted to confirm their previous notions. John Viridet, a physician of Geneva, announced that he had found an acid in the saliva and the pancreatic juice, and an alkali in the gastric juice and the bile. But the most celebrated experiments of that period were those of Raymond Vieussens, undertaken in 1698 in order to discover the presence of an acid spirit in the blood. His method was to mix blood with a species of clay called bole, and to subject the mixture to distillation. He found that the liquid distilled over was acid. Charmed with this discovery, which he considered as of first-rate importance, he announced it by letter to the different academies and colleges in Europe. Some doubts being raised about the accuracy of his experiment, it having been alleged that the acid came from the clay which he had mixed with the blood, and not from the blood itself, Vieussens purified the bole from all the acid which it could contain, and repeated his experiment again. The result was the same. The acrid salt of the fluid yielded an acid spirit. It would be needless in the present state of our knowledge to point out the inaccuracy of such an experiment, or how little it contributed to prove that the blood contains a free acid. It is now well known to chemists that blood is remarkably free from acids, and that if we accept a little common salt, which exists in all of the liquids of the human body, there is neither any acid nor salt whatever in that liquid. Michael et Müller at Leipzig, who was a chemist at some eminence in his day, and published a small treatise on the science which was much sought after, was also a zealous Iatro-Chemist, but his opinions were obviously regulated by the researches of Boyle. He denies the existence of acid and alkalis in certain bodies, and distinguishes carefully between acid and putrid fermentation. One of the most formidable antagonists to the iatrochemical doctrine was Dr. Archibald Pitcairn, first a professor of medicine at the University of Leyden and afterwards of Edinburgh, and one of the most eminent physicians of his time. He was born in Edinburgh on the 25th of December, 1652. After finishing his school education in Dalkeith, he went to the University of Edinburgh, where he improved himself in classical learning and completed a regular course of philosophy. He turned his attention to the law, and prosecuted his studies with so much ardour and intensity that his health began to suffer. He was advised to travel, and set out accordingly for the south of France. By the time he had reached Paris he was so far recovered that he determined to renew his studies, but as there was no eminent professor of law in that city, and as several gentlemen of his acquaintance were engaged in the study of medicine, he went with them to the lectures and hospitals, and employed himself in this way for several months, till his affairs called him home. On his return he applied himself chiefly to mathematics, in which, under the auspices of his friend, celebrated Dr. David Gregory, he made uncommon progress. Struck with the charms of this science, and hoping by the application of it to medicine to reduce the healing art under the rigid rules of mathematical demonstration, he formed the resolution of devoting himself to the study of medicine. There was at that time no medical school in Edinburgh, and no hospital at which he could improve himself. He therefore repaired to Paris, and devoted himself to his studies with a degree of ardour that ensured him an almost unparalleled success. In 1680 he received from the faculty of Reims the degree of Doctor of Medicine, and a degree also conferred on him in 1699 by the University of Aberdeen. In the year 1691 his reputation was so high that the University of Leyden solicited him to fill the medical chair, at that time vacant. He accepted the invitation, and delivered a course of lectures at Leyden, which was greatly admired by all his auditors, among whom were Boerhaave and Mead. At the close of the session he set out for Scotland to marry the daughter of Sir Archibald Stevenson. His friends in his own country would not consent to part with him, and thus he was reluctantly obliged to resign his chair in the University of Leyden. He settled as physician in Edinburgh, where he was appointed titular professor of medicine. His practice extended beyond example, and he was more consulted by foreigners than any Edinburgh physician either before or after his time. He died in October 1713, admired and regretted by the whole country. He was a zealous supporter of Iatro-Mathematics, and as such a professed antagonist of the Iatro-Chemists. He refuted their opinions with much strength of reasoning, while his high reputation gave his opinions uncommon effect, so that he contributed perhaps as much as anyone to put a period to the most disgraceful as well as dangerous set of opinions that ever overspread the medical horizon. Into the merits of the Iatro-mathematicians it is not the business of this work to enter. They at least display science and labour and erudition, and in all these respects are far before the Iatro-Chemists. Perhaps their own opinions were not more agreeable to the real structure of the human body, nor their practice more conformable to reason, or more successful than those of the chemists. Probably the most valuable of all Dr. Pitcairn's writings is his vindication of the claims of Hervey to the great discovery of the circulation. End of part 21. Read by Paul King, Mississauga. http pjk.scripts.mit.edu/pkj. Section 22 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga. pjk.scripts.mit.edu/pkj. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 4. Of the Progress of Chemistry under Paracelsus and his Disciples, Part 4. Boerhaave, the pupil of Pitcairn, and afterwards a professor in Leyden, was no less a zealous or successful opponent of the Iatro-Chemists. Hermann Boerhaave, perhaps the most celebrated physician that ever existed, if we except Hippocrates, was born at Voorhout, a village near Leyden, in 1668, where his father was the parish clergyman. At the age of 16 he was left without parents, protection, advice, or fortune. He had already studied theology and the other branches of knowledge that are considered as requisite for a clergyman, to which situation he aspired, and while occupied with these studies he supported himself at Leyden by teaching mathematics to the students, a branch of knowledge to which he had devoted himself with considerable ardour while living in his father's house. But a report being raised that he was attached to the doctrines of Spinoza, the clamour against him was so loud that he thought it requisite to renounce his intention of going into orders. Footnote: while travelling in a tract boat, one of his fellow travellers, more orthodox than well informed, attacked the system of Spinoza with so little spirit that Boerhaave was tempted to ask him if he had ever read Spinoza. The polemic was obliged to confess that he had not, but he was so much provoked at this public exposure of his ignorance that he propagated the report of Boerhaave's attachment to Spinozism, and thus blasted his intention of becoming a clergyman. End of footnote. He turned his studies to medicine and the branches of science connected with that pursuit, and these delightful subjects soon engrossed the whole of his attention. In 1693 he was created doctor of medicine and began to practice. He continued to teach mathematics for some time, till his practice increased sufficiently to enable him to live by his fees. His spare money was chiefly laid out upon books. He also erected a chemical laboratory, and though he had no garden, he paid great attention to the study of plants. His reputation increased with considerable rapidity, but his fortune rather slowly. He was invited to the Hague by a nobleman who stood high in the favour of William III, King of Great Britain, but he declined the invitation. His three great friends, to whom he was in some measure indebted for his success, were James Trigland, professor of theology, Daniel Alpen, and John Vanderburg, both of them successfully chief magistrates of Leyden and men of great influence. Vanderburg recommended him to the situation of professor of medicine in the University of Leyden, to which chair he was raised. Fortunately for the reputation of the university, on the death of Drelincourt in 1702, he not only gave public lectures on medicine, but was in the habit of also giving private instructions to his pupils. His success as a teacher was so great that a report having been spread of his intention to quit Leyden, the curators of the university added considerably to his salary on condition that he would not leave them. The first step towards fortune and eminence having been made, others followed with great rapidity. He was appointed successively professor of botany and of chemistry, while rectorships and deanships were showered upon him with an unsparing hand. And such was the activity, the zeal, and the ability with which he filled all these chairs, that he raised the University of Leyden to the very highest rank of all the universities in Europe. Students flocked to him from all quarters. Every country of Europe furnished him with pupils. Leyden was filled and enriched by an unusual crowd of strangers. Though his classrooms were large, yet so great was the number of students that it was customary for them to keep places, just as is done in the theatre when a first-rate actor is expected to perform. He died in the year 1738, while still filling the three different chairs with undiminished reputation. It is not our object here to speak of Boerhaave as a physician, or as a teacher of medicine or of botany, though in all these capacities he is entitled to the very highest eulogium. His practice was as unexampled as his success as a teacher. It is solely as a chemist that he claims our attention here. His system of chemistry, published in 2 quarto volumes in 1732, and of which we have an excellent English translation by Dr. Shaw, printed in 1741, was undoubtedly the most learned and most luminous treatise on chemistry that the world has yet seen. It is nothing less than a complete collection of all of the chemical facts and processes which were known in Boerhaave's time, collected from 1,000 different sources, and equally disgusting from their obscurity and their mysticism.
Everything is stated in the plainest way, stripped of all mystery, and chemistry is shown as a science and an art of the first importance, not merely to medicine, but to mankind in general. The processes given by him are too numerous and too tedious to have been all repeated by one man, how laborious soever he may have been. Many of them have been taken upon trust, and no distinction is made in the book between those which are stated upon his own authority and those which are merely copied from others. This treatise has been accused, and with some justice, as not always to be depended on. But the real information which it communicates is prodigious, and when we compare it with any other system of chemistry that preceded it, the superiority of Boerhaave's information will appear in a very conspicuous point of view. After a short but valuable historical introduction, he divides his work into two parts. The first treats of the theory of chemistry, the second of the practical processes. He defines chemistry as follows. Chemistry is an art which teaches the manner of performing certain physical operations, whereby bodies cognizable to the senses, or capable of being rendered cognizable, and of being contained in vessels, are so changed by means of proper instruments as to produce certain determinate effects, and at the same time discover the causes thereof, for the service of various arts. This definition is not calculated to throw much light on chemistry to those who are unacquainted with its nature and object. Neither is it conformable to the modern notions entertained of chemistry, but it is requisite to keep in mind Boerhaave's definition of chemistry when we examine his system, that we may not accuse him of omissions and imperfections, which are owing merely to the state of the science when he gave his system to the world. In his theory of chemistry he begins with the metals, which he treats in the following order: gold, mercury, lead, silver, copper, iron, tin. The account of them, though imperfect, is much fuller and more satisfactory than any that preceded it. He then treats of the salts, which are common salt, saltpeter, borax, sal ammoniac, and alum. This, it will be admitted, is but a meagre list. However, other salts occur in different parts of the book which are not described here. He next gives an account of sulphur. Here he introduces white arsenic, obtained, he says, from cobalt, and not known for more than 200 years. He considers it as a real sulphur, and takes no notice of metallic arsenic, though it had been already alluded to by Paracelsus. He then treats of bitumens, including under the name not merely bitumens liquid and solid, but likewise pit coal and ambergris. An account of stones and earths come next, and constitutes the most effective part of the book. It is very surprising that in this part of his work he takes no notice of lime. The semi-metals come next. They are antimony, bismuth, and zinc. Here he gives an account of the three vitriols or sulfates of iron, copper, and zinc. He knew the composition of sulfate of iron, but was ignorant of that of the sulfate of copper and sulfate of zinc. He considers semimetals as compounds of a true metal and sulfur, and therefore enumerates cinnabar among the semimetals. Lastly, he treats of vegetables and animals, and it is needless to say that his account is very imperfect. He next treats of the utility of chemistry, and shows its importance in natural philosophy, medicine, and the arts. Afterwards he describes the instruments of chemistry. This constitutes the longest and most important part of the whole work. He first treats of fire at great length. Here we have an account of the thermometer, of the expansion produced by heat, of steam, and in fact the germ of many of the most important parts of the science of heat, which have since been expanded and applied to the improvement not merely of chemistry, but of the arts and resources of human industry. The experiments of Fahrenheit related by him on the change of temperature induced by agitating water and mercury together at different degrees of heat gave origin to the whole doctrine of specific heats. Though Boerhaave himself seemed not aware of the importance of these experiments, or indeed even to have considered them with any attention, But when afterwards analyzed by Dr. Black, these experiments gave origin to one of the most important parts of the whole science of heat. He next treats at great length on fuel. Here his opinions are often very erroneous, from his ignorance of a vast number of facts which have since come to light. It is curious that during the whole of his very long account of combustion he makes no allusion to the peculiar opinions of Stahl on the subject, though they were known to the public and had been admitted by chemists in general before his work was published. To what are we to ascribe this omission? It could scarcely have been owing to ignorance, Stahl's reputation being too high to allow his opinions to be treated with neglect. We must suppose, I think, that Boerhaave did not adopt Stahl's doctrine of combustion, but at the same time did not think it proper to enter into any controversy on the subject. He next treats of the heat produced when different liquids are mixed, as alcohol and water, etc. He gives many examples of such increase of temperature, and describes the phenomenon very correctly. But he was unable to assign the cause of the evolution of this heat. The subject was elucidated many years after by Dr. Irvine, who showed that it was owing to a diminution of the specific heat which takes place when the liquids combine chemically together. It is in this part of his work that he gives an account of phosphorus, of the action of nitric acid on volatile oils, and he concludes from all the facts which he states that elementary fire is a corporeal body. His explanation of the combustion of Homburg's pyrophorus and of common phosphorus shows clearly that he had no correct notion of the reason why air is necessary to maintain combustion, nor of the way in which that elastic fluid performs its part in the great phenomena of nature. He next treats of the mode of regulating fire for chemical purposes. Then he treats of air, his account being chiefly taken from Boyle. He ascribes the discovery of the law of elasticity of air both to Boyle and Mariotte. Boyle, I believe, was the first discoverer of it. The French are in the habit of calling it the law of Mariotte. He then treats of water and lastly of earth, but even here no mention whatever is made of lime. In the last part of the theory of chemistry he treats at great length of menstruums. These are water, oils, alcohol, alkalis, acids, and neutral salts. He mentions potash and ammonia, but takes no notice of soda, the difference between potash and soda not being accurately known. Nor can we expect any particular account of the difference between the properties of mild and caustic potash, as this subject was not understood till the time of Dr. Black. The only acids which he mentions are the acetic, sulfuric, nitric, muriatic, and aqua regia. He subjoins a disquisition on the alkahest or universal solvent, which it is obvious enough, however, from the way in which he speaks of it, that he was not a believer in. The object of his practical part is to teach the method of making all the different chemical substances known when he wrote. This he does in 227 processes, in which all the manipulations are described with considerable minuteness. This part of the work must have been long considered as of great utility, and must have been long resorted to by the student as a mine of practical information upon almost every subject that could arrest his attention. So immense is the progress that chemistry has made since the days of Boerhaave, and so different are the researches that at present occupy chemists, and so much greater the degree of precision required to be attained, that his processes and directions are now of little or no use to a practical student of chemistry, as they convey little or none of the knowledge which it is requisite for him to possess. Boerhaave made a set of most elaborate experiments to refute the ideas of the alchemists respecting the possibility of fixing mercury. He put a quantity of pure mercury into a glass vessel, and kept it for 15 years at a temperature rather higher than 100 degrees. It underwent no alteration whatever, excepting that a small portion of it was converted into a black powder. But this black powder was restored to the state of running mercury by trituration in a mortar. In this experiment the air had free access to the mercury. It was repeated in a closed vessel with the same result, excepting that the mercury was kept hot for only 6 months instead of 15 years. To show that mercury cannot be obtained from metals by the processes recommended by the alchemists, he dissolved a pure nitrate of lead in water, and mixing the solution with sal ammoniac, chloride of lead, precipitated. Of this chloride he put a quantity into a retort, and poured over it a strong lixivium of caustic potash. The whole was digested at the temperature of 96 degrees for 6 months and 6 days. It was then distilled in a glass retort by a temperature gradually raised to redness, but not a particle of mercury was evaporated, as it had been alleged by the alchemists would be the case. Isaac Hollandus had stated that mercury could be easily obtained from the salt of lead made by means of distilled vinegar. To prove this he calcined a quantity of acetate of lead, ground the residue to powder, and triturated it with a very strong alkaline lixivium, and kept the lixivium over it covered with paper for months, taking care to add water in proportion as it evaporated. The calx was then distilled in a heat gradually raised to redness, but not a particle of mercury was obtained. These were not the only laborious experiments in which he made with this metal. He distilled it above 500 times, and found that it underwent no alteration. When long agitated in a glass bottle, it is convertible into a black acrid powder, obviously protoxide of mercury. This black powder, when distilled, is converted into running mercury. Exposure of mercury for some months in a heat of 180 degrees converts it also into protoxide, and if the heat be higher than this, the mercury is converted into a red acrid substance, obviously peroxide of mercury. But this peroxide, by simple distillation, is again reduced to the state of running mercury. Boerhaave combated the opinions of the Iatro-Chemists with great eloquence, and with a weight derived from his high reputation and the extraordinary veneration in which his opinions were held by his disciples. His efforts were assisted by those of Bonn, who combated the medical opinions by arguments drawn from both experience and observation, and perfectly irresistible, and the ruin of the chemical sect was consummated by the exertions of the celebrated Frederick Hoffmann, the founder of the most perfect and satisfactory system of medicine that has ever appeared. His efforts were probably roused into action by a visit which he paid to England in 1683, during which he got acquainted with Boyle and with Sydenham, the former the greatest experimentalist and the latter the greatest physician of the time, and both of whom were declared enemies to iatro-chemistry. End of Part 22. Read by Paul King, Mississauga, pjk.scripts.mit.edu/pkj.
Section 23 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 6, of Agricola and Metallurgy. I have been induced by a wish to prosecute the history of the opinions first supported by Paracelsus, and carried so much further by Van Helmont and Sylvius, to give a connected view of their effects upon medical practice and medical theory, and I have come to the commencement of the 18th century without taking notice of one of the most extraordinary men, and one of the greatest promoters of chemistry that ever existed. I mean George Agricola. I shall consecrate the whole of this chapter to his labors and those of his immediate successors. George Agricola was born at Glauber in Misnia in the year 1494. When a young man he acquired such a passion for mining and minerals by frequenting the mountains of Bohemia that he could not be persuaded to relinquish the study. He settled, indeed, as a physician at Joachimsthal, but his favorite study engrossed so much of his attention that he succeeded but ill in his medical capacity. This induced him to withdraw to Chemnitz, where he devoted himself to his favorite pursuits. He studied the mineralogical writings of the ancients with the most minute accuracy. But not satisfied with this, he visited the mines in person, examined the processes followed by the miners in extracting the different ores and in washing and sorting them. He made collections of all the different ores and studied their nature and properties attentively. He likewise collected information about the methods of smelting them and extracting from them the metals in a state of purity. The information which he collected respecting the mines wrought in the different countries of Europe is quite wonderful. If we consider the period in which he lived, the little intercourse which existed between nations, and the total want of all those newspapers and journals which now carry every new scientific fact with such rapidity to every part of the world. Agricola died at Chemnitz in the year 1555, after he had reached the 61st year of his age. Maurice, the celebrated Elector of Saxony, settled on him a pension, the whole of which he devoted to his metallurgic pursuits. To him we find him dedicating the edition of his works which he published in the year of his death, and which is dated the 14th before the calends of April 1555. He even spent a considerable proportion of his own estate in following out his favorite investigations. In the earlier part of his life he had expressed himself rather favorable to the Protestant opinions, but in his latter days he had attacked the Reformed religion. This rendered him so odious to the Lutherans, at that time predominant in Chemnitz, that they suffered his body to remain unburied for 5 days together, so that it was necessary to remove it from Chemnitz to Zeitz, where it was interred in the principal church. His great work is his treatise De Re Metallica, in 12 books. In this work he gives an account of the instruments and machines and everything connected with mining and metallurgy, and even gives figures of all the different pieces of apparatus employed in his time. He has also exhibited the Latin and German names for all these different utensils. This work may be considered as a very complete treatise on metallurgy, as it existed in the 16th century. The first 6 books are occupied with an account of mining and smelting. In the 7th book he treats of dosimetry, or the method of determining the quantity of metal which can be extracted from every particular ore. This he does so completely that most of his processes are still followed by miners and smelters. He gives a minute and accurate account of the furnaces, muffles, crucibles, etc., almost such as are still employed, with minute directions for preparing the ores which are to be subjected to examination, the fluxes with which they must be mixed, and the precautions necessary in order to obtain a satisfactory result. In short, this book may be considered as a complete manual of dosimetry. How much of the methods given originated with Agricola it is impossible to say. He probably did little more than collect the scattered processes employed by the smelters of metals in different parts of the world and reduced the whole to a regular system, but this was a great deal. Perhaps it is not saying too much that the great progress made in the chemical investigation of the metals was owing in a great measure to the labors of Agricola. Certainly the progress made by the moderns in the difficult arts of mining and metallurgy must in a great measure be ascribed to the labors of Agricola. In the 8th book he describes the mechanical preparation of the ores and the mode of roasting them, either in the open air or in furnaces. The 9th book is occupied with an account of smelting furnaces. It contains also a description of the processes for obtaining mercury, antimony, and bismuth from their ores. The 10th book treats of the separation of silver and gold from each other by means of nitric acid and aqua regia, minute directions for the preparation of which are given. The modes of purifying the precious metals by means of sulfur, antimony, and cementations are also described. In the 11th book he treats of the method of purifying silver from copper and iron by means of lead. He gives an account also of the processes employed for smelting and purifying copper. In the 12th book he treats of the methods of preparing common salt, saltpeter, alum, and green vitriol, or sulfate of iron, of the preparation and purification of sulfur, and of the mode of manufacturing glass. In short, Agricola's work De Re Metallica is beyond comparison the most valuable chemical work which the 16th century produced, and places the author very high indeed among the list of the improvers of chemistry. The other works of Agricola are his treatise De Natura Fossilium in 10 books, De Ortu et Causis Subterraneorum in 5 books, De Natura Eorum quae effluunt ex terra in 4 books, De Veteribus et Novis Metallis in 2 books, and his Bermanus Sive de Re Metallica Dialogus. The treatise De Veteribus et Novis Metallis is amusing. He not only collects together all the historical facts on record respecting the first discoverers of the different metals and the first workers of mines, but he gives many amusing anecdotes, nowhere else to be found, respecting the way in which some of the most celebrated German mines were discovered. In the 2nd book he takes a geographical view of every part of the known world, and states the mines wrought and the metals found in each. We must not suppose that all his statements in this historical sketch are accurate. To admit it would be to allow him a greater share of information than could possibly belong to any one man. He frequently gives us the authority upon which his statements are founded, but he often makes statements without any authority whatever. Thus he says that a mine of quicksilver had been recently discovered in Scotland. The fact, however, is that no quicksilver mine ever existed in any part of Britain. There was indeed a foolish story circulated about 30 years ago about a vein of quicksilver found under the town of Berwick-upon-Tweed, but it was an assertion unsupported by any authentic evidence. Many years elapsed before much addition was made to the processes described by Agricola. In the year 1566, Pedro Fernandez de Velasco introduced a method of extracting gold and silver from their ores in Mexico and Peru by means of quicksilver, but I have never seen a description of his process. Alonso Barba claims for himself, and seemingly with justice, the method of amalgamating the ores of gold and silver by boiling. Barba was a Spanish priest who lived about the year 1609 at Tarabuca, a market town in the province of Jairus, 8 miles from Plata in South America. In the year 1615 he was curate of Tiaguacano in the province of Pacayas, and in 1617 he lived in Lepas in Peru. He is said to have been a native of Lepe, a small township in Andalusia, and had for many years the living of the Church of St. Bernard at Potosi. His work on the amalgamation of gold and silver ores appeared in Madrid in the year 1640 in quarto. Footnote: it is entitled El arte de los metales, en que se enseña el verdadero beneficio de los de oro y plata por azoque, etc. End of footnote. In the year 1629, a new edition of it appeared with an appendix, under the title of Tratado de las Anticas Minas de España de Alonso Carrillo Lasso. The English minister at the court of Madrid, the Earl of Sandwich, published the first part of it in an English translation at London in 1674 under the title of The First Book of the Art of Metals, in which is declared the manner of their generation and the concomitants of them, written in Spanish by Elbaro Alonso Barba, by E. Earl of Sandwich. The next improver of metallurgic processes was Lazarus Erckern, who was upper bar master at Kuttenberg in the year 1588, and was superintendent of the mines in Germany, Hungary, Transylvania, the Tyrol, etc., to 3 successive emperors. His work has been translated into English under the title of Heta Minor, or the Laws of Art and Nature in Knowing, Judging, Assaying, Fining, Refining, and Enlarging the Bodies of Confined Metals, to which are added essays on metallic words illustrated with sculptures, by Sir J. Pettus, London, 1683, folio. But this translation is a very bad one. Erckern gives a plain account of all the processes employed in his time without a word of theory or reasoning. It is an excellent practical book, though it is obvious enough that the author was inferior in point of abilities to Agricola. His treatment of Don Juan de Cordoba, who offered in 1588 to put the court of Vienna in possession of the Spanish method of extracting gold and silver from the ores by amalgamation, as related by Baron Born in his work on amalgamation, shows very clearly that Erckern was a very illiberal-minded man and puffed up with an undue conceit of his own superior knowledge. Footnote: Born's New Process of Amalgamation, translated by Rasp, page 11. End of footnote. Had he condescended to assist the Spaniard and to furnish him with proper materials to work upon, the Austrians might have been in possession of the process of amalgamation with all its advantages a couple of centuries before its actual introduction. I need not take any notice of the docimastic treatises of Schindler's and Schlutter, which are of a much later date, and both of which have been translated into French, the former by Geoffroy Jr., the latter by Helot. This last translation, in 2 large quartos, published in 1764, constitutes a very valuable book, and exhibits all the docimastic and metallurgic processes known at that period, with much fidelity and minuteness. Very great improvements have taken place since that period, but I am not aware of any work published in any of the European languages that is calculated to give us an exact idea of the present state of the various mining and metallurgic processes, important as they are to civilized society. Gellert's Metallurgic Chemistry, so far as it goes, is an excellent book. End of section 23.
Section 24 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 7, of Glauber, Lemery, and some other chemists of the end of the 17th century. Hitherto I have treated of the alchemists, or Iatro-Chemists, and have brought the history of chemistry down to the beginning of the 18th century. But during the 17th century there existed several laborious chemists who contributed very materially by their exertions, either to extend the bounds of science, or to increase its popularity and respectability in the eyes of the world. Of some of the most eminent of these it is my intention to give an account in this chapter. Of John Rudolph Glauber, the first of these meritorious men in point of time, I know very few particulars. He was a German and a medical man, and spent most of his time at Salzburg, Ritzingen, Frankfurt on the Main, and at Cologne. Towards the end of his life he went to Holland, but during the greatest part of his residence in that country he was confined to a sick bed. He died at Amsterdam in 1668, after having reached a very advanced age. Like Paracelsus, whom he held in high estimation, he was in open hostility with the Galenical physicians of his time. This led him into various controversies, and induced him to publish various apologies, most of which still remain among his writings. One of the most curious of these apologies is the one against Farner. To this man Glauber had communicated certain secrets of his own, which were at that time considered as of great value, Farner binding himself not to communicate them to any person. This obligation he not only broke, but publicly deprecated the skill and integrity of Glauber, and offered to communicate to others, for stipulated sums, a set of secrets of his own, which he vaunted of as particularly valuable. Glauber examines these secrets, and shows that every one of them possessed of any value had been communicated by himself to Farner, and to put an end to Farner's unfair attempt to make money by selling Glauber's secrets, He, in this apology, communicates the whole processes to the public. Glauber's works were published in Amsterdam, partly in Latin and partly in the German language. In the year 1689, an English translation of them was published in London by Mr. Christopher Pack, in one large folio volume. Glauber was an alchemist and a believer in the universal medicine, but he did not confine his researches to these two particulars, but endeavored to improve medicine and the arts by the application of chemical processes to them. In his treatise of philosophical furnaces, he does not confine himself to a description of the method of constructing furnaces and explaining the use of them, but gives an account of a vast many processes and medicinal and chemical preparations which he made by means of these furnaces. One of the most important of these preparations was muriatic acid, which he obtained by distilling a mixture of common salt, sulphate of iron, and alum, in one of the furnaces which he describes. He makes known the method of dissolving most of the metals in muriatic acid, and the resulting chlorides, which he denominates oils of the respective metals, constitute in his opinion valuable medicines. He mentions particularly the chloride of gold, and from the mode of preparing it, the solution must have been strong. Yet he recommends it as an internal medicine, which he says may be taken with safety, and is a sovereign remedy in old ulcers of the mouth, tongue, and throat, arising from the French pox, leprosy, scorbut, etc. Thus we see the use of gold as a remedy for the venereal disease did not originate with M. Créchon of Montpellier. This chloride of gold is so violent a poison that it is remarkable that Glauber does not specify the dose that patients laboring under the diseases for which he recommends it ought to take. The sesquichloride of iron he recommends as a most excellent application to ill-conditioned ulcers and cancers. We see from this that the use of iron in cancers, lately recommended, is not so new a remedy as has been supposed. He mentions the violent action of chloride of mercury, obviously corrosive sublimate, and says that he saw a woman suddenly killed by it, being administered internally by a surgeon. Butter of antimony he first recognized as nothing else than a combination of chlorine and antimony. Before his time it had been always supposed to contain mercury. He describes the method of obtaining sulphuric acid by distilling sulphate of iron, gives an account of the mode of obtaining sulphate of iron and sulphate of copper in crystals. The method of obtaining nitric acid from niter by means of alum was much improved by him. He gives a particular detail of the way of obtaining fulminating gold. This fulminating gold, he says, is of little use in medicine, but he gives a method of preparing from it a red tincture of gold, which he considers as one of the most useful and efficacious of all medicines. This tincture is nothing else than chloride of gold. It would take up too much space to attempt an analysis of all the curious facts and preparations described in this treatise on philosophical furnaces, but it will repay the perusal of any person who will take the trouble to look into it. All the different pharmacopoeias of the 17th century borrowed from it largely. The third part of this treatise is peculiarly interesting. It will be seen that Glauber had already thought of the peculiar efficacy of applying solutions of sulphur, etc., to the skin, and had anticipated the various vapor and gaseous baths which have been introduced in Vienna and other places during the course of the present century, and considered as new, and as constituting an important era in the healing art. In the fourth part, he not only treats of the docimastic processes, so well described by Agricola and Keren, but gives us the method of making glass, and of imitating the precious stones by means of colored glasses. The fifth part is peculiarly valuable. In it he treats of the methods of preparing lutes for glass vessels, of the construction and qualities of crucibles, and of the vitrification of earthen vessels. Another of his tracts is called the Mineral Work, the object of which is to show the method of separating gold from flints, sand, clay, and other minerals by the spirit of salt, muriatic acid, which otherwise cannot be purged. Also a panacea or universal antimonial medicine. This panacea was a solution of deutoxide of antimony in pyrotartaric acid. Glauber gives a most flattering account of its efficacy in removing the most virulent diseases, particularly all kinds of cutaneous eruptions. The second and third parts of the mineral work are entirely alchemistical. In the treatise called Miraculum Mundi, his chief object is to write a panegyric on sulphate of soda, of which he was the discoverer, and to which he gave the name of sal mirabile. The high terms in which he speaks of this innocent salt are highly amusing, and serve well to show the spirit of the age, and the dreams which still continue to haunt the most laborious and sober-minded chemists. The sal mirabile was not merely a purgative, a virtue which it certainly possesses in a high degree, being as mild a purgative, perhaps the very best, of all the saline preparations yet tried, but it was a universal medicine, a panacea, a cure for all diseases. Nor was Glauber contented with this, but pointed out many uses in the various arts and manufactures for which in his opinion it was admirably fitted. But by far the fullest account of this sal mirabile is given by him in his treatise on the nature of salts. I shall satisfy myself with giving the titles of his other tracts. Every one of them contains facts of considerable importance, not to be found in any chemical writings that preceded him. But to attempt to connect these facts into one point of view would be needless, because they are not such as would be likely to interest the general reader. 1. The consolation of navigators. This gives an account of a method by which sailors may carry with them a great deal of nourishment in very small bulk. The method consists in evaporating the wort of malt to dryness, and carrying the dry extract to sea. This method has been had recourse to in modern times, and has been found to furnish an effectual remedy against the scurvy. He recommends also the use of muriatic acid as a remedy for thirst, and a cure for the scurvy. 2. A true and perfect description of the extracting good tartar from the lees of wine. 3. The first part of the Prosperity of Germany, in which is treated of the concentration of wine, corn, and wood, and the more profitable use of them than has hitherto been. 4. The second part of the Prosperity of Germany, wherein is shown by what means minerals may be concentrated by niter and turned into metallic and better bodies. 5. The third part of the Prosperity of Germany, in which is delivered the way of most easily and plentifully extracting saltpeter out of various subjects, everywhere obvious and at hand, together with a succinct explanation of Paracelsus' prophecy, that is to say, in what manner it is to be understood the Northern Lion will institute or plant his political or civil monarchy, and that Paracelsus himself will not abide in his grave, and that a vast quantity of riches will offer itself. Likewise who the artist Elias is, of whose coming in the last days, and his disclosing abundance of secrets, Paracelsus and others have predicted. 6. The fourth part of the Prosperity of Germany, in which are revealed many excellent useful secrets, and such as are serviceable to the country, and withal several preparations of efficacious cates, extracted out of the metals, and appointed to physical uses, as also various confections of golden potions. To which is also adjoined a small treatise, which maketh mention of my laboratory, in which there shall be taught and demonstrated, for the public good and benefit of mankind, wonderful secrets, and unto everybody most profitable, but hitherto unknown. 7. The fifth part of the Prosperity of Germany, clearly and solidly demonstrating, and as it were showing with the fingers, what alchemy is, and what benefit may, by the help thereof, be gotten everywhere and in most places of Germany, written and published to the honor of God, the giver of all good things primarily, and to the honor of all the great ones of the country, and for the health, profit, and assistance against foreign invasions of all their inhabitants that are by due right and obedience subject unto them. 8. The sixth and last part of the Prosperity of Germany, in which the arcanas already revealed in the fifth part are not only illustrated and with a clear elucidation, but also such are manifested as are most highly necessary to be known for the defense of the country against the Turks, together with an evident demonstration adjoined, showing that both a particular and universal transmutation of the imperfect metals into more perfect ones by salt and fire is most true, and withal, by what means any one, that is endued with but a mean knowledge in managing the fire, may experimentally try the truth hereof in 24 hours space. 9. The first century of Glauber's wealthy storehouse of treasures. Many of the processes given in this treatise are mystically stated or even concealed. 10. The second, third, fourth, and fifth century of Glauber's wealthy storehouse of treasures. 11. New chemical light, being a revelation of a certain new invented secret, never before manifested to the world. This was a method of extracting gold from stones. Probably the gold found by Glauber in his processes existed in some of the regions employed. This at least is the most natural way of accounting for the result of Glauber's trials. 12. The Spagyrical Pharmacopoeia or Dispensatory. In this book he treats chiefly of medicines peculiarly his own. One of those on which he bestows the greatest praise is secret sal ammoniac, or sulfate of ammonia. He describes the method of preparing this salt by saturating sulfuric acid with ammonia. He informs us that it was much employed by Paracelsus and von Helmont, who distinguished it by the name of alkahest. 13. Book of Fires, full of enigmas. 14. Treatise of the three principles of metals, viz. sulfur, mercury, and salt of philosophers, how they may be profitably used in medicine, alchemy, and other arts. 15. A short book of dialogues, chiefly relating to alchemy. 16. Proserpine, or the goddess of riches. 17. Of Elias the artist. 18. Of the three most noble stones generated by three fires. 19. Of the purgatory of philosophers. 20. Of the secret fire of philosophers. 21. A treatise concerning the animal stone. John Kunkel, who acquired a high reputation as a chemist, was born in the Duchy of Schleswig in the year 1630. His father was a trading chemist, or apothecary, and Kunkel himself had, in his younger years, paid great attention to the business of an apothecary. He had also diligently studied the different processes of glass making, and had paid particular attention to the assaying of metals. In the year 1659 he was chamberlain, chemist, and superintendent of apothecaries to the Dukes Francis Charles and Julius Henry of Lauenburg. While in this situation, he examined many pretended transmutations of metals, and undertook other researches of importance. From this situation he was invited by John George II, Elector of Saxony, on the recommendation of Dr. Langelot and Councillor Vogt, as chamberlain and superintendent of the Elector's laboratory, with a considerable salary. From this situation he went to Berlin, where he was chemist to the Elector Frederick William, after whose death his laboratory and glass house were accidentally burnt. From Berlin he was invited to Stockholm by Charles XI, King of Sweden, who gave him the title of Councillor of Metals and raised him to the rank of a nobleman. Here he died in 1702, in the 72nd year of his age. Kunkel's greatest discovery was the method of extracting phosphorus from urine. This curious substance had been originally discovered by Brandt, a chemist of Hamburg, in the year 1669, as he was attempting to extract from human urine a liquid capable of converting silver into gold. He showed a specimen of it to Kunkel, with whom he was acquainted. Kunkel mentioned the fact as a piece of news to one Kraft, a friend of his in Dresden, where he then resided. Kraft immediately repaired to Hamburg and purchased the secret from Brandt for 200 Rix dollars, doubtless exacting from him at the same time a promise not to reveal it to any other person. Soon after, he exhibited the phosphorus publicly in Britain and in France, whether for money or not does not appear. Kunkel, who had mentioned to his friend his intention of getting possession of the process, being vexed at the treacherous conduct of Kraft, attempted to discover it himself, and after 3 or 4 years' labour he succeeded, though all that he knew from Brandt was, that urine was the substance from which the phosphorus was procured. In consequence of this success, phosphorus was at first distinguished by the epithet of Kunkel added to the name. Kunkel published in 1678 a treatise on phosphorus, in which he describes the properties of this substance, at that time a subject of great wonder and curiosity. In this treatise he proposes phosphorus as a remedy of some efficacy, and gives a formula for preparing pills of it, to be taken internally. It is therefore erroneous to suppose, as has been done, that the introduction of this dangerous remedy into medicine is a modern discovery. Kunkel appears to have been acquainted with nitric ether. One of the most valuable of his books is his treatise on glassmaking, which was translated into French, and which till nearly the end of the 18th century constituted by far the best account of glassmaking in existence. The following is a list of the most important of his works. 1. Observations on fixed and volatile salts, potable gold and silver, spiritus mundi, etc. Also of the color and smell of metals, minerals, and bitumens. This tract was published at Hamburg in 1678, and has been several times reprinted since. 2. Chemical remarks on the chemical principles, acid, fixed and volatile alkaline salts, in the 3 kingdoms of nature, the mineral, vegetable, and animal, likewise concerning their color and smell, etc., with a chemical appendix against non-entia chymica. 3. Treatise of the phosphorus mirabilis and its wonderful shining pills, together with a discourse on what was formerly rightly named nitre, but is now called the blood of nature. 4. An epistle against spirit of wine without an acid. 5. Touchstone de acido et urinoso, sale calido et frigido. 6. Ars Vitraria experimentalis. 7. Collegium Physico-Chemicum Experimentale, or Laboratorium Chemicum. End of section 24.
Section 25 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 7, of Glauber, Lemery, and some other chemists of the end of the 17th century, Part 2. Nicolas Lemery, the first Frenchman who completely stripped chemistry of its mysticism, and presented it to the world in all its native simplicity, deserves our particular attention, in consequence of the celebrity which he acquired and the benefits which he conferred on the science. He was born at Rouen on the 17th of November, 1645. His father, Julien Lemery, was procureur of the Parliament of Normandy, and a Protestant. His son, when very young, showed a decided partiality for chemistry, and repaired to an apothecary in Rouen, a relation of his own, in hopes of being initiated into the science, but finding that little information could be procured from him, young Lemery left him in 1666 and went to Paris, where he boarded himself with M. Glauber, at that time demonstrator of chemistry at the Jardin du Roi. Glauber was a true chemist, according to the meaning at that time fixed to the term, full of obscure notions, unwilling to communicate what knowledge he possessed, and not at all sociable. In 2 months Lemery quitted his house in disgust. and set out with the resolution to travel through France and pick up chemical information as best he could from those who were capable of giving him information on the subject. He first went to Montpellier, where he boarded in the house of M. Verchant, an apothecary in that town. With his situation there he was so much pleased that he continued in it for 3 years. He employed himself assiduously in the laboratory, and in teaching chemistry to a number of young students who boarded with his host. Here his reputation gradually increased so much that he drew round him the professors of the Faculty of Medicine of Montpellier, and all the curious of the place, to witness his experiments. Here, too, he practised medicine with considerable success. After travelling through all France, he returned to Paris in 1672. Here he frequented the different scientific meetings at that time held in that capital, and soon distinguished himself by his chemical knowledge. In a few years he got a laboratory of his own, commenced apothecary, and began to give public lectures on chemistry, which were speedily attended by great crowds of students from foreign countries. For example, we are told that on one occasion 40 Scotchmen repaired to Paris on purpose to hear his lectures, and those of M. Duvernay on anatomy. The medicines which he prepared in his laboratory became fashionable and brought him a great deal of money. The magistery of bismuth, or pearl white, which he prepared as a cosmetic, was sufficient, we are told, to support the whole expense of his house. In the year 1675 he published his Cours de Chimie, certainly one of the most successful chemical books that ever appeared. It ran through a vast number of editions in a few years, and was translated into Latin, German, Spanish, and English. In 1681 he began to be troubled in consequence of his religious opinions. Louis XIV. Was at that time in the height of his glory, entirely under the control of his priests, and zealously bent upon putting an end to the reformed religion in his dominions. Indeed, from the infamous conduct of Charles II. Of England, and the bigotry of his successor, a prospect was opened to him, and of which he was anxious to avail himself, of annihilating the reformed religion altogether, and of plunging Europe a second time into the darkness of Roman Catholicism. Lemery found it expedient in 1683 to pass over into England. Here he was well received by Charles II., but England was at that time convulsed with those religious and political struggles which terminated 5 years afterwards in the Revolution. Lemery, in consequence of this state of things, found it expedient to leave England and return to France. He took a doctor's degree at Caen in Normandy, and, returning to Paris, he commenced all at once practitioner in medicine and surgery, apothecary, and lecturer on chemistry. The Edict of Nantes was revoked in 1685, when James II. Had assured Louis of his intention to overturn the established religion and bring Great Britain again under the dominion of the Pope. Lemery was obliged to give up practice and conceal himself in order to avoid persecution. Finding his success hopeless as long as he continued a Protestant, he changed his religion in 1686 and declared himself a Roman Catholic. This step secured his fortune. He was now as much caressed and protected by the court and the clergy as he had been formerly persecuted by them. In 1699, when the Academy of Sciences was new modelled, he was appointed associated chemist, and on the death of Bourdelin, before the end of that year, he became a pensioner. He died on the 19th of June, 1715, at the age of 70, in consequence of an attack of palsy, which terminated in apoplexy. Besides his system of chemistry, which has been already mentioned, he published the following works: 1. Pharmacopée universelle, contenant toutes les opérations de pharmacie qui sont en usage dans la médecine. 2. Traité universel des drogues simples mis en ordre alphabétique. 3. Traité de l'antimony, contenant l'analyse chimique de ces minéraux. Besides these works, 5 different papers by Lemery were printed in the Memoirs of the French Academy between 1700 and 1709 inclusive. These are as follow: 1. Explication physique et chimique des feuilles souterraines, des tremblements de terre, des ouragans, des éclairs et du tonnerre. This explanation is founded on the heat and combustion produced by the mutual action of iron fillings and sulphur on each other when mixed in large quantities. 2. Du camphre. 3. Du miel et de son analyse chimique. 4. De la urine des vaches, de ses effets en médecine et de son analyse chimique. 5. Réflexions et expériences sur des sublimes corrosifs. It appears from this paper that in 1709, when Lemery wrote, corrosive sublimate was considered as a compound of mercury with the sulphuric and muriatic acids. Lemery's statement that he made corrosive sublimate simply by heating a mixture of mercury and decrepitated salt is not easily explained. Probably the salt which he had employed was impure. This is the more likely because, from his account of the matter which remained at the bottom of the matrace after sublimation, it must have either contained peroxide of iron or peroxide of mercury, for its color, he says, was red. M. Lemery left a son who was also a member of the French Academy, an active chemist, and author of various papers, in which he endeavours to give a mechanical explanation of chemical phenomena. Another very active member of the French Academy, at the same time with Lemery, was M. William Homberg, who was born on the 8th of January 1652 at Batavia, in the island of Java. His father, John Homberg, was a Saxon gentleman who had been stripped of all his property during the 30 Years' War. After receiving some education by the care of a relation, he went into the service of the Dutch East India Company, and got the command of the arsenal at Batavia. There he married the widow of an officer, by whom he had 4 children, of whom William was the second. His father quitted the service of the India Company and repaired to Amsterdam with his family. Young Homberg studied with avidity. He devoted himself to the law, and in 1674 was admitted advocate of Magdeburg, but his taste for natural history and science was great. He collected plants in the neighborhood, and made himself acquainted with their names and uses. At night he studied the stars, and learned the names and positions of the different constellations. Thus he became a self-taught botanist and astronomer. He constructed a hollow, transparent celestial globe, on which, by means of a light placed within, the principal fixed stars were seen in the same relative positions as in the heavens. Otto Guericke was at that time burgomaster of Magdeburg. His experiments on a vacuum and his invention of the air pump are universally known. Homberg attached himself to Otto Guericke, and this philosopher, though fond of mystery, either explained to him his secrets, in consequence of his admiration of his genius, or was unable to conceal them from his penetration. At last Homberg, quite tired of his profession of advocate, left Magdeburg and went to Italy. He sojourned for some time at Padua, where he devoted himself to the study of medicine, anatomy, and botany. At Bologna he examined the famous Bologna stone, the nature of which had been almost forgotten, and succeeded in making a pyrophorus out of it. At Rome he associated particularly with Mark Antony Celio, famous for the large glasses for telescopes which he was able to grind. Nor did he neglect painting, sculpture, and music, pursuits in which, at that time, the Italians excelled all other nations. From Italy he went to France, and thence passed into England, where he wrought for some time in the laboratory of Mr. Boyle, at that time one of the most eminent schools of science in Europe. He then passed into Holland, studied anatomy under de Graaf, and after visiting his family went to Wittenberg, where he took the degree of Doctor of Medicine. After this he visited Baldwin and Kunkel to get more accurate information respecting the phosphorus which each had respectively discovered. He purchased a knowledge of Kunkel's phosphorus by giving in exchange a meteorological toy of Otto Guericke, now familiarly known, by which the moisture or dryness of the air was indicated. A little man came out of his house and stood at the door in dry weather, but retired under cover in moist weather. He next visited the mines of Saxony, Bohemia, and Hungary. He even went to Sweden to visit the copper mines of that country. At Stockholm he wrought in the chemical laboratory, lately established by the king, along with Herne, and contributed considerably to the success of that new establishment. He repaired a second time to France, where he spent some time actively engaged with the men of science in Paris. His father strongly pressed him to return to Holland and settle as a physician. He at last consented, and the day of his departure was come when, just as he was going into his carriage, he was stopped by a message from M. Colbert on the part of the king. Offers of so advantageous a nature were made of him if he would consent to remain in France, that after some consideration he was induced to embrace them. In 1682 he changed his religion and became Roman Catholic. This induced his father to disinherit him. In 1688 he went to Rome, where he practiced medicine with considerable success. A few years after he returned to Paris, where his knowledge and discoveries gave him a very high reputation. In 1691 he became a member of the Academy of Sciences, and got the direction of the laboratory belonging to the Academy. This enabled him to devote his undivided attention to chemical investigations. In 1702 he was talked into the service of the Duke of Orleans, who gave him a pension and put him in possession of the most splendid and complete laboratory that had ever been seen. He was presented with the celebrated burning glass of M. Tschirnhaus by the Duke of Orleans, and was enabled by means of it to determine many points that had hitherto been only conjectural. In 1704 he was made first physician to the Duke of Orleans, who honored him with this particular esteem. This appointment, obliging him to reside out of Paris, would have made it necessary for him to resign his seat in the Academy, had not the king made a special exemption in his favor. In 1708 he married a daughter of the famous M. Dodart, to whom he had been long attached. Some years after he was attacked by a dysentery, which was cured, but returned from time to time. In 1715 it returned with great violence, and Homburg died on the 24th of September. His knowledge was uncommonly great in almost every department of science. His chemical papers were very numerous, though there are few of them in this advanced period of the science that are likely to claim much attention from the chemical world. His pyrophorus, of which he has given a description in the Mémoires de l'Académie, was made by mixing together human feces and alum, and roasting the mixture till it was reduced to a dry powder. It was then exposed in a mattress to a red heat till everything combustible was driven off. Any combustible will do as a substitute for human feces. Gum, flour, sugar, charcoal may be used. When a little of this phosphorus is poured upon paper, it speedily catches fire and kindles the paper. Davy first explained the nature of this phosphorus. The potash of the alum is converted into potassium, which, by its absorption of oxygen from the atmosphere, generates heat, and sets fire to the charcoal contained in the powder. Homburg's papers printed in the Memoirs of the French Academy amount to 31. They are to be found in the volumes for 1699 to 1714 inclusive. M. Geoffroy, who was a member of the Academy about the same time with Lemery and Homburg, though he outlived them both, and who was an active chemist for a considerable number of years, deserves also to be mentioned here. Stephen Francis Geoffroy was born in Paris on the 13th of February 1672, where his father was an apothecary. While a young man, regular meetings of the most eminent scientific men of Paris were held in his father's house, at which he was always present. This contributed very much to increase his taste for scientific pursuits. After this he studied botany, chemistry, and anatomy in Paris. In 1692 his father sent him to Montpellier to study pharmacy in the house of a skilful apothecary, who at the same time sent his son to Paris to acquire the same art in the house of M. Geoffroy senior. Here he attended the different classes in the university, and his name began to be known as a chemist. After spending some time in Montpellier, he travelled round the coast to see the principal seaports, and was at St. Malo's in 1693 when it was bombarded by the British fleet. In 1698 Count Tallard, being appointed ambassador extraordinary to London, made choice of M. Geoffroy as his physician, though he had not taken a medical degree. Here he made many valuable acquaintances, and was elected a Fellow of the Royal Society. From London he went to Holland, and thence into Italy in 1700, when he went in the capacity of physician to M. de Louvois. The great object of M. Geoffroy was always natural history and materia medica. In 1693 he had subjected himself to an examination, and he had been declared qualified to act as an apothecary, but his own object was to be a physician, while that of his father was that he should succeed himself as an apothecary. This in some measure regulated his education. At last he declared his intentions, and his father agreed to them. He became a Bachelor of Medicine in 1702, and Doctor of Medicine in 1704. In 1709 he was made Professor of Medicine in the Royal College. In 1707 he began to lecture on chemistry at the Jardin du Roi, in place of M. Fagan, and continued to teach this important class during the remainder of his life. In 1726 he was chosen Dean of the Faculty of Medicine, and after the 2 years for which he was elected was finished, he was again chosen to fill the same situation. There existed at that time a lawsuit between the physicians and surgeons in Paris, a kind of civil war very injurious to both, and the mildness and suavity of his manners fitted him particularly for being at the head of the body of physicians during its continuance. He became a member of the Academy in 1699, and died on the 6th of January, 1731. The most important of all his chemical labours, and for which he will always be remembered in the annals of the science, was the contrivance which he fell upon, in 1718, of exhibiting the order of chemical decompositions under the form of a table. This method was afterwards much enlarged and improved. Such tables are now usually known by the name of tables of affinity, and, though they have been of late years somewhat neglected, there can be but one opinion of their importance when properly constructed. M. Geoffroy first communicated to the French chemists the mode of making Prussian blue, as Dr. Woodward did to the English. Claude Joseph Geoffroy, the younger brother of the preceding, was also a member of the Academy of Sciences, and a zealous cultivator of chemistry. Many of his chemical papers are to be found in the Memoirs of the French Academy. He demonstrated the composition of sal ammoniac, which however was known to Glauber. He made many experiments upon the combustion of the volatile oils by pouring nitric acid on them. He explained the pretended property which certain waters have of converting iron into copper, by showing that in such cases copper was held in solution in the water by an acid, and that the iron merely precipitated the copper, and was dissolved and combined with the acid in its place. He pointed out the constituents of the 3 vitriols, the green, the blue, and the white, showing that the 2 former were combinations of sulphuric acid with oxides of iron and copper, and the latter a solution of lapis calaminaris, carbonate of zinc, in the same acid. He has also a memoir on the emeticity of antimony, tartar emetic, and kermes mineral, but it is rather medical than chemical. He determined experimentally the nature of the salt of Sienna, or Rochelle salt, and showed that it was obtained by saturating cream of tartar with carbonate of soda and crystallizing. It is curious that this discovery was made about the same time by M. Boulduc. I have noticed only a few of the papers of M. Geoffroy junior, because though they all do him credit and contributed to the improvement of chemistry, yet none of them contain any of those great discoveries which stand as landmarks in the progress of science, and constitute an era in the history of mankind. For the same reason I omit several other names that, in a more minute history of chemistry, would deserve to be particularized. End of section 25.
Section 26 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 8 of the Attempts to Establish a Theory in Chemistry, Part 1. Bacon, Lord Verulam, as early as the commencement of the 17th century, had pointed out the importance of chemical investigations and had predicted the immense advantages which would result from the science when it came to be properly cultivated and extended. But he did not himself attempt either to construct a theory of chemistry or even to extend it beyond the bounds which it had reached before he began to write. Neither did Boyle, notwithstanding the importance of investigations, and his comparative freedom from the prejudices of the alchemists, attempt anything like a theory of chemistry, though the observations which he made in his Skeptical Chemist had considerable effect in overturning, or at least in hastening, the downfall of the absurd chemical opinions which at the time prevailed, and the puerile hypotheses respecting the animal functions, and the pathology and treatment of diseases founded on these opinions. The first person who can with propriety be said to have attempted to construct a theory of chemistry was Becher. John Joachim Becher, one of the most extraordinary men of the age in which he lived, was born at Spires, in Germany, in the year 1635. His father, as Becher himself informs us, was a very learned Lutheran preacher. As he lost his father when he was very young, and as that part of Germany where he lived had been ruined by the 30 Years' War, his family was reduced to great poverty. However, his passion for information was so great that he contrived to educate himself by studying what books he could procure, and in this way acquired a great deal of knowledge. Afterwards he travelled through the greatest part of Germany, Italy, Sweden, and Holland. In the year 1666 he was appointed public professor of medicine in the University of Mentz, and soon after chief physician to the Elector. In that capacity he took up his residence in Munich, where he was furnished by the Elector with an excellent laboratory, but he soon fell into difficulties, the nature of which does not appear, and was obliged to leave the place. He took refuge in Vienna, where, from his knowledge of finance, he was appointed chamberlain to Count Zinzendorf, and through him acquired so much importance in the eyes of the court that he was named a member of the newly erected College of Commerce, and obtained the title of Imperial Commercial Councillor and Chamberlain. But here also he speedily raised up so many enemies against himself that he found it necessary to leave Vienna and to carry with him his wife and children. He repaired to Holland and settled at Haarlem in 1678. Here he was likely to have been successful, but his enemies from Vienna followed him and obliged him to leave Holland. In 1680 we find him in Great Britain, where he examined the Scottish lead mines and smelting works, and in 1681 and 1682 he traversed Cornwall and studied the mines and smelting works of that great mining county. Here he suggested several improvements and ameliorations. Soon after this an advantageous proposal was made to him by the Duke of Mecklenburg-Güstrow by means of Count Zinzendorf, but all his projects were arrested by his death, which took place in the year 1682. It is said that he died in London, but I have not been able to find any evidence of this. It would be a difficult task to particularize his various discoveries, which are scattered through a multiplicity of writings. He was undoubtedly the first discoverer of boracic acid, though the credit of the discovery has usually been given to Homburg. But then he gives no account of boracic acid, nor does he seem to have attended to its qualities. The following is a list of Becher's writings. 1. Metallurgia, or the natural science of metals. 2. Institutiones Chymica. 3. Parnassus Medicinalis Illustrata. 4. Oedipus Chemicus seu Institutiones Chymica. 5. Acta Laborati Chimici Monacensis su Physica Subterranea. This, which is the most important of all his works, is usually known by the name of Physica Subterranea. This is the sole title affixed to it in the edition published at Leipzig in 1703, to which Stahl has prefixed a long introduction. It is divided into 7 sections. In the first he treats of the creation of the world. In the second he gives a chemical account of the motions and changes which are constantly going on in the earth. In the third he treats of the 3 principles of all bodies, which he calls earths. The first of these principles of metals and stones is the fusible or stony earth. The second principle of minerals is the fat earth, improperly called sulfur. The third principle is the fluid earth, improperly called mercury. In the fourth section he treats of the action of subterraneous principles, or the formulation of mixts. In the fifth he treats of the solution of the 3 classes of mixts, animals, vegetables, and metals. In the sixth he treats of mixts, in which he gives their chemical constituents. This section is very curious, because it gives Becker's views of the constitution of compound bodies. It will be seen from it that he had much more correct notions of the real objects of chemistry than any of his contemporaries. In the 7th and last section he treats of the accidents and physical affectations of subterraneous bodies. 6. Experimentum chemicum novum quo artificialis et instantanea metallorum generatio et transmutatio ad oculum demonstrator. This constitutes the first supplement to the Physica Subterranea. 7. Supplementum secundum in Physicum Subterranea demonstratio philosophica su theses chimica veritatem et possibilitatem transmutationis metallorum in aurum evincentes. 8. Trifolium Beckerianum Hollandicum. 9. Experimentum novum et curiosum de minera arenaria perpetua, sive podromus historiae, su propositionis praep D. Hollandiae, ordinibus ab authore facte circa auri extractionem mediante arena litorali per modum minere perpetua su operationis magna fusore cum emolumento, loco supplementi tertii in physicum suum subterraneum. 10. Chemical Luckpot, or Great Chemical Agreement, in a collection of 1,500 chemical processes. 11. Foolish Wisdom and Wise Folly. 12. Magnalia Natura. 13. Tripus Hermeticus Fatidicus Pendens Oracula Chemica su I Laboratorium Portatile cum methodo vere spagiricae su juxta exigentium natura laborandi. Accessit pro praxi et exemplo. 2. Centrum mundi concatenatum su duum veratus hermeticus s magnorum duorum productorum nitri et salis textura et anatomia atque in omnium precedentium confirmationem adjunctum est. 3. Alphabetum minerale su viginti quatuor theses de subterraneorum mineralium genesi textura et analysi his accessit concordantia mercurii lunae et menstruorum. 14. Chemical Rose Garden. 15. Pantaleon de Lavartus. 16. Beccari, Lancelotti, etc. Epistolae Quatuor Chimica. Becker's great merit was the contrivance of a chemical theory, by which all the known facts were connected together and deduced from one general principle. But as this theory was adopted and considerably modified by Stahl, it will be better to lay a sketch of it before the reader. After mentioning a few particulars of the life and labors of one of the most extraordinary men whom Germany has produced, a man who, in spite of the moroseness and haughtiness of his character, and in spite of the barbarity of his style, raised himself to the very first rank as a man of science, and had the rare or almost unique fortune of giving laws at the same time to 2 different and important sciences, which he cultivated together, without letting his opinions respecting the one influence him with regard to the other. These sciences were chemistry and medicine. George Ernest Stahl was born at Ansbach in the year 1660. He studied medicine at Jena under George Wolfgang Wedel, and got his doctor's degree at the age of 23. Immediately after this he began his career as a public lecturer. In 1687 the Duke of Weimar gave him the title of physician to the court. In 1694 he was named, at the solicitation of Frederick Hoffmann, second professor of medicine in the University of Halle, which had just been established. Hoffmann and he were at that time great friends, though they afterwards quarrelled. Both of them were men of the very highest talents, and both were the founders of medical systems which, of course, each was anxious to support. Hoffmann had greatly the superiority in elegance and clearness of style, and in all the amenities of polite manners, but perhaps the moroseness of Stahl, and the obscurity, or rather mysticism of his style, contributed equally with the more amicable qualities of Hoffmann to excite the attention and produce the veneration with which he was viewed by his pupils, and, indeed, by the world at large. At Halle he continued as a teacher of medicine for 22 years. In 1716 he was appointed physician to the King of Prussia. In consequence of this appointment he left Halle and resided in Berlin, where he died in the year 1734, in the 75th year of his age. Notwithstanding the great figure that Stahl made as a chemist, there is no evidence that he ever taught that science in any public school. The Berlin Academy had been founded under the superintendence of Leibniz, who was its first president, and therefore existed when Stahl was in Berlin, but till it was renovated in 1745 by Frederick the Great, this academy possessed but little activity, and could scarcely, therefore, have stimulated Stahl to attend to chemical science. However, his Chemia Rationalis et Experimentalis was published in 1720, while he resided in Berlin. The same date is appended to the preface of his Fundamenta Chymica, but from some expressions in that preface, it must, I should think, have been written not by Stahl, but by some other person. I suspect that the book had been written by some of his pupils, from the lectures of the author while at Halle. If this was really the case, it was obvious that Stahl must have taught chemistry as well as medicine in the University of Halle. Stahl's medical theory is not less deserving of notice than his chemical, but it is not the object of this work to enter into medical speculations. Like van Helmont, he resolved all diseases into the actions of the soul, which was not merely the former of the body, but its ruler and regulator. When any of the functions are deranged, the soul exerts itself to restore them again to their healthy state, and she accomplishes this by what in common language is called disease. The business of a medical man, then, is not to prevent diseases or to stop them short when they appear, because they are the efforts of the soul, the vis medicatrix natura, to restore the deranged state of the functions, but he must watch these diseases and prevent the symptoms from becoming too violent. He must assist nature to produce the intended effect, and check her exertions when they become abnormal. It was a kind of modification of this theory, or rather a mixture of the Stahlian and Hoffmannian theories, that Dr. Cullen afterwards taught in Edinburgh with so much éclat. And these opinions, so far as medical theories have any influence on practice, still continue in some measure prevalent. Indeed, much of the vulgar practice followed by medical men, chiefly in consequence of the education which they have received, is deduced from these two theories. But it would be too great a digression from the object of this work to enter into any details. Suffice it to say that the rival theories of Hoffmann and Stahl for many years divided the medical world in Germany, if not in the greater part of Europe. It was no small matter of exultation to so young a medical school as Halle to have at once within its walls two such eminent teachers as Hoffmann and Stahl. Let us turn our attention to the chemical writings of Stahl. Of these the most important is his Fundamenta Chymica Dogmatica et Experimentialis. It is divided, like the chemistry of Boerhaave, into a theoretical and practical part. The perusal of it is very disagreeable, as it is full of German words and phrases, and symbols are almost constantly substituted for words, as was at the time the custom. His definition of chemistry is much more exact than Boerhaave's. It is, according to him, the art resolving compound bodies into their constituents, and of again forming them by uniting these constituents together. He is inclined to believe with Becker that the simple principles are 4 in number. The mixts are compounds of these principles, and he shows by the doctrine of permutations that if we suppose the simple principles 4, then the number of mixts will be 40,340. He treats in the first place of mixts, compounds, and aggregates. The first object of chemistry is corruption, the second generation. Of these he treats at considerable length, giving an account of the different chemical processes and of the apparatus employed. He next treats of salts, which he defines mixts composed of water and earth, both simple and pure, and intimately united. The salts are vitriol, alum, nitre, common salt, and sal ammoniac. He next treats of more compound salts. These are sugar, tartar, salts from the animal and salts from the mineral kingdom, and quicklime. After this comes sulfur, cinnabar, antimony, the sulfur of vitriol, the sulfur of nitre, resins, and distilled oils. Then he treats of water, which he divides into aqua humide or common water, and aqua sicca or mercury. Next he treats of earths, which are of two kinds, viz., friable earths, such as clay, loam, sand, etc., and metallic earths, constituting the bases of the metals. He next treats of the metals, and, as a preliminary, we have a description of the method of smelting and operating upon the different metals. The metals are then described successively in the following order: gold, silver, copper, iron, tin, lead, bismuth, zinc, antimony. To this part of the system are added 3 sections. The first treats of mercuries, the second of the philosopher's stone, and the third of the universal medicine. We must not suppose that Stahl was a believer in these ideal compositions. His object was merely to give a history of the different processes which had been recommended by the alchemists. The second part of his work is divided into 2 tracts. The first tract contains 3 sections. The first of these treats the nature of solids and fluids, or solutions and menstrua, of the effects of heat and fire, of effervescence and boiling, of volatilization, of fusion and liquefaction, of distillation, of precipitation, of calcination and incineration, of detonation, of amalgamation, of crystallization and insipation, and of the fixity and firmness of bodies. In the second section we have an account of salts, and of their generation and transmutation, of sulfur and inflammability, of phosphorus, of colors, and of the nature of metals and minerals. In this article he gives short definitions of these bodies and shows how they may be known. The bodies thus defined are gold, silver, iron, copper, lead, tin, mercury, antimony, sulfur, arsenic, vitriol, common salt, nitre, alum, sal ammoniac, alkalis, and salts, viz., muriatic acid, sulfuric, nitric, and sulfurous. In the third section he treats of the method of reducing metallic calces, of the mode of separating metals from their scoria, of the mode of making artificial gems, and finally of the mode of giving copper a golden color. The second tract is divided into 2 parts. The first part is divided into 4 sections. In the first section he treats of the instruments of chemical motion, of fire, of air, of water, of the most subtile earth or salt. In the second section he treats de subjectis, under the several heads of dissolving aggregates, of triturations and solutions, and of calcinations and combustions. In the third section he treats of the object of chemistry under the following heads: of chemical corruption, consisting of compounds from liquids, of the separation of solids and fluids, of mixts, of the solution of compounds from solids. In the fourth section he treats of fermentation. The second part of this second tract treats of chemical generation and is divided into 2 sections. In the first section he treats of the aggregate collection of bodies into fluids and solids. The section treats of compositions under the heads of volatile and solid bodies. He gives in the last article an account of the combination of mixts. The third and last part of this elaborate work discusses 3 subjects, viz., zymotechnia or fermentation, halotechnia or the production and properties of salts, and pyrotechnia, in which the whole of the Stahlian doctrine of phlogiston is developed. This third part has all the appearance of having been notes written down by some person during the lectures of Stahl, for it consists of alternate sentences of Latin and German. It is not at all likely that Stahl himself would have produced such a piebald work, but if he lectured in Latin, as was at that time the universal custom, it was natural for a person occupied in taking down the lectures to write as far as possible in Latin, but when any of the Latin phrases were lost, or did not immediately occur to memory, it were equally natural to write down the meaning of what the professor stated in the language most familiar to the writer, which was undoubtedly the German. End of section 26. Recording by Grognor.
Section 27 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Keren Turton. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 8 of the Attempts to Establish a Theory in Chemistry, Part 2. Another of Stahl's works is entitled Opusculum Chemico-Physico-Medicum, published at Halle in a thick quarto volume in the year 1715. It contains a great number of tracts, partly chemical and partly medical, which it is needless to specify. Perhaps the most curious of them all is his dissertation to show the way in which Moses ground the golden calf to powder, dissolved it in water, and obliged the children of Israel to drink it. He shows that a solution of hypersulphurous sulphuret of potassium has the property of dissolving gold, and he draws as a conclusion from his experiments that this was the artifice employed by Moses. We have seen in the same volume a pretty detailed treatise on metallurgic pyrotechny and dosimacy. This is the more curious because Stahl never appears to have frequented the mines and smelting houses of Germany. He must therefore have drawn his information from books and from experiment. Another of his books is entitled Experimenta, Observations, Animadversions, CCC, numero, an octavo volume printed at Berlin in 1731. Another of his books is entitled Specimen Beturanium. There are also two chemical books of Stahl, which I have seen only in a French translation, viz. Traité de Soufre and Traité de Sets. These are the only chemical writings of Stahl that I have seen. There are probably others. Indeed, I have seen the titles of several other chemical works ascribed to him. But as it is doubtful whether he really wrote them or not, I think it unnecessary to specify them here. Stahl's writings evince the great progress which chemistry had made even since the time of Becher. But it is difficult to say what particular new facts which appear first in his writings were discovered by himself and what by others. I shall not, therefore, attempt any enumeration of them. His reasoning is more subtle, and his views much more extensive and profound than those of his predecessors. The great improvement which he introduced into chemistry was the employment of phlogiston to explain the phenomena of combustion and calcination. This theory had been originally broached by Becher, from whom Stahl evidently borrowed it, but he improved and simplified it so much that the whole credit of it was given to him. It was called the Stahlian theory, and raised him to the highest rank among chemists. The sole objects of chemists for 30 or 40 years after his time was to elucidate and extend his theory. It applied so happily to all the known facts, and was supported by experiments, which appeared so decisive that nobody thought of calling it into question, or of interrogating nature in any other way than he had pointed out. It will be requisite, therefore, before proceeding further with this historical sketch, to lay the outlines of the phlogistic theory before the reader. It was conceived by Becher and Stahl that all combustible bodies are compounds. One of the constituents they supposed to be dissipated during the combustion, while the other constituent remained behind. Now, when combustible bodies are subjected to combustion, some of them leave an acid behind them, while others have a fixed powdery matter possessing the properties of an earth, and called usually the calx of the combustible body. The metals are the substance which leave a calx behind them when burnt, and sulphur and phosphorus leave an acid. With respect to those bodies that would not burn, chemists did not speculate much at first, but afterwards they came to think that they consisted of the fixed substance that remained after combustion. Hence the conclusion was natural that they had already undergone combustion. Thus, quicklime possessed properties very similar to the calces of metals. It was natural, therefore, to consider it a calx, and to believe that if the matter dissipated during combustion could be again restored, lime would be converted into a substance similar to the metals. Combustibility, then, according to this view of the subject, depends upon a principle or material substance existing in every combustible body and dissipated during the combustion. This substance was considered to be absolutely the same in all combustible bodies whatever. Hence the difference between combustible bodies proceeded from the other principle or number of principles with which the common substance is combined. In consequence of this identity, Stahl invented the term phlogiston, by which he denoted this common principle of combustible bodies. Inflammation, with the several phenomena that attend it, depended on the gradual separation of this principle, which being once separated, what remained of the body could no longer be an inflammable substance, but must be similar to the other kinds of matter. It was this opinion, that combustibility is owing to the presence of phlogiston, and inflammation to its escape, that constituted the peculiar theory of Becher, and which was afterwards illustrated by Stahl with so much clearness, and experiments to prove its truth were advanced by him of so much force, that it came to be distinguished by the name of the Stahlian theory. The identity of phlogiston in all combustible bodies was founded upon observations and experiments of so decisive a nature, that after the existence of the principle itself was admitted, they could not fail to be satisfactory. When phosphorus is made to burn, it gives out a strong flame, much heat is evolved, and the phosphorus is dissipated in a white smoke. But if the combustion be conducted within a glass vessel of proper shape, this white smoke will be deposited on the inside of the glass. It quickly absorbs moisture from the atmosphere, and runs into an acid liquid, known by the name of phosphoric acid. If this liquid be put into a platinum crucible, and gradually heated to redness, the water is dissipated, and a substance remains which, on cooling, congeals into a transparent, colourless body like glass. This is dry phosphoric acid. If we now mix phosphoric acid with a quantity of charcoal powder, and heat it sufficiently in a glass retort, taking care to exclude the external air, a portion or the whole of the charcoal will disappear, and phosphorus will be formed, possessed of the same properties that it had before it was subjected to combustion. The conclusion deduced from this process appeared irresistible. The charcoal, or a portion of it, had combined with the phosphoric acid, and both together had constituted the phosphorus. Now, in changing phosphoric acid to phosphorus, we may employ almost any kind of combustible substance that we please, provided it be capable of bearing the requisite heat. They will all equally answer, and will all convert the acid into phosphorus. Instead of charcoal, we may take lamp black, or sugar, or resin, or even several of the metals. Hence it was concluded that all of these bodies contain a common principle which they communicate to the phosphoric acid, and since the new body formed is in all cases identical, the principle communicated must also be identical. Hence, combustible bodies contain an identical principle, and this principle is phlogiston. Sulfur by burning is converted into sulfuric acid, and if sulfuric acid be heated with charcoal, or phosphorus, or even sulfur, it is again converted into sulfur. Several of the metals produce the same effect. The reasoning here was the same as with regard to phosphoric acid, and the conclusion was similar. When lead is kept nearly at a red heat in the open air for some time, being constantly stirred to expose new surfaces to the air, it is converted into the beautiful pigment called red lead. This is a calx of lead. To restore this calx again to the state of metallic lead, we have only to heat it in contact with almost any combustible matter whatever. Pit coal, peat, charcoal, sugar, flour, iron, zinc, etc. All these bodies then must contain one common principle, which they communicate to red lead, and by doing so convert it into lead. This common principle is phlogiston. These examples are sufficient to show the reader the way in which Stahl proved the identity of phlogiston in all combustible bodies, and the demonstration was considered as so complete that the opinion was adopted by every chemist without exception. When we inquire further, and endeavour to learn what qualities phlogiston was supposed to have in its separate state, we find this part of the subject very unsatisfactory, and the opinions very unsettled. Becher and Stahl represented phlogiston as a dry substance, or of an earthy nature, the particles of which are exquisitely subtle, and very much disposed to be agitated, and set in motion with inconceivable velocity. This was called by Stahl motus verticillaris. When the particles of any body are agitated with this kind of motion, the body exhibits the phenomena of heat or ignition, or inflammation, according to the violence and rapidity of the motion. This very crude opinion of the earthy nature of phlogiston appears to have been deduced from the insolubility of most combustible substances in water. If we accept alcohol and ether and gums, very few of them are capable of being dissolved in that liquid. Thus the metals, sulfur, phosphorus, oils, resins, bitumens, charcoal, etc., are well known to be insoluble. Now, at the time that Becher and Stahl lived, insolubility in water was considered as a character peculiar to earthy bodies, and as those bodies which contain a great deal of phlogiston are insoluble in water, though the other constituents be very soluble in that liquid, it was natural enough to conclude that phlogiston itself was of an earthy nature. But though the opinions of chemists about the nature and properties of phlogiston in a separate state were unsettled, no doubts were entertained respecting its existence, and respecting its identity in all combustible bodies. Its presence or its absence produced almost all the changes which bodies undergo. Hence, chemistry and combustion came to be in some measure identified, and a theory of combustion was considered as the same thing with a theory of chemistry. Metals were compounds of calces and phlogiston. The different species of metals depend upon the different species of calx, which each contains, for there are as many calces, each simple and peculiar, as there are metals. These calces are capable of uniting with phlogiston in indefinite proportions. The calx united to a little phlogiston still retains its earthy appearance. A certain additional portion restores the calx to the state of a metal. An enormous quantity of phlogiston, with which some calces, as calx of manganese, are capable of combining, destroys the metallic appearance of the body and renders it incapable of dissolving in acids. The affinity between a metallic calx and phlogiston is strong, but the facility of union is greatly promoted when the calx still retains a little phlogiston. If we drive off the whole phlogiston, we can scarcely unite the calx with phlogiston again, or bring it back to the state of a metal. Hence, the extreme difficulty of reducing the calx of zinc, and even the red calx of iron. The various colors of bodies are owing to phlogiston, and these colors vary with every alteration in the proportion of phlogiston present. It was observed very early that when a metal was converted into a calx, its weight was increased. But this, though known to Becher and Stahl, does not seem to have had any effect on their opinions. Boyle, who does not seem to have been aware of the phlogistic theory, though it had been broached before his death, relates an experiment on tin which he made. He put a given weight of it into an open glass vessel and kept it melted on the fire till a certain portion of it was converted into calx. It was now found to have increased considerably in weight. This experiment he relates in order to prove the materiality of heat. In his opinion, a certain quantity of heat had united to the tin and occasioned the increase of weight. This opinion of Boyle was incompatible with the Stahlian theory, for the tin had not only increased in weight, but had been converted into a calx. It was therefore the opinion of Boyle that calx of tin was a combination of tin and heat. It could not consequently be true that calx of tin was tin deprived of phlogiston. When this difficulty struck the phlogistians, which was not till long after the time of Stahl, they endeavoured to evade it by assigning new properties to phlogiston. According to them, it is not only destitute of weight, but endowed with the principle of levity. In consequence of this property, a body containing phlogiston is always lighter than it would otherwise be, and it becomes heavier when the phlogiston makes its escape. Hence the reason why calx of tin is heavier than the same tin in the metallic state. The increase of weight is not owing, as Boyle believed, to the fixation of heat in the tin, but to the escape of phlogiston from it. Those philosophic chemists who thus refined upon the properties of phlogiston did not perceive that by endowing it with the principle of levity, they destroyed all the other characters which they had assigned to it. What is gravity? Is it not an attraction by means of which bodies are drawn towards each other and remain united? And is there any reason for supposing that chemical attraction differs in its nature from the other kinds of attraction which matter possesses? If, then, phlogiston be destitute of gravity, it cannot possess any attraction for other bodies. If it be endowed with the principle of levity, it must have the property of repelling other bodies, for that is the only meaning that can be attached to the term. But if phlogiston has the property of repelling all other substances, how comes it to be fixed in combustible bodies? It must be united to the calces, or the acids, which constitute the other principle of these bodies, and it could not be united and remain united unless a principle of attraction existed between it and these bases. That is to say, unless it possessed a principle the very opposite of levity. Thus the fact that calces are heavier than the metals from which they are formed in reality overturned the whole doctrine of phlogiston, and the only reason why the doctrine continued to be admitted after the fact was known is, that in these early days of chemistry the balance was scarcely ever employed in experimenting, hence alterations in weight were little attended to or entirely overlooked. We shall see afterwards that when Lavoisier introduced a more accurate mode of experimenting, and rendered it necessary to compare the original weights of the substances employed with the weights of the products, he made use of this very experiment of Boyle, and a similar one made with mercury, to overturn the whole doctrine of phlogiston. The phlogistic school being thus founded by Stahl in Berlin, a race of chemists succeeded him in that capital, who contributed in no ordinary degree to the improvement of the science. The most deservedly celebrated of these were Neumann, Pott, Marggraf, and Eller. Caspar Neumann was born at Zullichau in Germany in 1682. He was early received into favor by the King of Prussia, and traveled at the expense of that monarch into Holland, England, France, and Italy. During these travels he had an opportunity of making a personal acquaintance with the most eminent men of science in all the different countries which he visited. On his return home in 1724 he was appointed professor of chemistry in the Royal College of Physic and Surgery at Berlin, where he delivered a course of lectures annually. During the remainder of his life he enjoyed the situation of superintendent of the Royal Laboratory and apothecary to the King of Prussia. He died in 1737. He was a fellow of the Royal Society, and several papers of his appeared in the Transactions of that learned body. The following is a list of these papers, all of which were written in Latin. 1. Disquisitio de Camphora. 2. De experimento probandi spiritum vini Gallii, per quam usitato sed revera falso et fallaci. Some merchants in Holland, England, Hamburg, and Danzig were in possession of what they considered an infallible test to distinguish French brandy from every other kind of spirit. It was a dusky yellowish liquid. When 1 or 2 drops of it were let fall into a glass of French brandy, a beautiful blue color appeared at the bottom of the glass, and when the brandy is stirred, the whole liquid becomes azure. But if the spirit tried be malt spirit, no such color appears in the glass. Neumann ascertained that the test liquid was merely a solution of sulphate of iron in water, and that the blue color was the consequence of the brandy having been kept in oak casks, and thus having dissolved a portion of tannin. Every spirit will exhibit the same color if it has been kept in oak casks. 3. De Silibus alkino fixis. 4. De camphora thymi. 5. De ambra gricia. His other papers published in Germany are the following. In the Ephemerides. 1. De oleo distillato formicorum atherio. 2. De albumine ovi sessino simili. In the Miscellanea Berlinensia. 1. Meditationes in vinas observationes de aqua per putrefactionem rubra, vulgo pro tali in sanguinem versa habita. 2. Succincta relatio exactis Pomeranius de prodigio sanguinis in palude viso. 3. De prodigio sanguinis ex Pomeranio nunciato. 4. Disquisitio de camphora. 5. De experimento probandi spiritum vini gallicum. 6. De spiritu urinoso caustico. 7. Demonstratio syrupum violarum ad probanda liquida non sufficere. 8. Examen correctiones olei raparum. 9. De vi caustica et conversiona salium alkalino fixorum aeri expositorum in salia neutra. He published separately 1. De salibus alkalino fixis et camphora. 2. De succino opio cariophilus aromaticis et castorio. 3. On saltpeter, sulfur, antimony, and iron. 4. On tea, coffee, beer, and wine. 5. Disquistio de ambragrisia. 6. On common salt, tartar, sal, ammoniac, and ants. After Newman's death, 2 copies of his chemical lectures were published, the first consisting of notes taken by one of his pupils, intermixed with incoherent compilations from other authors, was printed at Berlin in 1740. The other was printed by the booksellers of the Orphan Hospital of Zwickau, the place of Newman's birth, and is said to have been taken from the original papers in the author's handwriting. Of this last, an excellent translation with many additions and corrections was published by Dr. Lewis in London in the year 1759. It was entitled The Chemical Works of Caspar Neumann, M.D., Professor of Chemistry at Berlin, F.R.S., etc., abridged and methodized, with large additions containing the later discoveries and improvements made in chemistry and the arts depending thereon, by William Lewis, M.B., F.R.S., London, 1759. This is an excellent book, and contains many things that still retain their value, notwithstanding the improvements which have been made since in every department of chemistry. End of section 27. Section 28 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Keren Turton. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 8 of the Attempts to Establish a Theory in Chemistry, Part 3. I have reason to believe that the laborious part of this translation and compilation was made by Mr. Chicholm, whom Dr. Lewis employed as his assistant. Dr. Chicholm, when a young man, went to London from Aberdeen, where he had studied at the university and acquired a competent knowledge of Greek and Latin, but no means of supporting himself. On his arrival in London, one of the first things that struck his attention was a Greek book, placed open against the pane of a bookseller's window. Chicholm went up to the window, at which he continued standing till he had perused the whole Greek page thus exposed to his view. Dr. Lewis happened to be in the shop. He had been looking out for a young man whom he could employ to take charge of his laboratory and manage his processes, and who should possess sufficient intelligence to read chemical works for him, and collect out of each whatever deserved to be known, either from its novelty or ingenuity. The appearance and manners of Chicholm struck him, and made him think of him as a man likely to answer the purposes which he had in view. He called him into the shop, and after some conversation with him, took him home and kept him all his life as his assistant and operator. Chicholm was a laborious and painstaking man, and by continually working in Lewis's laboratory, soon acquired a competent knowledge of chemistry. He compiled several manuscript volumes, partly consisting of his own experiments, and partly of collections from other authors. At Dr. Lewis's death, all his books were sold by auction, and these manuscript volumes among the rest. They were purchased by Mr. Wedgwood, senior, who at the same time took Mr. Chicholm into his service and gave him the charge of his own laboratory. It was Mr. Chicholm that was the constructor of the well-known piece of apparatus known by the name of Wedgwood's pyrometer. After his death, the instrument continued still to be constructed for some time, but so many complaints were made of the unequal contraction of the pieces that Mr. Wedgwood, Jr., who had succeeded to the pottery in consequence of the death of his father, put an end to the manufacture of them altogether. John Henry Pott was born at Halberstadt in the year 1692. He was a scholar of Hoffmann and Stahl, and from this last he seems to have imbibed his taste for chemistry. He settled at Berlin, where he became assessor of the Royal College of Medicine and Surgery, inspector of medicines, superintendent of the Royal Laboratory, and dean of the Academy of Sciences of Berlin. He was chosen professor of theoretical chemistry at Berlin, and on the death of Neumann in 1737 he succeeded him as professor of practical chemistry. He was beyond question the most learned and laborious chemist of his day. His erudition indeed was very great, and his historical introductions to his dissertation displays the extent of his reading on every subject of which he had occasion to treat. It has often struck me that the historical introductions which Bergman has prefixed to his papers are several of them borrowed from Pott. The Lithogeognosia of Pott is one of the most extraordinary productions of the age in which he lived. It was the result of a request of the King of Prussia to discover the ingredients of which Saxon porcelain was made. Mr. Pott, not being able to procure any satisfactory information relative to the nature of the substances employed at Dresden, resolved to undertake a chemical examination of all the substances that were likely to be employed in such a manufacture. He tried the effect of fire upon all the stones, earth, and minerals that he could procure, both separately and mixed together in various proportions. He made at least 30,000 experiments in 6 years, and laid the foundation for a chemical knowledge of these bodies. It is to this work of Pott that we are indebted for our knowledge of the effects of heat upon various earthy bodies, and upon mixtures of them. Thus he found that pure white clay, or mixtures of pure clay and quartz sand, would not fuse at any temperature which he could produce, but clay, mixed with lime or with oxide of iron, enters speedily into fusion. Clay also fuses with its own weight of borax. It forms a compact mass with half its weight, and does not concrete into a hard body when mixed with a third of its weight of that salt. Clay fuses easily with fluorspar. It fuses also with twice its weight of protoxide of lead, and with its own weight of sulphate of lime, but with no other proportion tried. It was a knowledge of these mutual actions of bodies on each other, when exposed to heat, that gradually led to the methods of examining minerals by the blowpipe. These methods were brought to the present state of perfection by Assessor Gahn, of Fahlun, the result of whose labours has been published by Berzelius in his treatise on the blowpipe. Pott died in 1777, in the 85th year of his age. His different chemical works, his Lithogeognosia excepted, were collected and translated into French by M. de Marchy in the year 1759, and published in 4 small octavo volumes. The chemical papers contained in these volumes are 32 in number. Some of these papers cannot but appear somewhat extraordinary to a modern chemist. For example, M. Duhamel had published in the Memoirs of the French Academy in the year 1737 a set of experiments on common salt, from which he deduced that its basis was a fixed alkali, which possessed properties different from those of potash, and which of course required to be distinguished by a peculiar name. It is sufficiently known that the term soda was afterwards applied to this alkali, by which name it is known at present. Pott, in a very elaborate and long dissertation on the base of common salt, endeavours to refute these opinions of Duhamel. The subject was afterwards taken up by Margraaf, who demonstrated by decisive experiments that the base of common salt is soda, and that soda differs essentially in its properties from potash. Pott's dissertation on bismuth is of considerable value. He collects in it the statements and opinions of all preceding writers on this metal, and describes its properties with considerable accuracy and minuteness. The same observations apply to his dissertation on zinc. John Theodore Eller of Brockhuser was born on the 29th of November, 1689, at Pletzkau, in the Principality of Anhalt-Bernburg. He was the 4th son of Jobst Hermann Eller, a man of respectable family, whose ancestors were proprietors of considerable estates in Westphalia and the Netherlands. Young Eller received the rudiments of his education in his father's house, from which he went to the University of Quedlinburg, and from thence to the University of Jena in 1709. He was sent thither to study law, but his passion was for natural philosophy, which led him to devote himself to the study of medicine. From Jena he went to Halle, and finally to Leyden, attracted by the reputation of the older Albinus, of Professor Sengard, and the celebrated Boerhaave, at that time in the height of his reputation. The only practical anatomist then in Leyden was M. Bidlu, an old man of 80, and of course unfit for teaching. This induced Eller to repair to Amsterdam to study under Rau, and to inspect the anatomical museum of Ruysch. Bidlu soon dying, Rau was appointed his successor at Leyden, whither Eller followed him, and dissected under him till the year 1716. After taking his degree at Leyden, Eller returned to Germany and devoted a considerable time to the study and examination of the mines of Saxony and the Harz, and the metallurgic processes connected with these mines. From these mines he repaired to France and resumed his anatomical studies under Duverney and Winslow. Chemistry also attracted a good deal of his attention, and he frequented the laboratories of Gros, Lemery, Bolduc, and Homburg, at that time the most eminent chemists in Paris. From Paris he repaired to London, where he formed an acquaintance with the numerous medical men of eminence who at that time adorned this capital. On returning to Germany in 1721, he was appointed physician to Prince Victor Frederick of Anhalt-Bernburg. From Bernburg he went to Magdeburg, and the King of Prussia called him to Berlin in 1724 to teach anatomy in the great anatomic theatre which had been just erected. Soon after he was appointed physician to the king, councillor and professor in the Royal Medico-Chirurgical College, which had been just founded in Berlin. He was also appointed dean of the Superior College of Medicine and physician to the army and to the great hospital of Frederick. In the year 1755, Frederick the Great made him a privy councillor, which is the highest rank that a medical man can attain in Prussia. The same year he was made director of the Royal Academy of Sciences of Berlin. He died in the year 1760, in the 71st year of his age. He was twice married, and his second wife survived him. Many chemical papers of Eller are to be found in the memoirs of the Berlin Academy. They were of sufficient importance at the time when he published them to add considerably to his reputation, though not sufficiently so to induce me to give a catalogue of them here. I am not aware of any chemical discovery for which we are indebted to him, but have been induced to give this brief notice of him, because he is usually associated with Pott and Marggraf, making with them the three celebrated chemists who adorned Berlin during the splendid reign of Frederick the Great. Andrew Sigismund Marggraf was born in Berlin in the year 1709, and acquired the first principles of chemistry from his father, who was an apothecary in that city. He afterwards studied under Neumann, and travelling in quest of information to Frankfurt, Strasbourg, Halle, and Freiburg, he returned to Berlin enriched with all the knowledge of his favourite science which at that time existed. In 1760, on the death of Eller, he was made director of the physical class of the Berlin Academy of Sciences. He died in the year 1782, in the 73rd year of his age. He gradually acquired a brilliant reputation in consequence of the numerous chemical papers which he successfully published, each of which usually contained a new chemical fact of more or less importance, deduced from a set of experiments generally satisfactory and convincing. His papers have a greater resemblance to those of Scheele than of any other chemist to whom we can compare them. He may be considered as in some measure the beginner of chemical analysis, for before his time the chemical analysis of bodies had hardly been attempted. His methods, as might have been expected, were not very perfect, nor did he attempt numerical results. His experiments on phosphorus and on the method of extracting it from urine are valuable. They communicated the first accurate notions relative to this substance and to phosphoric acid. He first determined the properties of the earth of alum, now known by the name of alumina, showed that it differed from every other, and that it existed in clay, and gave to that substance its peculiar properties. He demonstrated the peculiar nature of soda, the base of common salt, which Pott had called in question, and thus verified the conclusions of Duhamel. He gives an easy process for obtaining pure silver from the chloride of that metal. His method is to dissolve the pure chloride of silver in a solution of caustic ammonia, and to put into the liquid a sufficient quantity of pure mercury. The silver is speedily reduced and converted into an amalgam, and when this amalgam is exposed to a red heat, the mercury is driven off and pure silver remains. The usual method of reducing the chloride of silver is to heat it in a crucible with a sufficient quantity of carbonate of potash, a process which was first recommended by Kunkel. But it is scarcely possible to prevent the loss of a portion of the silver when the chloride is reduced in this way. The modern process is undoubtedly the simplest and the best, to reduce it by means of hydrogen. If a few pieces of zinc be put into the bottom of a beer glass, and some dilute sulphuric acid be poured over it, an effervescence takes place, and hydrogen gas is disengaged. Chloride of silver, placed above the zinc in the same glass, is speedily reduced by this hydrogen, and converted into a metallic silver. Marggraf's chemical papers, down to the time of publication, were collected together, translated into French, and published at Paris in the year 1762. In two very small octavo volumes. They consist of 26 different papers, some of the most curious and important of which are those that have been just particularized. Several other papers written by him appeared in the Memoirs of the Berlin Academy. After this collection of his works was published, particularly demonstration of the possibility of drawing fixed alkaline salts from tartar by means of acids without employing the action of a violent fire. It was this paper, probably, that led Scheele, a few years after, to his well-known method of obtaining tartaric acid. a modification of which is still followed by manufacturers. Observations concerning a remarkable volatilization of a portion of a kind of stone known by the names of floss, flus, fluorspar, and likewise by that of hesperos, which volatilization was effectuated by means of acids. Pott had hardly shown the value of fluorspar as a flux. 3 years after the appearance of Margraaf's paper, Scheele discovered the nature of fluorspar, and first drew the attention of chemists to the peculiar properties of fluoric acid. In France, in consequence chiefly of the regulations established in the Academy of Sciences in the year 1699, a race of chemists always existed whose specific object was to cultivate chemistry and extend and improve it. The most eminent of these chemical labourers, after the Stahlian theory was fully admitted in France, till its credit began to be shaken, were Reaumur, Hellot, Duhamel, Rouelle, and Macquer. Besides these, who were the chief chemists in the Academy, there were a few others to whom we are indebted for chemical discoveries that deserve to be recorded. End of section 28. Section 29 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Keren, Turton. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 8 of the Attempts to Establish a Theory in Chemistry, Part 5. René Antoine Fichault, Esquire, Seigneur de Reaumur, certainly one of the most extraordinary men of his age, was born at Rochelle in 1683. He went to the school of Rochelle, and afterwards studied philosophy under the Jesuits at Poitiers. Hence he went to Bourges, to which one of his uncles, canon of the Holy Chapel in that city, had invited him. At this time he was only 17 years of age, yet his parents ventured to entrust a younger brother to his care, and this care he discharged with all the fidelity and sagacity of a much older man. Here he devoted himself to mathematics and physics, and he soon after went to Paris to improve the happy talents which he had received from nature. He was fortunate enough to meet with a friend and relation in the President, Helmont, equally devoted to study with himself, equally eager for information, and possessed of equal honour and integrity, and equally promising talents. He came to Paris in 1703. In 1708 he was admitted into the Academy of Sciences in the situation of élève of M. Varignon, vacant by the promotion of M. Saurin to the rank of associate. The first papers of his which were inserted in the Memoirs of the Academy were geometrical. He gave a general method of finding an infinity of curves, described by the extremity of a straight line, the other extremity of which, passing along the surface of a given curve, is always obliged to pass through the same point. Next year he gave a geometrical work on develops, but this was the last of his mathematical tracts. He was discharged by the Academy with the task of giving a description of the arts, and his taste for natural history began to draw to that study the greatest part of his attention. His first work as a naturalist was his observations on the formation of shells. It was unknown whether shells increase by intussusception like animal bodies, or by the exterior and successive addition of new parts. By a set of delicate observations he showed that shells are formed by the addition of new parts, and that this was the cause of the variety of colour, shape, and size which they usually affect. His observations on snails, with a view to the way in which their shells are formed, led him to the discovery of a singular insect, which not only lives on snails, but in the inside of their bodies, from which it never stirs till driven out by the snail. During the same year he wrote his curious paper on the silk of spiders. The experiments of M. Bone had shown that spiders could spin a silk that might be usefully employed, but it remained to be seen whether these creatures could be fed with profit, and in sufficiently great numbers to produce a sufficient quantity of silk to be of use. Reaumur undertook this disagreeable task, and showed that spiders could not be fed together without attacking and destroying one another. The next research which he undertook was to discover in what way certain sea animals are capable of attaching themselves to fixed bodies, and again disengaging themselves at pleasure. He discovered the various threads and pinnae which some of them possess for this purpose, and the prodigious number of limbs by which the sea star is enabled to attach itself to solid bodies. Other animals employ a kind of cement to glue themselves to those substances to which they are attached, while some fix themselves by forming a vacuum in the interval between themselves and the solid substances to which they are attached. It was at this point that he found great quantities of the buccinum, which yielded the purple dye of the ancients upon the coast of Poitou. He observed also that the stones and little sandy ridges round which the shellfish had collected were covered with a kind of oval grains, some of which were white and others of a yellowish colour, and having collected and squeezed some of these upon the sleeve of his shirt, so as to wet it with the liquid which they contained, he was agreeably surprised in about half an hour to find the wetted spot assume a beautiful purple colour, which was not discharged by washing. He collected a number of these grains, and carrying them to his apartment, bruised and squeezed different parcels of them upon bits of linen, but to his great surprise, after 2 or 3 hours no colour appeared on the wetted part, but at the same time 2 or 3 spots of the plaster at the window on which drops of the liquid had fallen had become purple, though the day was cloudy. On carrying the pieces of linen to the window and leaving them there, they also acquired a purple colour. It was the action of light, then, on the liquor, which caused it to tinge the linen. We found likewise that when the colouring matter was put into a phial, which filled it completely, it remained unchanged. But when the phial was not full, and was badly corked, it acquired colour. From these facts it is evident that the purple colour is owing to the joint action of the light and the oxygen of the atmosphere upon the liquor of the shellfish. About this time likewise he made experiments upon a subject which attracted the attention of mechanicians, to determine whether the strength of a cord was greater or less, or equal to the joint strength of all the fibres which compose it. The result of Römer's experiments was, that the strength of the cord is less than that of all the fibres of which it is composed. Hence it follows that the less that a cord differs from an assemblage of straight fibres, the stronger it is. This, at that time considered as a singular mechanical paradox, was afterwards elucidated by M. Duhamel. It was a popular opinion of all the inhabitants of the seashore, that when the claws of crabs, lobsters, etc., are lost by any means, they are gradually replaced by others, and that the animal in a short time becomes as perfect as at first. This opinion was ridiculed by men of science as inconsistent with all our notions of true philosophy. Römer subjected it to the test of experiment by removing the claws of these animals and keeping them alone for the requisite time in sea water. New claws soon sprang out, and perfectly replaced those that had been removed. Thus the common opinion was verified, and the contemptuous smile of the half-learned man of science was shown to be the result of ignorance, not of knowledge. Römer was not so fortunate in his attempts to explain the nature of the shock given by the torpedo, which we now know to be an electric shock produced by a peculiar apparatus within the animal. Römer endeavoured to prove from dissection that the shock was owing to the prodigious rapidity of the blow given by the animal in consequence of a peculiar structure of its muscles. The turquoise was at that time, as it still is, considerably admired in consequence of the beauty of its colour. Persia was the country from which this precious stone came, and it was at that time considered as the only country in the universe where it occurred. Römer made a set of experiments on the subject, and showed that the fossil bones found in Languedoc, when exposed to a certain heat, assume the same beautiful green colour, and become turquoises equally beautiful with the Persian. It is now known that the true Persian turquoise, the calamite of mineralogists, is quite different from fossil bones coloured with copper. So far, therefore, Römer deceived himself by these experiments. But at that time chemical knowledge was too imperfect to enable him to subject Persian turquoise to an analysis, and determine its constitution. About the same period he undertook an investigation of the nature of imitation pearls, which resemble the true pearls so closely that it is very difficult, from appearances, to distinguish the true from the false. He showed that the substance which gave the false pearls their colour and lustre was taken from a small fish, called by the French able or ablet. He likewise undertook an investigation of the origin of true pearls, and showed that they were indebted for their production to a disease of the animal. It is now known that the introduction of any solid body, as a grain of sand, within the shell of the living pearl shellfish, gives occasion to the formation of pearl. Linnaeus boasted that he knew a method of forming artificial pearls, and doubtless his process was merely introducing some solid particle of matter into the living shell. Pearls consist of alternate layers of carbonate of lime and animal membrane, and the colour and lustre to which they owe their value depends on the thinness of the alternate coats. The next paper of Römer was an account of the rivers in France whose sand yielded gold dust, and the method employed to extract the gold. This paper will well repay the labour of a perusal. It owes its interest in a great measure to the way in which the facts are laid before the reader. His paper on the prodigious bank of fossil shells at Turton, from which the inhabitants draw manure in such quantities for their fields, deserves attention in a geological point of view. But his paper on flints and stones is not so valuable. It consists in speculations which, from the infant state of chemical analysis when he wrote, could not be expected to lead to correct conclusions. I pass over many of the papers of this most indefatigable man, because they are not connected with chemistry, but his History of Insects constitutes a charming book, and contains a prodigious number of facts of the most curious and important nature. This book alone, supposing Reaumur had done nothing else, would have been sufficient to have immortalized the author. In the year 1722, he published his work on the art of converting iron into steel, and of softening cast iron. At that time no steel whatever was made in France. The nation was supplied with that indispensable article from foreign countries, chiefly from Germany. The object of Reaumur's book was to teach his countrymen the art of making steel, and if possible to explain the nature of the process by which iron is changed into steel. Reaumur concluded from his experiments that steel is iron impregnated with sulphurous and saline matters. The word sulphurous, as at that time used, was nearly synonymous with our present term combustible. The process which he found to answer, and which he recommends to be followed, was to mix together 4 parts of soot, 2 parts of charcoal powder, 2 parts of wood ashes, and 1½ parts of common salt. The iron bars to be converted into steel were surrounded with this mixture and kept red hot till converted into steel. Reaumur's notion of the difference between iron and steel was an approximation to the truth. The saline matters which he added do not enter into the composition of the steel, and if they did, so far from improving, they would injure its qualities. But the charcoal and soot, which consist chiefly of carbon, really produce the desired effect. For steel is a combination of iron and carbon. In consequence of these experiments of Reaumur, it came to be an opinion entertained by chemists that steel differed from iron merely by containing a greater proportion of phlogiston, for the charcoal and soot, with which the iron bars were surrounded, was considered as consisting almost entirely of phlogiston, and the only useful purpose which they could serve was supposed to be to furnish phlogiston. This opinion continued prevalent till it was overturned towards the end of the last century, first by the experiments of Bergman, and afterwards by those of Berthelot, Vandermonde, and Monge, published in the Memoirs of the French Academy for 1786, page 132. In this elaborate memoir, the authors take a view of all the different processes followed in bringing iron from the ore to the state of steel. They then give an account of the researches of Reaumur and Bergman, and lastly relate their own experiments, from which they finally draw as a conclusion that steel is a compound of iron and carbon. The Regent Orleans, who at that time administered the affairs of France, thought that this work of Reaumur was deserving a reward, and accordingly offered him a pension of 12,000 livres. Reaumur requested of the regent that this pension should be given in the name of the Academy, that after his death it should continue, and be devoted to defray the necessary expenses towards bringing the arts into a state of perfection. The request was granted, and the letters patent made out on the 22nd of December, 1722. At that time, tin plate, as well as steel, was not made in France, but all the tin plates wanted were brought from Germany, where the processes followed were kept profoundly secret. Reaumur undertook to discover a method of tinning iron sufficiently cheap to admit the article to be manufactured in France, and he succeeded. The difficulty consisted in removing the scales with which the iron plates, as prepared, were always covered. These scales consist of a vitrified oxide of iron, to which the tin will not unite. Reaumur found that when these plates are steeped in water, acidulated by means of bran, and then allowed to rust in stoves, the scales become loose, and are easily detached by rubbing the plates with sand. If, after being thus cleansed, they are plunged into melted tin, covered with a little tallow to prevent oxidizement, they are easily tinned. In consequence of this explanation of the process by Reaumur, tin plate manufactories were speedily established in different parts of France. It was about the same time, or only a little before it, that the tin plate manufactories were first started in England. The English tin plate was much more beautiful than the German, and therefore immediately preferred to it, because in Germany the iron was converted into plates by hammering, whereas in England it was rolled out. This made it much smoother, and consequently more beautiful. Another art, at that time unknown in France, and indeed in every part of Europe except Saxony, was the art of making porcelain, a name given to the beautiful translucent stoneware which is brought from China and Japan. Reaumur undertook to discover the process employed in making it. He procured specimens of porcelain from China and Japan, and also of the imitations of those vessels at that time made in various parts of France and other European countries. The true porcelain remained unaltered, though exposed to the most violent heat which he was capable of producing, but the imitations, in a furnace heated by no means violently, melted into a perfect glass. Hence he concluded that the imitation porcelains were merely glass, not heated sufficiently to be brought into fusion, but true porcelain he conceived to be composed of two different ingredients, one of which is capable of resisting the most violent heat, which can be raised, but the other, when heated sufficiently, melts into a glass. It is this last ingredient that gives porcelain its translucency, while the other makes it refractory in the fire. This opinion of Reaumur was soon after confirmed by Father d'Entrecolles, a French missionary in China, who sent some time after a memoir to the Academy, describing the mode followed by the Chinese in the manufacture of their porcelain. Two substances are employed by them, the one called kaolin, and the other pétunce. It is now known that kaolin is what we call porcelain clay, and that pétunce is a fine white feldspar. Feldspar is fusible in a violent heat, but porcelain clay is refractory in the highest temperatures that we have it in our power to produce in furnaces. Reaumur made another curious observation on glass, which has been, since his time, employed very successfully to explain the appearance of many of our trap rocks. If a glass vessel properly secured in sand be raised to a red heat and then allowed to cool very slowly, it puts off the appearance of glass and assumes that of stoneware or porcelain. Vessels thus altered have received the name of Reaumur's porcelain. They are much more refractory than glass, and therefore may be exposed to a pretty strong red heat without any danger of softening or losing their shape. This shape is occasioned by the glass being kept long in a soft state. The various substances of which it is composed are at liberty to exercise their affinities and to crystallize. This makes the vessel lose its glassy structure altogether. In like manner, it was found by Sir James Hall and Mr. Gregory Watt that when common greenstone was heated sufficiently and then rapidly cooled, it melted and concreted into a glass. But if after having been melted it was allowed to cool exceedingly slowly, the constituents again crystallized and arranged themselves as at first, so that a true greenstone was again formed. In the same way, lavas from a volcano either assume the appearance of slag or of stone, according as they have cooled rapidly or slowly. Many of the lavas from Vesuvius cannot be distinguished from our greenstones. Reaumur's labours upon the thermometer must not be omitted here, because he gave his name to a thermometer which was long used in France and in other parts of Europe. The first person that brought thermometers into a state capable of being compared with each other was Sir Isaac Newton, in a paper published in the Philosophical Transactions for 1701. Fahrenheit of Amsterdam was the first person that put Newton's method in practice by fixing 2 points on his scale, the freezing water point and the boiling water point, and dividing the interval between them into 180 degrees. But no fixed point existed in the thermometers employed in France, everyone graduating them according to his fancy, so that no two thermometers could be compared together. Reaumur graduated his thermometers by plunging them into freezing water or a mixture of snow and water. This point was marked 0 and was called the freezing water point. The liquid used in his thermometers was spirit of wine. He took care that it should be always of the same strength, and the interval between the point of freezing and boiling water was divided into 80 degrees. De Luc afterwards rectified this thermometer by substituting mercury for spirit of wine. This not only enabled the thermometer to be used to measure higher temperatures, but corrected an obvious error which existed in all the thermometers constructed upon Reaumur's principle. For spirit of wine cannot bear a temperature of 80 degrees Reaumur without being dissipated into vapor, absolute alcohol boiling at 162 degrees 2/3. It is obvious from this that the boiling point in Reaumur's thermometer could not be accurate, and that it would vary according to the quantity of empty space left above the alcohol. Finally, he contrived a method of hatching chickens by means of artificial heat, as is practiced in Egypt. We are indebted to him also for a set of important observations on the organs of digestion in birds. He showed that in birds of prey which live wholly upon animal food, digestion is performed by solvents in the stomach, as is the case with digestion in man, while those birds that live upon vegetable food have a very powerful stomach or gizzard, capable of triturating the seeds which they swallow. To facilitate this triturating process, these fowls are in the habit of swallowing small pebbles. End of section 29. Section 30 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Keren, Turton. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 8 of the Attempts to Establish a Theory in Chemistry, Part 5. The moral qualities of M. Reaumur seem not to have been inferior to the extent and variety of his acquirements. He was kind and benevolent and remarkably disinterested. He performed the duties of Intendant of the Order of St. Louis from the year 1735 till his death, without accepting any of the emoluments of the office, all of which were most religiously given to the person to whom they belonged, had she been capable of performing the duties of the place. M. Reaumur died on the 17th of October, 1756, after having lived nearly 75 years. John Hellot was born in Paris in the year 1685 on the 20th of November. His father, Michael Hellot, was of a respectable family, and the early part of his son's education was at home. It seems to have been excellent, as young Hellot acquired the difficult art of writing on all manner of subjects in a precise, clear, and elegant style. His father intended him for the church, but his own taste led him decidedly to the study of chemistry. He had an uncle, a physician, some of whose papers on chemical subjects fell into his hands. This circumstance kindled his natural taste into a flame. He formed an acquaintance with M. Geoffroy, whose reputation as a chemist was at that time high, and this friendship was afterwards cemented by Geoffroy marrying the niece of M. Hellot. His circumstances being easy, he went over to England to form a personal acquaintance with the many eminent philosophers who at that time adorned that country. His fortune was considerably deranged by Law's celebrated scheme during the regency of the Duke of Orleans. This obliged him to look out for some resource. He became editor of the Gazette de France, and continued in this employment from 1718 to 1732. During these 14 years, however, he did not neglect chemistry, though his progress was not so rapid as it would have been, could he have devoted to that science his undivided attention. In 1732 he was put forward by his friends as a candidate for a place in the Academy of Sciences, and in the year 1735 he was chosen adjunct chemist, vacant by the promotion of M. de la Condamine to the place of associate. 3 years after he was declared supernumerary pensioner without passing through the step of associate. His reputation as a chemist was already considerable, and after he became a member of the Academy, he devoted himself to the investigations connected with his favorite science. His first labors were on zinc. In 2 successive papers he endeavored to decompose this metal and to ascertain the nature of its constituents. Though his labor was unsuccessful, yet he pointed out many new properties of this metal and various new compounds into which it enters. Neither was he more successful in his attempt to account for the origin of the red vapors which are exhaled from nitre in certain circumstances. He ascribed them to the presence of ferruginous matters in the nitre, whereas they are owing to the expulsion and partial decomposition of the nitric acid of the nitre, in consequence of the action of some more powerful acid. His paper on sympathetic ink is of more importance. A German chemist had shown him a saline solution of a red color, which became blue when heated. This led him to form a sympathetic ink, which was pale red while the paper was moist, but became blue upon drying it by holding it to the fire. This sympathetic ink was a solution of cobalt and muriatic acid. It does not appear from Hellot's paper that he was exactly aware of the chemical constitution of the liquid which constituted his sympathetic ink, though it is clear he knew that cobalt constitutes an essential part of it. Kunkel's phosphorus, though it had been originally discovered in Germany, could not be prepared by any of the processes which had been given to the public. Boyle had taught his operator, Godfrey Hankwitz, the method of making it. This man had, after Boyle's death, opened a chemist's shop in London, and it was he that supplied all Europe with this curious article. On that account it was usually distinguished by the name of English phosphorus. But in the year 1737 a stranger appeared in Paris, who offered for a stipulated reward to communicate the method of manufacturing the substance to the Academy of Sciences. The offer was accepted by the French government, and a committee of the Academy, at the head of which was Hellot, was appointed to witness the process, and ascertain all its steps. The process was repeated with success, and Hellot drew up a minute detail of the whole, which was inserted in the Memoirs of the Academy for the year 1737. The publication of this paper constitutes an era in the preparation of phosphorus. It was henceforward in the power of every chemist to prepare it for himself. A few years after, the process was much improved by Margraaf, and within little more than 20 years after, the very convenient process still in use was suggested by Scheele. Hellet's experiments on the comparative merits of the salts of Peyrac and of Pecase were of importance, because they decided a dispute. They may also perhaps be considered as curiosities in an historical point of view, because we see from them the methods which Hellet had recourse to at the early period in order to determine the purity of common salt. They are not entitled, however, to a more particular notice here. In the year 1740, M. Hellet was charged with the general inspection of dyeing, a situation which M. Dufoy had held till the time of his death in 1739. It was this appointment, doubtless, which turned his attention to the theory of dyeing, which he tried to explain in two memoirs, read to the Academy in 1740 and 1741. The subject was afterwards prosecuted by him in subsequent memoirs which were published by the Academy. In 1745 he was named to go to Lyons, in order to examine with care the processes followed for refining gold and silver. Before his return he took care to give to these processes the requisite precision and exactness. Immediately after his return to Paris he was appointed to examine the different mines and assay the different ores in France. This appointment led him to turn his thoughts to the subject. The result of this was the publication of an excellent work on assaying and metallurgy, entitled De la Fonte des Mines, des Fonderies, etc., traduit de l'Allemand de Christophe André Schluter. The first volume of this book appeared in 1750, and the second in 1753. Though this book is called by Hellet a translation, it contains in fact a great deal of original matter. The arrangement is quite altered, many processes not noticed by Schluter are given, and many essential articles are introduced which had been totally omitted in the original work. He begins with an introduction in which he gives a short sketch of all the mines existing in every part of France, together with some notice of the present state of each. The first volume treats entirely of dosimetry, or the art of assaying the different metallic ores. Though this art has been much improved since Hellet's time, yet the processes given in the volume are not without their value. The second volume treats of the various metallurgic processes followed in order to extract metals from their ores. This volume is furnished with no fewer than 55 plates, in which all the various furnaces, etc., used in these processes are exhibited to the eye. While occupied in preparing this work for the press, he was chosen to endeavour to bring the porcelain manufactory at Sèvres to a greater state of perfection than it had yet reached. In this he was successful. He even discovered various new colours proper for painting upon porcelain, which contributed to give to this manufactory the celebrity which it acquired. In the year 1763, a phenomenon at that time quite new to France took place in the coal mine of Briançon. A quantity of carburetted hydrogen gas had collected in the bottom of the mine, and being kindled by the lights employed by the miners, it exploded with great violence, and killed or wounded every person in the mine. This destructive gas, distinguished in this country by the name of fire damp, had long been known in Great Britain and in the Low Countries, though it had not before been known in France. The Duc de Choiseul, informed of this event, had recourse to the Academy for assistance, who appointed Messrs. de Montigny, Duhamel, and Hellet, a committee to endeavour to discover the remedies proper to prevent any such accident from happening for the future. The report of these gentlemen was published in the Memoirs of the Academy. They give an account both of the fire damp and choke damp, or carbonic acid gas, which sometimes also makes its appearance in coal mines. They very justly observe that the proper way to obviate the inconveniency of these gases is to ventilate the mine properly, and they give various methods by which this ventilation may be promoted, by means of fires lighted at the bottom of the shaft, etc. In 1763, M. Hellet was appointed, conjointly with M. Tillet, to examine the process followed for assaying gold and silver. They showed that the cupels always retained a small portion of the silver assayed, and that this loss, ascribed to the presence of a foreign metal, made the purity of the silver be always reckoned under the truth, which occasioned a loss to the proprietor. His health continued tolerably good till he reached his 80th year. He was then struck with palsy, but partially recovered from the first attack. But a second attack on the 13th of February 1765 refused to yield to every medical treatment, and he died on the 15th of that month, at an age a little beyond 80. Henry Louis Duhamel de Monceau was born at Paris in the year 1700. He was descended from Lot Duhamel, a Dutch gentleman who came to France in the suite of the infamous Duke of Burgundy about the year 1400. Young Duhamel was educated in the College of Harcourt, but the course of study did not suit his taste. He left it with only one fact engraven on his memory, that men, by observing nature, had created a science called physics, and he resolved to profit by his freedom from restraint and turn the whole of his attention to that subject. He lodged near the Jardin du Roi, where alone at that time physics were attended to in Paris. Dufoy, Geoffroy, Lemery, Jussieu, and Vaillant were the friends with whom he associated on coming to Paris. His industry was stimulated solely by a love of study and by the pleasure which he derived from the increase of knowledge. Love of fame does not appear to have entered into his account. In the year 1718, saffron, which is much cultivated in that part of France formerly distinguished by the name of Gatinois, where Duhamel's property lay, was attacked by a malady which appeared contagious. Healthy bulbs, when placed in the neighbourhood of those that were diseased, soon became affected with the same malady. Government consulted the Academy on the subject, and this learned body thought they could not do better than request M. Duhamel to investigate the cause of the disease, though he was only 18 years of age and not even a member of the Academy. He ascertained that the malady was owing to a parasitical plant which attached itself to the bulb of the saffron and drew nourishment from it. This plant extended under the earth from one bulb to another, and thus infected the whole saffron plantations. M. Duhamel formed the resolution, at the commencement of his scientific career, to devote himself to public utility, and to prosecute those subjects which were likely to contribute most effectually to the comfort of the lower ranks of men. Much of his time was spent in endeavouring to promote the culture of vegetables, and in rendering that culture more useful to society. This naturally led to a careful study of the physiology of trees. The fruit of this study he gave to the world in the year 1758, when his Physique des Arbres was published. This constitutes one of the most important works on the subject which has ever appeared. It contains a great number of new and original facts, and contributed very much indeed to advance this difficult but most important branch of science. Nor is it less remarkable for modesty than for value. The facts gathered from other sources, even those which make against his own opinions, are most carefully and accurately stated. The experiments that preceded his are repeated and verified with much care, and the reader is left to discover the new facts and new views of the author without any attempt on his part to claim them as his own. M. Duhamel had been attached to the Department of the Marine by M. de Maurepas, who had given him the title of Inspector General. This led him to turn his attention to naval science in general. The construction of vessels, the weaving of sailcloths, the construction of ropes and cables, the method of preserving the wood, occupied his attention successively, and gave birth to several treatises, which, like all his works, contain immense collections of facts and experiments. He endeavours always to discover which is the best practice, to reduce it to fixed rules, and to support it by philosophical principles, but abstains from all theory when it can be supported only by hypothesis. From the year 1740, when he became an academician, till his death in 1781, he made a regular set of meteorological observations at Pithiviers, with details relative to the direction of the needle, to agriculture, to the medical constitution of the year, and to the time of nest building and of the passage of birds. Above 60 memoirs of his were published in the Transactions of the French Academy of Sciences. They are so multifarious in their nature, and embrace such a variety of subjects, that I shall not attempt even to give their titles, but satisfy myself with stating such only as bear more immediately upon the science of chemistry. It will be proper in conducting this review to notice the result of his labours connected with the ossification of bones, because, though not strictly chemical, they throw light upon some branches of the animal economy, more closely connected with chemistry than with any other of the sciences. He examined in the first place whether the ossification of bones and their formation and reparation did not follow the same law that he had assigned to the increments of trees, and he established by a set of experiments that bones increase by the ossification of layers, the periosteum, as trees do by the hardening of their cortical layers. Bones in a soft state increase in every direction like the young branches of plants, but after their induration they increase only like trees by successive additions of successive layers. This organization was incompatible with the opinion of those who thought that bones increased by the addition of an earthy matter deposited in the meshes of the organized network which forms the texture of bones. M. Duhamel combated this opinion by an ingenious experiment. He had been informed by Sir Hans Sloane that the bones of the young animals fed upon madder were tinged red. He conceived the plan of feeding them alternately with food mingled with madder and with ordinary food. The bones of animals thus treated were found to present alternate concentric layers of red and white, corresponding to the different periods in which the animal had been fed with food containing or not containing madder. When these bones are sawn longitudinally, we see the thickness of the colored layers greater or less according to the number of plates of the periosteum which have ossified. As for the portions still soft, or susceptible of extending themselves in every direction, such as the plates in the neighborhood of the marrow, the reservoir of which increases during a part of the time that the animal continues to grow, the red color marks equally the progress of their ossification by colored points more or less extended. This opinion was attacked by Haller and defended by M. Faugeroux, a nephew of M. Duhamel, but it is not our business here to inquire how far correct. One of the most important of M. Duhamel's papers, which will secure his name a proud station in the annals of chemistry, is that which was inserted in the Memoirs of the Academy for 1737, in which he shows that the base of common salt is a true fixed alkali, different in some respects from the alkali extracted from land plants, and known by the name of potash, but similar to that obtained by the incineration of marine plants. We are surprised that a fact so simple and elementary was disputed by the French chemists, and rather indicated than proved by Stahl and his followers. The conclusions of Duhamel were disputed by Pott, but finally confirmed by Marggraf. M. Duhamel carried his researches further. He wished to know if the difference between potash and soda depends on the plants that produce them, or on the nature of the soil in which they grow. He sowed kali at Denain-Villiers and continued his experiments during a great number of years. M. Cadet, at his request, examined the salts contained in the ashes of kali of Denain-Villiers. He found that during the first year, soda predominated in these ashes. During the successive years, the potash increased rapidly, and at last the soda almost entirely disappeared. It was obvious from this that the alkalis in plants are drawn at least chiefly from the soil in which they vegetate. The memoirs of M. Duhamel on ether, at that time almost unknown, on soluble tartars, and on lime, contain many facts both curious and accurately stated, though our present knowledge of these bodies is so much greater than his. The new facts ascertained respecting them are so numerous and important that the contributions of this early experimenter, which probably had a considerable share in the success of subsequent investigations, are now almost forgotten. Nor would many readers bear patiently with an attempt to enumerate them. There is a curious paper of his in the Memoirs of the Academy for 1757. In this he gives the details of a spontaneous combustion of large pieces of cloth soaked in oil and strongly pressed. Cloth thus prepared had often produced similar accidents. Those who were fortunate enough to prevent them took care to conceal the facts, partly from ignorance of the real cause of the combustion, and partly from a fear that if they were to state what they saw, their testimony would not gain credit. If the combustion had not been prevented, then the public voice would have charged those who had the care of the cloths with culpable negligence, or even with criminal conduct. The observation of M. Duhamel, therefore, was useful in order to prevent such unjust suspicions from hindering those concerned from taking the requisite precautions. Yet, 20 years after the publication of his paper, 2 accidental spontaneous combustions in Russia were ascribed to treason. The Empress Catherine II alone suspected that the combustion was spontaneous, and experiments made by her orders fully confirmed the evidence previously advanced by the French philosopher. End of section 30. Section 31 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Keren, Turton. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 8, of the Attempts to Establish a Theory in Chemistry, Part 6. One man alone would have been insufficient for all the labours undertaken by M. Duhamel, but he had a brother who lived upon his estate at Denainvilliers, the name of which he bore, and divided his time between the performance of benevolent actions and studying the operations of nature. M. Denainvilliers prosecuted in his retreat the observations and experiments entrusted by his brother to his charge. Thus, in fact, the memoirs of Duhamel exhibit the assiduous labours of two individuals, one of whom contentedly remained unknown to the world, satisfied with the good which he did, and the favours which he conferred upon his country and the human race. The works of M. Duhamel are very voluminous, and are all written with the utmost plainness. Everything is elementary, no previous knowledge is taken for granted. His writings are not addressed to philosophers, but to all who are in quest of practical knowledge. He has been accused of diffuseness of style and of want of correctness, but his style is simple and clear, and as his object was to inform, not philosophers, but the common people, greater conciseness would have been highly injudicious. Neither he nor his brother ever married, but thought it better to devote their undivided attention to study. Both were assiduous in no ordinary degree, but the ardour of Duhamel himself continued nearly undiminished till within a year of his death, when, though he still attended the meetings of the Academy, he no longer took the same interest in its proceedings. On the 22nd of July, 1781, just after leaving the Academy, he was struck with apoplexy, and died after lingering 22 days in a state of coma. He was, without doubt, one of the most eminent men of the age in which he lived, but his merits as a chemist will chiefly be remembered in consequence of his being the first person who demonstrated, by satisfactory evidence, the peculiar nature of soda, which had been previously confounded with potash. His merits as a vegetable physiologist and agriculturist were of a very high order. Peter Joseph Macquer was born at Paris in 1718. His father, Joseph Macquer, was descended from a noble Scottish family, which had sacrificed its property and its country out of attachment to the family of the Stuarts. Young Macquer made choice of medicine as a profession, and devoted himself chiefly to chemistry, for which he showed early a decided taste. He was admitted a member of the Academy of Sciences in the year 1745, when he was 27 years of age. Original researches in chemistry, the composition of chemical elementary works, and the study of the arts connected with chemistry occupied the whole remainder of his life. His first paper treated of the effect produced by heating a mixture of saltpeter and white arsenic. It was previously known that when such a mixture is distilled, nitric acid comes over tinged with a blue colour, but nobody had thought of examining the residue of this distillation. Macquer found it soluble in water and capable of crystallizing into a neutral salt composed of potash, the base of saltpeter, and an acid into which the arsenic was changed by the nitric acid communicating oxygen to it. Macquer found that a similar salt might be obtained with soda or ammonia for its base. Thus he was the first person who pointed out the existence of arsenic acid, and ascertained the properties of some of the salts which it forms. But he made no attempt to obtain arsenic acid in a separate state, or to determine its properties. That very important step was reserved for Scheele, for Macquer seems to have had no suspicion of the true nature of the salt which he had formed. His next set of experiments was on Prussian blue. He made the first step towards the discovery of the nature of the principle to which the pigment owes its colour. Prussian blue had been accidentally discovered by Diesbach, an operative chemist of Berlin, in 1710, but the mode of producing it was kept secret till it was published in 1724 by Dr. Woodward in the Philosophical Transactions. It consisted in mixing potash and blood together and heating the mixture in a covered crucible, having a small hole in the lid, till it ceased to give out smoke. The solution of this mixture in water, when mixed with a solution of sulphate of iron, threw down a green powder, which became blue when treated with muriatic acid. This blue matter was Prussian blue. Macquer ascertained that when Prussian blue is exposed to a red heat, its blue colour disappears, and it is converted into common peroxide of iron. Hence he concluded that Prussian blue is a compound of oxide of iron, and of something which is destroyed or driven off by a red heat. He showed that this something possessed the characters of an acid, for when Prussian blue is boiled with caustic potash, it loses its blue colour, and if the potash be boiled with successive portions of Prussian blue, as long as it is capable of discolouring them, it loses the characters of an acid and assumes those of a neutral salt, and at the same time acquires the property of precipitating iron from the solutions of the sulphate at once of a blue colour. Macquer ascribed the green colour thrown down by mixing the blood lye and sulphate of iron to the potash in the blood lye, not being saturated with the colouring matter of Prussian blue. Hence a portion of the iron is thrown down in the state of Prussian blue, and another portion in that of yellow oxide of iron. These two being mixed form a green. The muriatic acid dissolves the yellow oxide and leaves the Prussian blue untouched. Macquer, however, did not succeed in determining the nature of the colouring matter, a task reserved for Scheele, whose lot it was to take up the half-finished investigations of Macquer and throw upon them a new and brilliant light. Macquer thought that this colouring matter was phlogiston. On that account, the potash saturated with it, which was employed by chemists to detect the presence of iron by forming with it Prussian blue, was called phlogisticated alkali. Macquer, conjointly with Baume, subjected the grains of crude platinum, to which the attention of chemists had been newly drawn, to experiment. Their principal object was to examine its fusibility and ductility. They succeeded in fusing it imperfectly, by means of a burning mirror, and found that the grains thus treated were not destitute of ductility. But upon the whole, the experiments of these chemists threw but little light upon the subject. Many years elapsed before chemists were able to work this refractory metal, and to make it into vessels fitted for the uses of the laboratory. For this important improvement, which constitutes an era in chemistry, the chemical world was chiefly indebted to Dr. Wollaston. In the year 1750, M. Macquer was charged with a commission by the court. There existed at that time in Brittany a man, the Count de la Garenne, who, yielding to a passion for benevolence, had for 40 years devoted himself to the service of suffering humanity. He had built an hospital by the side of a chemical laboratory. He took care of the patients in the hospital himself, and treated them with medicines prepared in his laboratory. Some of these were new, and in his opinion excellent medicines, and he offered to sell them to government for the service of his hospital. Macquer was charged by government with the examination of these medicines. The project of the Count de la Garenne was to extract the salutary parts of minerals by a long maceration with neutral salts. Among other things, he had prepared a mercurial tincture by a process which lasted several months. But this tincture was merely a solution of corrosive sublimate in spirit of wine. Such is the history of most of those boasted secrets. Sometimes they are chimerical, and sometimes known to all the world except to those who purchase them. M. Macquer had the fortune to live at a time when chemistry began to be freed from the reveries of alchemists. But methodical arrangement was a merit still unknown to the elementary chemical books, especially in France, where a residue of Cartesianism added to the natural obscurity of the science, by surcharging it with pretended mechanical explanations. Macquer was the first French chemist who gave to an elementary treatise the same clearness, simplicity, and method which is to be found in the other branches of science. This was no small merit, and undoubtedly contributed considerably to the rapid improvement of the science which so speedily followed. His Elements of Chemistry were translated into different languages, especially into English, and long constituted the textbook employed in the different European universities. Dr. Black recommended it for many years in the University of Edinburgh. Indeed, it was only superseded in consequence of the new views introduced into chemistry by Lavoisier, which, requiring a new language to render them intelligible, naturally superseded all the elementary chemical books which had preceded the introduction of that language. Macquer, during a number of years, delivered regular courses of chemical lectures, conjointly with Baume. In these courses he preferred the arrangement which appeared to him to require the least preliminary knowledge of chemistry. He described the experiments, stated the facts with clearness and precision, and explained them in the way which appeared to him most plausible, according to the opinions generally received, but without placing much confidence in the accuracy of these explanations. He thought it necessary to theorize a little, to enable his pupils the better to connect the facts and to remember them, and to put an end to that painful state of uncertainty which always results from a collection of facts without any theoretical links to bind them together. When the discoveries of Lavoisier began to shake the foundation of the Stahlian theory, Macquer was old, and it appears from a letter of his published by de la Metherie in the Journal de Physique that he was alarmed by the prophetic announcements of Lavoisier in the Academy that the reign of phlogiston was drawing towards an end. M. Condorcet assures us that his attachment to theory, by which he means phlogiston, was by no means strong, but his own letter to de la Metherie rather shows that this statement was not quite correct. How, indeed, could he fail to experience an attachment to opinions which it had been the business of his whole life to inculcate? Macquer also published a Dictionary of Chemistry, which which was very successful, and which was translated into most of the European languages. This mode of treating chemistry was well suited to a science still in its infancy, and which did not yet constitute a complete whole. It enabled him to discuss the different topics in succession, and independent of each other, and thus to introduce much important matter which could not easily have been introduced into a systematic work on chemistry. The second edition of this dictionary was published just at the time when the gases began to attract the attention of scientific men. When facts began to multiply with prodigious rapidity, and to shake the confidence of chemists in all received theories, he acquitted himself of the difficult task of collecting and stating these new facts with considerable success, and doubtless communicated much new information to his countrymen, for the discoveries connected with the gases originated and were chiefly made in England, from which, on account of the Revolutionary American War, there was some difficulty of obtaining early information. M. Hellot, who was Commissioner of the Council for Dyeing, and chemist to the porcelain manufacture, requested to have M. Macquer for an associate. This request did much honour to Hellot, as he was conscious that the reputation of Macquer as a chemist was superior to his own. Macquer endeavoured in the first place to lay down the true principles of the art of dyeing, as the best method of dissipating the obscurity which still hung over it. A great part of his treatise on the art of dyeing silk, published in the collection of the Academy of Sciences, has these principles for its object. He gave processes also for dyeing silk with Prussian blue, and for giving to silk, by means of cochineal, as brilliant a scarlet colour as can be given to woolen cloth by the same dye stuff. He published nothing on the porcelain manufacture, though he attended particularly to the processes, and introduced several ameliorations. The beautiful porcelain earth at present used at Sevres was discovered in consequence of a premium which he offered to any person who could point out a clay in every respect proper for making porcelain. Macquer passed a great part of his life with a brother whom he affectionately loved. After his death he devoted himself entirely to his wife and 2 children, whose education he superintended. He was rather averse to society, but conducted himself well in it with much sweetness and affability. He was fond of tranquillity and independence, though his health had been injured a good many years before his death. The calmness and serenity of his temper prevented strangers from being aware that he was afflicted with any malady. He himself was sensible that his strength was gradually sinking. He predicted his approaching end to his wife, whom he thanked for the happiness which she had spread over his life. He left orders that his body should be opened after his decease, that the cause of his death might be discovered. He died on the 15th of February 1784. An ossification of the aorta, and several calculous concretions found in the cavities of the heart, had been the cause of the disease under which he had suffered for several years before his death. These 4 chemists, of whose lives a sketch has just been given, were the most eminent that France ever produced, belonging to the Stahlian school of chemistry. Baron, Malouin, Rouelle Senior, Tillet, Cadet, Baume, Sage, and several others whose names I purposely omit, likewise cultivated chemistry during that period with assiduity and success, and were each of them the authors of papers which deserve attention, but which it would be impossible to particularize without swelling this work into a size greatly beyond its proper limits. Hilaire Marin Rouelle, who was born at Cayenne in 1718, was, however, too eminent a chemist to be passed over in silence. His elder brother, William Francis, was a member of the Academy of Sciences, and demonstrated to Macquer, who gave lectures in the Jardin du Roi. At the death of Macquer, in 1770, Hilaire Marin Rouelle succeeded him. He devoted the whole of his time and money to this situation, and quite altered the nature of the experimental course of chemistry given in the Jardin du Roi. He was in some measure the author of the chemistry of animal bodies, at least in France. When he published his experiments on the salts of urine and of blood, he had scarcely any model, and though he committed some considerable mistakes, he ascertained several essential and important facts, which have been since fully confirmed by more modern experimenters. He died on the 7th of April, 1779, aged 61 years. His temper was peculiar, and he was too honest and too open for the situation in which he was placed, and for a state of society in which everything was carried by intrigue and finesse. This is the reason why, in France, his reputation was lower than it ought to have been. It accounts, too, for his never becoming a member of the Academy of Sciences, nor of any of the other numerous academies which at that time swarmed in France. Nothing is more common than to find these unjust decisions raise or depress men of science far above or far below their true standard. Romée de Lisle, the first person who commenced the study of crystals, and placed that study in a proper point of view, was a man of the same stamp with the younger Rouelle, and never on that account became a member of any academy, or acquired that reputation during his lifetime to which his laborious career justly entitled him. It would be an easy, though an invidious task, to point out various individuals, especially in France, whose reputation, in consequence of accidental and adventitious circumstances, rose just as much above their deserts as those of Rouelle and Rome de Lisle were sunk below. End of section 31.
Section 32 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jairus Amar. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 9. Of the Foundation and Progress of Scientific Chemistry in Great Britain. Part 1. The spirit which Newton had infused for the mathematical science was so great that during many years they drew within their vortex almost all the scientific men in Great Britain. Dr. Stephen Hales is almost the only remarkable exception during the early part of the 18th century. His vegetable statics constituted a most ingenious and valuable contribution to vegetable physiology. His hemostatics was a no less valuable contribution to iatro-mathematics, at that time the fashionable medical theory in Great Britain, while his analysis of air and experiments on the animal calculus constituted, in all probability, the foundation stone of the whole discoveries respecting the gases to which the great subsequent progress of chemistry is chiefly owing. Dr. William Cullen, to whom medicine lies under deep obligations, and who afterwards raised the medical celebrity of the College of Edinburgh to so high a pitch, had the merit of first perceiving the importance of scientific chemistry and the reputation which that man was likely to earn who should devote himself to the cultivation of it. Hitherto, chemistry in Great Britain, and on the continent also, was considered as a mere appendage to medicine, and useful only so far as it contributed to the formation of new and useful remedies. This was the reason why it came to constitute an essential part of the education of every medical man, and why a physician was considered as unfit for practice unless he was also a chemist. But Dr. Cullen viewed the science as far more important, as capable of throwing light on the constitution of bodies, and of improving and amending of those arts and manufactures that are most useful to man. He resolved to devote himself to its cultivation and improvement, and he would undoubtedly have derived celebrity from this science, had not his fate led rather to the cultivation of medicine. But Dr. Cullen, as the true commencer of the study of scientific chemistry in Great Britain, claims a conspicuous place in this historical sketch. William Cullen was born in Lanarkshire, in Scotland, in the year 1712, on the 11th of December. His father, though chief magistrate of Hamilton, was not in circumstances to lay out much money on his son. William, therefore, after serving an apprenticeship to a surgeon in Glasgow, went several voyages to the West Indies as surgeon in the trading vessel from London. But tiring of this, he settled, when very young, in the parish of Shotts, and after residing for a short time among the farmers and country people, he went to Hamilton, with a view of practicing as a physician. While he resided near Shotts, it happened that Archibald, Duke of Argyll, who at that time bore the chief political sway in Scotland, paid a visit to a gentleman of rank in that neighbourhood. The Duke was fond of science, and was at that time engaged in some chemical researches which required to be elucidated by experiment. Eager in these pursuits, while on his visit he found himself at a loss for some piece of chemical apparatus which his landlord could not furnish. But he mentioned young Cullen to the Duke as a person fond of chemistry, and likely therefore to possess the required apparatus. He was accordingly invited to dine, and introduced to his Grace. The Duke was so pleased with his knowledge, politeness, and address, that an acquaintance commenced, which laid the foundation of all Cullen's future advancement. His residence in Hamilton naturally made his name known to the Duke of Hamilton, whose palace is situated in the immediate vicinity of that town. His Grace being taken with a sudden illness, sent for Cullen, and was highly delighted with the sprightly character and ingenious conversation of the young physician. He found no difficulty, especially as young Cullen was already known to the Duke of Argyll, in getting him appointed to a place in the University of Glasgow, where his singular talents as a teacher soon became very conspicuous. It was while Dr. Cullen was a practitioner in Shotts that he formed a connection with William, afterwards Dr. Hunter, the famous lecturer on anatomy in London, who was a native of the same part of the country as Cullen. These two young men, stimulated by genius, though thwarted by the narrowness of their circumstances, entered into a copartnery business, as surgeons and apothecaries, in the country. The chief object of their contract was to furnish the parties with the means of carrying on their medical studies, which they were not able to do separately. It was stipulated that one of them, alternately, should be allowed to study in whatever college he preferred during the winter, while the other carried on the common business in his absence. In consequence of this agreement, Cullen was first allowed to study in the University of Edinburgh for a winter. When it came to Hunter's turn next winter, he rather chose to go to London. There his singular neatness in dissecting, and uncommon dexterity in making anatomical preparations, his assiduity in study, his mild manners, and easy temper, drew upon him the attention of Dr. Douglas, who at that time read lectures on anatomy and midwifery in the capital. He engaged him as his assistant, and he afterwards succeeded him in the same department with much honor to himself, and advantage to the public. Thus was dissolved a copartnership of perhaps as singular a kind as any that occurs in the annals of science. Cullen was not disposed to let any engagement with him prove a bar to his partner's advancement in the world. The articles were abandoned, and Cullen and Hunter kept up ever after a friendly correspondence, though there is reason to believe that they never afterwards met. It was while a country practitioner that young Cullen married a Miss Johnston, daughter of a neighborhood clergyman. The connection was fortunate and lasting. She brought her husband a numerous family, and continued his faithful companion through all the alterations of his fortune. She died in the summer of 1786. In the year 1746, Cullen, who had now taken the degree of Doctor of Medicine, was appointed lecturer on chemistry in the University of Glasgow, and in the month of October began a course on that science. His singular talent for arrangement, his distinctness of enunciation, his vivacity of manner, and his knowledge of the science which he taught, rendered his lectures interesting to a degree which had been till then unknown in that university. He was adored by the students. The former professors were eclipsed by the brilliancy of his reputation, and he had to encounter all those little rubs and insults that disappointed envy naturally threw in his way. but he proceeded in his career regardless of these petty mortifications, and supported by the public, he was more than consoled for the contumely heaped upon him by the ill nature and pitiful malignity of his colleagues. His practice as a physician increased every day, and a vacancy occurring in the chair of 1751, he was appointed by the Crown Professor of Medicine, which put him on a footing of equality with his colleagues in the university. This new appointment called forth powers which he was not before known to possess, and thus served still further to increase his reputation. At that time, the patrons of the University of Edinburgh were eagerly bent on raising the reputation of their medical school, and were in consequence on the lookout for men of abilities and reputation to fill their respective chairs. Their attention was soon drawn towards Cullen, and on the death of Dr. Plummer, in 1756, he was unanimously invited to fill the vacant chemical chair. He accepted the invitation, and began his academic career in the College of Edinburgh in October of that year, and here he continued during the remainder of his life. The appearance of Dr. Cullen in the College of Edinburgh constitutes a memorable era in the progress of that celebrated school. Hitherto, chemistry being reckoned of little importance, had been attended by very few students. When Cullen began to lecture, it became a favorite study, almost all the students flocking to hear him, and the chemical class becoming immediately more numerous than any other in the college, anatomy alone excepted. The students in general spoke of the new professor with that rapturous ardor so natural to young men when highly pleased. These eulogiums were doubtless extravagant, and proved disgusting to his colleagues. A party was formed to oppose this new favorite of the public. His opinions were misrepresented. It was affirmed that he taught doctrines which excited the alarm of some of the most moderate and conscientious of his colleagues. Thus a violent ferment was excited, and some time elapsed before the malignant arts by which this flame had been blown up were discovered. During this time of public ferment, Cullen went steadily forward. He never gave an ear to the gossip brought him respecting the conduct of his colleagues, nor did he take any notice of the doctrines which they taught. Some of their unguarded strictures on himself might occasionally have come to his ears, but if it was so, he took no notice of them whatever. They seemed to have made no impression on him. This futile attempt to lower his character being thus baffled, his fame as a professor and his reputation as a physician increased daily, nor could it be otherwise. His professional knowledge was always great, and his manner of lecturing singularly clear and intelligible, lively and entertaining. To his patients his conduct was so pleasing, his address so affable and engaging, and his manner so open, so kind, and so little regulated by pecuniary considerations, that those who once applied to him for medical assistance could never afterwards dispense with it. He became the friend and companion of every family he visited, and his future acquaintance could not be dispensed with. His private conduct to his students was admirable, and deservedly endeared him to every one of them. He was so uniformly attentive to them, and took so much interest in the concerns of those who applied to him for advice, was so cordial and so warm, that it was impossible for anyone who had a heart susceptible of generous emotions not to be delighted with a conduct so uncommon and so kind. It was this which served more than anything else to extend his reputation over every civilized quarter of the globe. Among ingenious youth, gratitude easily degenerates into rapture, hence the popularity which he enjoyed, and which to those who do not well weigh the causes which operated on the students must appear excessive. The general conduct of Cullen to his students was this. With all such as he observed to be attentive and diligent, he formed an early acquaintance, by inviting them by twos, by threes, and by fours at a time, to sup with him, conversing with them at such times with the most engaging ease, entering freely with them into the subject of their studies, their amusements, their difficulties, their hopes, and future prospects. In this way he usually invited the whole of his numerous class, till he made himself acquainted with their private character, their abilities, and their objects of pursuit. Those of whom he formed the highest opinion were of course invited most frequently, till an intimacy was gradually formed, which proved highly beneficial to them. To their doubts and difficulties he listened with the most obliging condescension, and he solved them to the utmost of his power. His library was at all times open for their accommodation. In short, he treated them as if they had been all his relatives and friends. Few men of distinction left the University of Edinburgh in his time with whom he did not keep up a correspondence till they were fairly established in business. This enabled him gradually to form an accurate knowledge of the state of medicine in every country, and the knowledge thus acquired put it in his power to direct students to the choice of places where they might have an opportunity of engaging in business with a reasonable prospect of success. Nor was it in this way alone that he befriended the students of the University of Edinburgh. Remembering the difficulties with which he had himself to struggle in his younger days, he was at all times singularly attentive to the pecuniary wants of his students. From the general intimacy which he contracted with them, he found no difficulty in discovering those whose circumstances were contracted, or who labored under any pecuniary embarrassment, without being under the necessity of hurting their feelings by a direct inquiry. To such persons, when their habits of study admitted it, he was peculiarly attentive. They were more frequently invited to his house than others. They were treated with unusual kindness and familiarity. They were conducted to his library and encouraged by the most delicate address to borrow from it freely whatever books he thought they had occasion for. And as persons under such circumstances are often extremely shy, books were sometimes pressed upon them as a sort of task, the doctor insisting upon knowing their opinion of such and such passages which they had not read, and desiring them to carry the book home for that purpose. In short, he behaved to them as if he had courted their company. He thus raised them in the opinion of their acquaintances, which, to persons in their circumstances, was of no little consequence. They were inspired at the same time with a secret sense of dignity, which elevated their minds, and excited an uncommon ardor, instead of that desponding inactivity so natural to depressed circumstances. Nor was he less delicate in the manner of supplying their wants. He often found out some polite excuse for refusing to take money for a first course, and never was at a loss for one to an after course. Sometimes, as his lectures were never written, he would request the favor of a sight of their notes, if he knew that they were taken with care, in order to refresh his memory. Sometimes he would express a wish to have their opinion of a particular part of his course, and presented them with a ticket for the purpose. By such delicate pieces of address, in which he greatly excelled, he took care to anticipate their wants. Thus he not only gave them the benefit of his own lectures, but by refusing to take money, enabled them to attend such others as were necessary for completing their course of medical study. he introduced another general rule into the university dictated by the same spirit of disinterested benevolence. Before he came to Edinburgh, it was the custom of the medical professors to accept of fees for their medical attendance when wanted, even from medical students themselves, though they were perhaps attending the professor's lectures at the time. But Dr. Cullen would never take a fee from any student of the university, though he attended them, when called on as a physician, with the same assiduity and care as if they had been persons of the first rank who paid him most liberally. This gradually led others to follow his example, and it has now become a general rule for medical professors to decline taking any fees when their assistance is necessary to a student. For this useful reform, as well as for many others, the students of the University of Edinburgh are entirely indebted to Dr. Cullen. The first lectures which Dr. Cullen delivered in Edinburgh were on chemistry, and for many years he also gave lectures on the cases that occurred in the infirmary. In the month of February, 1763, Dr. Alston died, after having begun his usual course of lectures on the materia medica. The magistrates of Edinburgh, who are the patrons of the university, appointed Dr. Cullen to that chair, requesting that he would finish the course of lectures that had been begun by his predecessor. This he agreed to do, and, though he had only a few days to prepare himself, he never once thought of reading the lectures of his predecessor, but resolved to deliver a new course, which should be entirely his own. Some idea may be formed of the popularity of Cullen by the increase of students to a class nearly half finished. Dr. Alston had been lecturing to 10. As soon as Dr. Cullen began, 100 new students enrolled themselves. Some years after, on the death of Dr. Witt, professor of the theory of medicine, Dr. Cullen was appointed to give lectures in his stead. It was then that he thought it requisite to resign the chemical chair in favor of Dr. Black, his former pupil, whose talents in that department of science were well known. Soon after, on the death of Dr. Rutherford, professor of the practice of medicine, Dr. John Gregory having become a candidate for this place, along with Dr. Cullen, a sort of compromise took place between them, by which they agreed to give lectures alternately on the theory and practice of medicine during their joint lives, the longest survivor being allowed to hold either of the classes he should incline. Unluckily, this arrangement was soon destroyed by the sudden and unexpected death of Dr. Gregory, in the flower of his age. Dr. Cullen thenceforth continued to give lectures on the practice of medicine till within a few months of his death, which happened on the 5th of February, 1790, when he was in the 77th year of his age. It is not our business to follow Dr. Cullen's medical career, nor to point out the great benefits which he conferred on nosology and the practice of medicine. He taught 4 different classes in the University of Edinburgh, which we are not aware to have happened to any other individual, except to Professor Dugald Stewart. End of section 32. Section 33 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 9. Of the Foundation and Progress of Scientific Chemistry in Great Britain, Part 2. Notwithstanding the important impulse which he gave to chemistry, he published nothing upon that science, except a short paper on the cold produced by the evaporation of ether, which made its appearance in one of the volumes of the Edinburgh Physical and Literary Essays. Dr. Cullen employed Dr. Dobson of Liverpool, at that time his pupil, to make experiments on the heat and cold produced by mixing liquids and solids with each other. Dr. Dobson, in making these experiments, observed that the thermometer, when lifted out of many of the liquids, and suspended a short time in the air beside them, fell to a lower degree than indicated by another thermometer which had undergone no such process. After varying his observations on this phenomenon, he found reason to conclude that it was occasioned by the evaporation of the last drop of liquid which adhered to the bulb of the thermometer, the sinking of the thermometer being always greatest when this instrument was taken out of the most volatile liquids. Dr. Cullen had the curiosity to try whether the same phenomenon would appear on repeating these experiments under the exhausted receiver of an air pump. To satisfy himself, he put on the plate of the air pump a glass goblet containing water, and in the goblet he placed a wide-mouthed vial containing sulfuric ether. The whole was covered with an air pump receiver, having at the upper end a collar of leathers in a brass socket, through which a thick smooth wire could be moved, and from the lower end of this wire, projecting into the receiver, was suspended a thermometer. By pushing down the wire, the thermometer could be dipped into the ether. By drawing it up, could be taken out, and suspended over the vial. The apparatus being thus adjusted, the air pump was worked to extract the air. An unexpected phenomenon immediately appeared, which prevented the experiment from being made in the way intended. The ether was thrown into a violent agitation, which Dr. Cullen ascribed to the extrication of a great quantity of air. In reality, however, it was boiling violently. What was still more remarkable, the ether, by this boiling or rapid evaporation, became all of a sudden so cold as to freeze the water in the goblet around it, though the temperature of the air and of all the materials were at the 54th degree of Fahrenheit at the beginning of the experiment. I have been particular in giving an account of this curious phenomenon, as it was the only direct contribution to the science of chemistry which Dr. Cullen communicated to the public. The nature of the phenomenon was afterwards explained by Dr. Black. In addition to Dr. Cullen, a philosopher, whom the grand stimulus which his lectures gave to the cultivation of scientific chemistry in this country had the important merit of bringing forward. Joseph Black was born in France, on the banks of the Garonne, in the year 1728. His father, Mr. John Black, was a native of Belfast, but of a Scottish family which had been for some time settled there. Mr. Black resided for the most part at Bordeaux, where he was engaged in the wine trade. He married a daughter of Mr. Robert Gordon, of the family of Hillhead, in Aberdeenshire, who was also engaged in the same trade at Bordeaux. Mr. Black was a gentleman of most amiable manners, candid and liberal in his sentiments, and of no common information. These qualities, together with the warmth of his heart, appear very conspicuous in a series of letters to his son, which that son preserved with the nicest care. His good qualities did not escape the discerning eye of the great Montesquieu, one of the presidents of the Court of Justice in that province. This illustrious and excellent man honored Mr. Black with a friendship and intimacy altogether rare, of which his descendants were justly proud. Long before Mr. Black retired from business, his son Joseph was sent home to Belfast, that he might have the education of a British subject. This was in the year 1740, when he was 12 years of age. After the ordinary instruction at the grammar school, he was sent, in 1746, to continue his education in the University of Glasgow. Here he studied with much assiduity and success. Physical science, however, chiefly engrossed his attention. He was a favorite pupil of Dr. Robert Dick, professor of natural philosophy, and the intimate companion of his son and successor. This young professor was of a character peculiarly suited to Dr. Black's taste, having the clearest conception and soundest judgment, accompanied by a modesty that was very uncommon. When he succeeded his father, in 1751, he became the delight of the students. He was carried off by a fever in 1757. Young Black being required by his father to make choice of a profession, he preferred that of medicine as the most suitable to the general habits of his studies. Fortunately, Dr. Cullen had just begun his great career in the College of Glasgow, and having made choice of the field of philosophical chemistry, which lay as yet unaccompanied before him. Hitherto, chemistry had been treated as a curious and useful art, but Cullen saw in it a vast department of the science of nature, depending on principles as immutable as the laws of mechanism, and capable of being formed into a system as comprehensive and as complete as astronomy itself. He conceived the resolution of attempting himself to explore this magnificent field, and expected much reputation from accomplishing his object. Nor was he altogether disappointed. He quickly took the science out of the hands of artists, and exhibited it as a study fit for a gentleman. Dr. Black attended his chemical lectures, and, from the character which has already been given of him, it is needless to say that he soon discovered the uncommon value of his pupil, and attached him to himself, rather as a cooperator and a friend than a pupil. He was considered as his assistant in all his operations, and his experiments were frequently adduced in the lecture as good authority. Young Black laid down a very comprehensive and serious plan of study. This appears from a number of notebooks found among his papers. There are some in which he seems to have inserted everything as it took his fancy, in medicine, chemistry, jurisprudence, or matters of taste. Into others, the same things are transferred, but distributed according to their scientific connections. In short, he kept a journal and a ledger of his studies, and has posted his books like a merchant. What particularly strikes one in looking over these books is the steadiness with which he advanced in any path of knowledge. Things are inserted for the first time from some present impression of their singularity or importance, but without any allusion to their connections. When a thing of the same kind is mentioned again, there is generally a reference back to its fellow, and thus the most isolated facts often acquired a connection which gave them importance. He went to Edinburgh to finish his medical studies in 1750 or 1751, where he lived with his cousin german, Mr. James Russell, professor of natural philosophy in that university. It was the good fortune of chemical science that at this very time the opinions of professors were divided concerning the manner in which certain lithontryptic medicines, particularly lime water, acted in alleviating the excruciating pains of the stone and gravel. The students usually partake of such differences of opinion. They are thereby animated to more serious study, and science gains by their emulation. This was a subject quite to the taste of young Mr. Black, one of Dr. Cullen's most zealous and intelligent chemical pupils. It was, indeed, a most interesting subject, both to the chemist and the physician. All the medicines which were then in vogue as solvents of urinary calculi had a greater or less resemblance to caustic potash or soda, substances so acrid when in a concentrated state that in a short time they reduced the fleshy parts of the animal body to a mere pulp. Thus, though they might possess lithontryptic properties, their exhibition was dangerous, if in unskillful hands. They all seem to derive their efficacy from quicklime, which again derives its power from the fire. It was therefore very natural for them to ascribe its power to igneous matter imbibed from the fire, retained by the lime, and communicated by it to alkalis, which it renders powerfully acrid. Hence, undoubtedly, the term caustic applies to the alkalis in that state, and hence also the acidum pingue of Mayer, which was a peculiar state of fire. It appears from Dr. Black's notebooks that he originally entertained the opinion that caustic alkalis acquired igneous matter from quicklime. In one of them he hints at some way of catching this matter as it escapes from lime, while it becomes mild by exposure to the air. But on the opposite blank page is written, quote, "Nothing escapes. The cup rises considerably by absorbing air." End quote. A few pages further on, he compares the loss of weight sustained by an ounce of chalk when calcined, with its loss while dissolved in muriatic acid. Immediately after this, a medical case is mentioned, which occurred in November 1752. Hence it would appear that he had before that time suspected the real cause of the difference between limestone and burnt lime. He had prosecuted his inquiry with vigor, for the experiments with magnesia are soon after mentioned. These experiments laid open the whole mystery, as appears by another memorandum. Quote, "When I precipitate lime by a common alkali, there is no effervescence. The air quits the alkali for the lime, but it is lime no longer, but CCC. It now effervesces, which good lime will not." End quote. What a multitude of important consequences naturally flowed from this discovery. He now knew to what the causticity of alkalis is owing, and how to induce it or remove it at pleasure. The common notion was entirely reversed. Lime imparts nothing to the alkalis. It only removes from them a peculiar kind of air, carbonic acid gas, with which they were combined, and which prevented their natural caustic properties from being developed. All the former mysteries disappear, and the greatest simplicity appears in those operations of nature which before appeared so intricate and obscure. Dr. Black had fixed upon this subject for his inaugural dissertation, and was induced, in consequence, to defer applying for his degree till he had succeeded in establishing his doctrine beyond the possibility of contradiction. The inaugural essay was delivered at a moment peculiarly favorable to the advancement of science. Dr. Cullen had just been removed to Edinburgh, and there was a vacancy in the chemical chair in Glasgow. It could not be bestowed better than on such an alumnus of the university, on one who had distinguished himself both as a chemist and an excellent reasoner. For few finer models of inductive investigation exist than are displayed in Black's essay on quicklime and magnesia. He was appointed professor of anatomy and lecturer on chemistry in the University of Glasgow in 1756. It was a fortunate circumstance both for himself and for the public that a situation thus presented itself, just at the time when he was under the necessity of settling in the world. a situation which allowed him to dedicate his talents chiefly to the cultivation of chemistry, his favorite science. When Dr. Black took his degree in medicine, he sent some copies of his essay to his father at Bordeaux. A copy was given by the old gentleman to his friend, the President Montesquieu, who, after a few days, called on Mr. Black, and said to him, quote, "Mr. Black, my very good friend, I rejoice with you. Your son will be the honor of your name and family." End quote. This anecdote was told Professor John Robison by the brother of Dr. Black. Thus Dr. Black, while in Glasgow, taught at one and the same time 2 different classes. He did not consider himself very well qualified to teach anatomy, but determined to do his utmost. But he soon afterwards made arrangements with the professor of medicine, who, with the concurrence of the university, exchanged his own chair for that of Dr. Black. Black's medical lectures constituted his chief task while in Glasgow. They gave the greatest satisfaction by their perspicuity and simplicity, and by the cautious moderation of all his general doctrines, and, indeed, all his perspicuity and all his neatness of manner in exhibiting simple truths were necessary to create a relish for moderation and caution, after the brilliant prospects of systematic knowledge to which the students had been accustomed by Dr. Cullen, his celebrated predecessor. But Dr. Black had no wish to form a medical school, distinguished by some all-comprehending doctrine. He satisfied himself with a clear account of as much of physiology as he thought founded on good principles, and a short sketch of such general doctrines as were maintained by the most eminent authors, though perhaps on a less firm foundation. He then endeavored to deduce a few canons of medical practice, and concluded with certain rules founded on successful practice only, but not deducible from the principles of physiology previously laid down. With his medical lectures, he does not appear to have been himself entirely satisfied. He did not encourage conversation on the different topics, and no remains of these lectures were to be found among his papers. The preceding account of them was given to Professor Robison by a surgeon in Glasgow, who attended the 2 last medical courses which Dr. Black ever delivered. Dr. Black's reception at Glasgow by the university was in the highest degree encouraging. His former conduct as a student had not only done him credit in his classes, but had conciliated the affection of the professors to a very high degree. He became immediately connected with the strictest friendship with the celebrated Dr. Adam Smith, a friendship which continued intimate and confidential through the whole of their lives. Both were remarkable for a certain simplicity of character and the most incorruptible integrity. Dr. Smith used to say that no one had less nonsense in his head than Dr. Black, and he often acknowledged himself obliged to him for setting him right in his judgment of character, confessing that he himself was too apt to form his opinion from a single feature. It was during his residence in Glasgow, between the years 1759 and 1763, that he brought to maturity those speculations concerning the combination of heat with matter, which had frequently occupied a portion of his thoughts. It had long been known that ice has the property of continuing always at the temperature of 32 degrees till it be melted. This happens equally though it be placed in contact with the warm hand or surrounded by bodies many degrees hotter than itself. The hotter the bodies are that surround it, the sooner it is melted, but its temperature during the whole process of melting continues uniformly the same. Yet, during the whole process of melting, it is constantly robbing the surrounding bodies of heat, for it makes them colder, without acquiring itself any sensible heat. Dr. Black had some vague notion that the heat so received by the ice, during its conversion into water, was not lost, but was contained in the water. This opinion was founded chiefly on a curious observation of Fahrenheit, recorded by Boerhaave, namely, that water might in some cases be made considerably colder than melting snow, without freezing. In such cases, when disturbed, it would freeze in a moment, and in the act of freezing always gave out a quantity of heat. This opinion was confirmed by observing the slowness with which water is converted into ice, and ice into water. A fine winter day of sunshine is never sufficient to clear the hills of snow, nor is one frosty night capable of covering the ponds with a thick coating of ice. The phenomena satisfied him that much heat was absorbed and fixed in the water which trickles from wreaths of snow, and that much heat emerged from it while water was slowly converted into ice, for during a thaw the melting snow is always colder than the air, and must therefore be always receiving heat from it, while, during a frost, the air is always colder than the freezing water, and must therefore be always receiving heat from it. These observations, and many others which it is needless to state, satisfied Dr. Black that when ice is converted into water, it unites with a quantity of heat, without increasing in temperature, and that when water is frozen into ice, it gives out a quantity of heat without diminishing in temperature. The heat thus combined is the cause of the fluidity of water. As it is not sensible to the thermometer, Dr. Black called it latent heat. He made an experiment to determine the quantity of heat necessary to convert ice into water. This he estimated by the length of time necessary to melt a given weight of ice, measuring how much heat entered into the same weight of water, reduced as nearly to the temperature of ice as possible during the first half hour that the experiment lasted. As the ice continued during the whole of its melting at the same temperature as at first, he concluded that it would absorb, every half hour that the process lasted, as much heat as the water did during the first half hour. The result of this experiment was that the latent heat of water amounts to 140 degrees, or in other words, that this heat, if thrown into a quantity of water, equal in weight to that of the ice melted, would raise its temperature 140 degrees. End of section 33. Section 34 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 9. Of the Foundation and Progress of Scientific Chemistry in Great Britain, Part 3. Dr. Black, having established this discovery in the most incontrovertible manner by simple and decisive experiments, drew up an account of the whole investigation, and the doctrine which he founded upon it, and read it to a literary society which met every Friday in the faculty room of the college, consisting of the members of the university and several gentlemen of the city, who had a relish for science and literature. This paper was read on the 23rd of April, as appears by the registers of the society. Dr. Black quickly perceived the vast importance of this discovery, and took a pleasure in laying before his students a view of the beneficial effects of this habitude of heat in the economy of nature. During the summer season, a vast magazine of heat was accumulated in the water, which, by gradually emerging during congelation, serves to temper the cold of winter. Were it not for this accumulation of heat in water and other bodies, the sun would no sooner go a few degrees to the south of the equator than we should feel all the horrors of winter. He did not confine his views to the congelation of water alone, but extended them to every case of congelation into liquefaction which he has ascribed equally to the evolution or fixation of latent heat. Even those bodies which change from solid to fluid, not all at once, but by slow degrees, as butter, tallow, resins, owe, he found, their gradual softening to the same absorption of heat, and to the same combination of it with the substance undergoing liquefaction. Another subject that engaged his attention at this time was an examination of the scale of the thermometer, to learn whether equal differences of expansion corresponded to equal additions or abstractions of heat. His mode was to mix together equal weights of water of different temperatures, and to measure the temperature of the mixture by a thermometer. It is obvious that the temperature must be the exact mean of that of the two portions of water, and that if the expansion or contraction of the mercury in the thermometer be an exact measure of the difference of temperature, a thermometer, so placed, will indicate the exact mean. Suppose 1 pound of water at 100 degrees to be mixed with 1 pound of water at 200 degrees, and the whole heat still to remain in the mixture. It is obvious that it would divide itself equally between the two portions of water. The water of 100 degrees would become hotter, and the water of 200 degrees would become colder, and the increase of temperature in the colder portion would be just as much as the diminution of temperature in the hotter portion. The colder portion would become hotter by 50 degrees, while the hotter portion would become colder by 50 degrees. Hence, the real temperature, after mixture, would be 150 degrees, and a thermometer plunged into such a mixture, if a true measurer of heat, would indicate 150 degrees. The result of his experiments was, that as high up as he could try, by mixing water of different temperatures, the mercurial thermometer is an accurate measurer of the alterations of temperature. An account of his experiments on this subject was drawn up by him, and read to the Literary Society of the College of Glasgow, on the 28th of March, 1760. Dr. Black, at the time he made these experiments, did not know that he had been already anticipated in them by Dr. Brooke Taylor, the celebrated mathematician who had obtained similar results, and had consigned his experiments to the Royal Society, in whose Transactions for 1723 they were published. It has been since found by Coulomb and Petit that at higher temperatures than 212 degrees, the rate of the expansion of mercury begins to increase. Hence, it happens that at high temperatures, the expansion of mercury is no longer an accurate measure of temperature. Fortunately, the expansion of glass very nearly equals the increment of that of mercury. The consequence is that in a common glass thermometer, mercury measures the true increments of temperature very nearly up to its boiling point, for the boiling point of mercury measured by an air thermometer is 662 degrees, and if a glass mercurial thermometer be plunged into boiling mercury, it will indicate 660 degrees, a difference of only 2 degrees from the true point. There is such an analogy between the cessation of thermometric expansion during the liquefaction of ice and during the conversion of water into steam, that there could be no hesitation about explaining both in the same way. Dr. Black immediately concluded that as water is ice united to a certain quantity of latent heat, so steam is water united to a still greater quantity. The slow conversion of water into steam, notwithstanding the great quantity of heat constantly flowing into it from the fire, left no reasonable doubt about the accuracy of this conclusion. In short, all the phenomena are precisely similar to those of the conversion of ice into water, and so, of course, must the explanation be. So much was he convinced of this, that he taught the doctrine in his lectures in 1761, before he had made a single experiment on the subject, and he explained, with great felicity of argument, many phenomena of nature, which result from this vaporic combination of heat. From notes taken in his class during this session, it appears that nothing more was wanting to complete his views on this subject than a set of experiments to determine the exact quantity of heat which was combined in steam in a state not indicated by the thermometer, and therefore latent, in the same sense that the heat of liquefaction in water is latent. The requisite experiments were first attempted by Dr. Black in 1764. They consisted merely in measuring the time requisite to convert a certain weight of water of a given temperature into steam. The water was put into a tin plate wide-mouthed vessel, and laid upon a red-hot plate of iron. The initial temperature of the water was marked, and the time necessary to heat it from that point to the boiling point noted, and then the time requisite to boil the whole to dryness. It was taken for granted that as much heat would enter into the water during every minute that the experiment lasted, as did during the first minute. From this it was concluded that the latent heat of steam is not less than 810 degrees. Mr. James Watt afterwards repeated these experiments with a better apparatus and very great care, and calculated from his results that the latent heat of steam is not under 950 degrees. Lavoisier and Laplace afterwards made experiments in a different way, and deduced 1000 degrees as the result of their experiments. The subsequent experiments of Count Rumford, made in a very ingenious manner, so as to obviate most of the sources of error to which such researches are liable, come very nearly to those of Lavoisier. 1000 degrees, therefore, is usually nowadays adopted as the number which denotes the true latent heat of steam. Dr. Black continued in the University of Glasgow from 1756 to 1766, much esteemed as an eminent professor, much employed as an able and attentive physician, and much beloved as an amiable and accomplished man, happy in the enjoyment of a small but select society of friends. Meanwhile, his reputation as a chemical philosopher was every day increasing, and pupils from foreign countries carried home with them the peculiar doctrines of his courses, so that fixed air and latent heat began to be spoken of among the naturalists of the continent. In 1766, Dr. Cullen, at that time professor of chemistry in Edinburgh, was appointed professor of medicine, and thus a vacancy was made in the chemical chair of that university. There was but one wish with regard to a successor. Indeed, when the vacancy happened in 1756, on the death of Dr. Plummer, the reputation of Dr. Black, who had just taken his degree, was so high, both as a chemist and an accurate thinker and reasoner, that, had the choice depended on the university, he would have been the new professor of chemistry. He had now, in 1766, greatly added to his claim of merit by his important discovery of latent heat, and he had acquired the esteem of all by the singular moderation and scrupulous caution which marked all his researches. Dr. Black was appointed to the chemical chair in Edinburgh in 1766, to the general satisfaction of the public, but the University of Glasgow suffered an irreparable loss. In this new situation, his talents were more conspicuous and more extensively useful. He saw that the case was so, and while he could not but be gratified by the number of students whom the high reputation of Edinburgh, as a medical school, brought together, his mind was forcibly struck by the importance of his duties as a teacher. This led him to form the resolution of devoting the whole of his study to the improvement of his pupils in the elementary knowledge of chemistry. Many of them came to his class with a very scanty stock of previous knowledge. Many from the workshop of the manufacturer had little or none. He was conscious that the number of this kind of pupils must increase with the increasing activity and prosperity of the country, and they appeared to him by no means the least important part of his auditory. To engage the attention of such pupils, and to be perfectly understood by the most illiterate of his audience, Dr. Black considered as a sacred duty. He resolved, therefore, that plain doctrines taught in the plainest manner should henceforth employ his chief study. To render his lectures perfectly intelligible, they were illustrated by suitable experiments, by the exhibition of specimens, and by the repetition of chemical processes. To this method of lecturing Dr. Black rigidly adhered, endeavoring every year to make his courses more plain and familiar, and illustrating them by a greater variety of examples in the way of experiment. No man could perform these more neatly or successfully. They were always ingeniously and judiciously contrived, clearly establishing the point in view, and were never more complicated than was sufficient for the purpose. Nothing that had the least appearance of quackery, nothing calculated to surprise and astonish his audience, nothing savouring of a showman or sleight-of-hand man was ever permitted in his lecture room. Everything was simple, neat, and elegant, calculated equally to please and to inform. Indeed, simplicity and neatness stamped his character. It was this that constituted the charms of his lectures, and rendered them so delightful to his pupils. I can speak of them from experience, for I was fortunate enough to hear the last course of lectures which he ever delivered. I can say with perfect truth that I never listened to any lectures with so much pleasure as to his, and it was the elegant simplicity of his manner, the perfect clearness of his statements, and the vast quantity of information which he contrived in this way to communicate, that delighted me. I was all at once transported to a new world. My views were suddenly enlarged, and I looked down from a height which I had never before reached. And all this knowledge was communicated without any apparent effort either on the part of the professor or his pupils. His illustrations were just sufficient to answer completely the object in view, and nothing more. No quackery, no trickery, no love of mere dazzle and glitter, ever had the least influence upon his conduct. He constituted the most complete model of a perfect chemical lecturer that I have ever had an opportunity of witnessing. The discovery which Dr. Black had made, that marble is a combination of lime and a peculiar substance, to which he gave the name of fixed air, began gradually to attract the attention of chemists in other parts of the world. It was natural in the first place to examine the nature and properties of this fixed air, and the circumstances under which it is generated. It may seem strange and unaccountable that Dr. Black did not enter with ardor into this new career which he had himself opened, and that he allowed others to reap the corn after having himself sown the grain. Yet he did take some steps towards ascertaining the properties of fixed air, though I am not certain what progress he made. He knew that a candle would not burn in it, and that it is destructive to life, when any living animal attempts to breathe it. He knew that it was formed in the lungs during the breathing of animals, and that it is generated during the fermentation of wine and beer. Whether he was aware that it possesses the properties of an acid, I do not know, though with the knowledge which he possessed that it combines with alkalis and alkaline earths, and neutralizes them, or at least blunts and diminishes their alkaline properties, the conclusion that it partook of alkaline properties was scarcely avoidable. All these, and probably some other properties of fixed air, he was in the constant habit of stating in his lectures from the very commencement of his academical career, though, as he never published anything on the subject himself, it is not possible to know exactly how far his knowledge of the properties of fixed air extended. The oldest manuscript copy of his lectures that I have seen was taken down in writing in the year 1773, and before that time Mr. Cavendish had published his paper on fixed air and hydrogen gas, and had detailed the properties of each. It was impossible from the manuscript of Dr. Black's lectures to know which of the properties of fixed air stated by him were discovered by himself, and which were taken from Mr. Cavendish. This languor and listlessness on the part of Dr. Black is chiefly to be ascribed to the delicate state of his health, which precluded much exertion, and was particularly inconsistent with any attempt at putting his thoughts down on paper. Hence, probably, that carelessness about posthumous fame, and that regardlessness of reputation, which, however it may be accounted for from bodily ailment, must still be considered as a blemish. How differently did Pascal act in a similar state of health? With what energy did he exert himself in spite of bodily ailment? But the tone of his mind was quite different from that of Dr. Black. Gentleness, diffidence, and perhaps even slowness of apprehension were the characteristic features by which the latter was distinguished. There is an anecdote of Black which I was told by the late Benjamin Bell, of Edinburgh, author of a well-known system of surgery, and he assured me that he had it from the late Sir George Clarke, of Pennacook, who was a witness of the circumstance related. Soon after the appearance of Mr. Cavendish's paper on hydrogen gas, in which he made an approximation to the specific gravity of that body, showing that it was at least 10 times lighter than common air, Dr. Black invited a party of his friends to supper, informing them that he had a curiosity to show them. Dr. Hutton, Mr. Clarke of Eldon, and Sir George Clarke of Pennacook were of the number. When the company invited had assembled, he took them into a room. He had the allentois of a calf filled with hydrogen gas, and upon setting it at liberty, it immediately ascended, and adhered to the ceiling. The phenomenon was easily accounted for. It was taken for granted that a small black thread had been attached to the allentois, that this thread passed through the ceiling, and that someone in the apartment above, by pulling the thread, elevated it to the ceiling, and kept it in this position. This explanation was so probable that it was acceded to by the whole company, though, like many other possible theories, it turned out wholly unfounded. For when the allentois was brought down, no thread whatever was found attached to it. Dr. Black explained the cause of the ascent to his admiring friends, but such was his carelessness of his own reputation, and of the information of the public, that he never gave the least account of this curious experiment even to his class, and more than 12 years elapsed before this obvious property of hydrogen gas was applied to the elevation of air balloons, by Monsieur Charles, in Paris. The constitution of Dr. Black had always been exceedingly delicate. The slightest cold, the most trifling approach to repletion, immediately affected his chest, occasioned feverishness, and if the disorder continued for 2 or 3 days, brought on a spitting of blood. In this situation, nothing restored him to ease, but relaxation of thought and gentle exercise. The sedentary life to which study confined him was manifestly hurtful, and he never allowed himself to indulge in any investigation that required intense thought, without finding these complaints increased. Thus situated, Dr. Black was obliged to be a contented spectator of the rapid progress which chemistry was making, without venturing himself to engage in any of the numerous investigations which presented themselves on every side. Such indeed was the eagerness with which chemistry was at that time prosecuted, and such the passion for discovery, that there was some risk that his undoubted claim to originality and priority in his own great discoveries might be called in question, and even rendered doubtful. His friends at least were afraid of this, and often urged him to do justice to himself by publishing an account of his own discoveries. He more than once began the task, but was so nice in his notions of the manner in which it should be executed, that the pains he took in forming a plan of the work never failed to affect his health, and oblige him to desist. It is known that he felt hurt at the publication of several of Lavoisier's papers, in the Mémoires de l'Académie, without any allusion whatever to what he himself had previously done on the same subject. How far Lavoisier was really culpable, and whether he did not intend to do full justice to all the claims of his predecessors, cannot be known, as he was cut off in the midst of his career, while so many of his scientific projects remained unexecuted. From the posthumous works of Lavoisier, there is some reason for believing that if he had lived, he would have done justice to all parties, but there is no doubt that Dr. Black, in the meantime, thought himself aggrieved, and that he formed the intention of doing himself justice by publishing an account of his own discoveries. However, this intention was thwarted and prevented by bad health. End of section 34. Section 35 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 9, of the Foundation and Progress of Scientific Chemistry in Great Britain, Part 4. No one contributed more largely to establish, to support, and to increase the high character of the medical school in the University of Edinburgh than Dr. Black. His talent for communicating knowledge was not less eminent than his faculty of observation. He soon became one of the principal ornaments of the university, and his lectures were attended by an audience which continued increasing from year to year for more than 30 years. His personal appearance and manners were those of a gentleman, and peculiarly pleasing. His voice in lecturing was low, but fine, and his articulation so distinct that he was perfectly well heard by an audience consisting of several hundreds. While in Glasgow, he had practiced extensively as a physician, but in Edinburgh he declined general practice, and confined his attendance to a few families of intimate and respected friends. He was, however, a physician of good repute in a place where the character of a physician implied no common degree of liberality, propriety, and dignity of manners, as well as of learning and skill. Such was Dr. Black as a public man. While young, his countenance was comely and interesting, and as he advanced in years, it continued to preserve that pleasing expression of inward satisfaction which, by giving ease to the beholder, never fails to please. His manners were simple, unaffected, and graceful. He he was of the most easy approach, affable, and readily entered into conversation, whether serious or trivial, for he was not merely a man of science, but was well acquainted with the elegant accomplishments. He had an accurate musical ear, and a voice which would obey it in the most perfect manner. He sang and performed on the flute with great taste and feeling, and could sing a plain air at sight, which many instrumental performers cannot do. Music was his amusement in Glasgow. After his removal to Edinburgh, he gave it up entirely. Without having studied drawing, he had acquired a considerable power of expression with his pencil, both in figures and in landscape. He was peculiarly happy in expressing the passions, and seemed in this respect to have the talents of a historical painter. Figure, indeed, of every kind, attracted his attention. In architecture, furniture, ornament of every sort, it was never a matter of indifference to him. Even a retort or a crucible was to his eye an example of beauty or deformity. These are not indifferent things. They are features of an elegant mind, and they account for some part of that satisfaction and pleasure which persons of different habits and pursuits felt in Dr. Black's company and conversation. Those circumstances of form, and in which Dr. Black perceived or sought for beauty, were suitableness or propriety, something that rendered them well adapted for the purposes for which they were intended. This love for propriety constituted the leading feature in Dr. Black's mind. It was the standard to which he constantly appealed, and to which he endeavored to make the directing principle of his conduct. Dr. Black was fond of society, and felt himself beloved in it. His chief companions, in the earlier part of his residence in Edinburgh, were Dr. Adam Smith, Mr. David Hume, Dr. Adam Ferguson, Mr. John Home, Dr. Alexander Carlyle, and a few others. Mr. Clark of Eldon and his brother Sir George, Dr. Roebuck, and Dr. James Hutton, particularly the latter, were affectionately attached to him, and in their society he could indulge in his professional studies. Dr. Hutton was the only person near him to whom Dr. Black imparted every speculation in chemical science, and who knew all his literary labours. Seldom were the two friends asunder for 2 days together. Towards the close of the 18th century, the infirmities of advanced life began to bear more heavily on his feeble constitution. Those hours of walking and gentle exercise, which had hitherto been necessary for his ease, were gradually curtailed. Company and conversation began to fatigue. He went less abroad, and was visited only by his intimate friends. His duty at college became too heavy for him, and he got an assistant, who took a share of the lectures, and relieved him from the fatigue of the experiments. The last course of lectures which he delivered was in the winter of 1796-7. After this, even lecturing was too much for his diminished strength, and he was obliged to absent himself from the class altogether. But he still retained his usual affability of temper, and his habitual cheeriness, and even to the very last was accustomed to walk out and take occasional exercise. As his strength declined, his constitution became more and more delicate. Every cold he caught occasioned to some degree of spitting of blood, yet he seemed to have this unfortunate disposition of body almost under command, so that he never allowed it to proceed far, or to occasion any distressing illness. He spun his thread of life to the very last fibre. He guarded against illness by restricting himself to an abstemious diet, and he met his increasing infirmities with a proportional increase of attention and care, regulating his food and exercise by the measure of his strength. Thus he made the most of a feeble constitution, by preventing the access of disease from abroad, and enjoyed a state of health which was feeble indeed, but scarcely interrupted, as well as a mind undisturbed in the calm and cheerful use of its faculties. His only apprehension was that of a long-continued sickbed, from the humane consideration of the trouble and distress that he might thus occasion to attending friends, and never was such generous wish more completely gratified than in his case. On the 10th of November, 1799, in the 71st year of his age, he expired without any convulsion, shock, or stupor, to announce or retard the approach of death. Being at table with his usual fare, some bread, a few prunes, and a measured quantity of milk, diluted with water, and having the cup in his hand when the last stroke of his pulse was to be given, he set it down on his knees, which were joined together, and kept it steady with his hand in the manner of a person perfectly at ease, and in this attitude expired without spilling a drop, and without a writhe in his countenance, as if an experiment had been required to show his friends the facility with which he departed. His servant opened the door to tell him that someone had left his name, but getting no answer, stepped about halfway to him, and seeing him sitting in that easy posture, supporting his basin of milk with one hand, he thought that he had dropped asleep, which was sometimes wont to happen after meals. He went back and shut the door, but before he got downstairs some anxiety, which he could not account for, made him return and look again at his master. Even then he was satisfied, after coming pretty near him, and turned to go away, but he again returned, and coming close up to him, he found him without life. His very near neighbour, Mr. Benjamin Bell, the surgeon, was immediately sent for, but nothing whatever could be done. Dr. Black's writings are exceedingly few, consisting altogether of no more than 3 papers. The first, entitled Experiments under Magnesia alba, Quicklime, and other alkaline substances, constituted the subject of his inaugural dissertation. It afterwards appeared in an English dress in one of the volumes of the Edinburgh Physical and Literary Essays, in the year 1755. Mr. Creech, the bookseller, published it in a separate pamphlet, together with Dr. Cullen's little essay on the cold produced by evaporating fluids, in the year 1796. This essay exhibits one of the very finest examples of inductive reasoning to be found in the English language. The author shows that magnesia is a peculiar earthy body, possessed of properties very different from lime. He gives the properties of lime in a pure state, and proves that it differs from limestone merely by the absence of the carbonic acid, which is a constituent of limestone. Limestone is a carbonate of lime. Quicklime is the pure uncombined earth. He shows that magnesia has also the property of combining with carbonic acid, that caustic potash, or soda, is merely these bodies in a pure or isolated state, while the mild alkalis are combinations of these bodies with carbonic acid. The reason why quicklime converts mild into caustic alkali is that the lime has a stronger affinity for the carbonic acid than the alkali. Hence the lime is converted into carbonate of lime, and the alkali, deprived of its carbonic acid, becomes caustic. Mild potash is a carbonate of potash. Caustic potash is a potash freed from carbonic acid. The publication of this essay occasioned a controversy in Germany, which was finally settled by Jacquin and Lavoisier, who repeated Dr. Black's experiments and showed them to be correct. Dr. Black's second paper was published in the Philosophical Transactions for 1775. It is entitled The Supposed Effect of Boiling on Water, in disposing it to freeze more readily, ascertained by experiments. He shows that when water that has been recently boiled is exposed to cold air, it begins to freeze as soon as it reaches the freezing point, while water that has not been boiled may be cooled some degrees below the freezing point before it begins to congeal. But if the unboiled water be constantly stirred during the whole time of its exposure, it begins to freeze when cooled down to the freezing point, as well as the other. He shows that the difference between the two waters consists in this, that the boiled water is constantly absorbing air, which disturbs it, whereas the other water remains in a state of rest. His last paper was An Analysis of the Water of Some Boiling Springs in Iceland, published in the Transactions of the Royal Society of Edinburgh. This was the water of the geyser spring, brought from Iceland by Sir J. Stanley. Dr. Black found it to contain a great deal of silica, held in solution in the water by caustic soda. The tempting career which Dr. Black opened, and which he was unable to prosecute for want of health, soon attracted the attention of one of the ablest men that Great Britain has produced. I mean Mr. Cavendish. The Honourable Henry Cavendish was born in London on the 10th of October, 1731. His father was Lord Charles Cavendish, a cadet of the House of Devonshire, one of the oldest families in England. During his father's lifetime he was kept in rather narrow circumstances, being allowed an annuity of £500 only, while his apartments were a set of stables, fitted up for his accommodation. It was during this period that he acquired those habits of economy, and those singular oddities of character, which he exhibited ever after in so striking a manner. At his father's death he was left a very considerable fortune, and an aunt who died at a later period bequeathed him a very handsome addition to it. But in consequence of the habits of economy which he had acquired, it was not in his power to spend the greater part of his annual income. This occasioned a yearly increase to his capital, till at last it accumulated so much, without any care on his part, that at the period of his death he left behind him nearly £1,300,000, and he was at that time the greatest proprietor of stock in the Bank of England. On one occasion, the money in the hands of his bankers had accumulated to the amount of £70,000. These gentlemen, thinking it improper to keep so large a sum in their hands, sent one of the partners to wait upon him, in order to learn how he desired it disposed of. This gentleman was admitted, and after employing the necessary precautions to a man of Mr. Cavendish's peculiar disposition, stated the circumstance, and begged to know whether it would not be proper to lay out the money at interest. Mr. Cavendish dryly answered, "You may lay it out if you please," and left the room. He hardly ever went into any other society than that of his scientific friends. He never was absent from the weekly dinner of the Royal Society Club at the Crown and Anchor Tavern in the Strand. At these dinners, when he happened to be seated near those that he liked, he often conversed a great deal, though at other times he was very silent. He was likewise a constant attendant at Sir Joseph Banks's Sunday evening meetings. He had a house in London, which he only visited once or twice a week at stated times, and without ever speaking to the servants. It contained an excellent library, to which he gave all literary men the freest and most unrestrained access. But he lived in a house on Clapham Common, where he scarcely ever received any visitors. his relation, Lord George Cavendish, to whom he left by will the greatest part of his fortune, visited him only once a year, and the visit hardly ever exceeded 10 or 12 minutes. He was shy and bashful to a degree bordering on disease. He could not bear to have any person introduced to him, or to be pointed out in any way as a remarkable man. One Sunday evening he was standing at Sir Joseph Banks in a crowded room, conversing with Mr. Hatchett, when Dr. Ingenhouse, who had a great deal of pomposity of manner, came up with an Austrian gentleman in his hand, and introduced him formally to Mr. Cavendish. He mentioned the titles and qualifications of his friend at great length, and said that he had been peculiarly anxious to be introduced to a philosopher so profound and so universally known and celebrated as Mr. Cavendish. As soon as Dr. Ingenhouse had finished, the Austrian gentleman began, and assured Mr. Cavendish that his principal reason for coming to London was to see and converse with one of the greatest ornaments of the age, and one of the most illustrious philosophers that ever existed. To all these high-flown speeches, Mr. Cavendish answered not a word, but stood with his eyes cast down quite abashed and confounded. At last, spying an opening in the crowd, he darted through it with all the speed of which he could master, nor did he stop till he reached his carriage, which drove him directly home. Of a man whose habits were so retired, and whose intercourse with society was so small, there is nothing else to relate except his scientific labours. The current of his life passed on with the utmost regularity. The description of a single day would convey a correct idea of his whole existence. At one time, he was in the habit of keeping an individual to assist him in his experiments. This place was for some time filled by Sir Charles Blagden, but they did not agree well together, and after some time Sir Charles left him. Mr. Cavendish died on the 4th of February, 1810, aged 78 years, 4 months, and 6 days. When he found himself dying, he gave directions to his servant to leave him alone, and not to return till a certain time which he specified, and by which period he expected to be no longer alive. The servant, however, who was aware of the state of his master, and was anxious about him, opened the door of the room before the time specified, and approached the bed to take a look at the dying man. Mr. Cavendish, who was still sensible, was offended at the intrusion, and ordered him out of the room with a voice of displeasure, commanding him not by any means to return till the time specified. When he did come back at that time, he found his master dead. What a contrast between the characters of Mr. Cavendish and Dr. Black. End of section 35. Section 36 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 9. Of the Foundation and Progress of Scientific Chemistry in Great Britain, Part 5. The appearance of Mr. Cavendish did not much prepossess strangers in his favour. He was somewhat above the middle size, his body rather thick, and his neck rather short. He stuttered a little in his speech, which gave him an air of awkwardness. His countenance was not strongly marked, so as to indicate the profound abilities which he possessed. This was probably owing to the total absence of all the violent passions. His education seems to have been very complete. He was an excellent mathematician, a profound electrician, and a most acute and ingenious chemist. he never ventured to give an opinion on any subject, unless he had studied it to the bottom. He appeared before the world first as a chemist, and afterwards as an electrician. The whole of his literary labours consist of 18 papers, published in the Philosophical Transactions, which, though they occupy only a few pages, are full of the most important discoveries and the most profound investigations. Of these papers, there are 10 which treat of chemical subjects, 2 treat of electricity, 2 of meteorology, 3 are connected with astronomy, and there is 1, the last which he wrote, which gives his method of dividing astronomical instruments. Of the papers in question, those alone which treat of chemistry can be analyzed in a work like this. 1. His first paper, entitled Experiments on Fictitious Air, was published in the year 1766, when Mr. Cavendish was 35 years of age. Dr. Hales had demonstrated, as had previously been done by Van Helmont and Glauber, that air is given out by a vast number of bodies in peculiar circumstances. But he never suspected that any of the airs which he obtained differed from common air. Indeed, common air had always been considered as an elementary substance, to which every elastic fluid was referred. Dr. Black had shown that the mild alkalis and limestone, and carbonate of magnesia, were combinations of these bodies with a gaseous substance, to which he had given the name of fixed air. And he had pointed out various methods of collecting this fixed air, though he himself had not made much progress in investigating its properties. This paper of Mr. Cavendish may be considered as a continuation of the investigations begun by Dr. Black. He shows that there exist 2 species of air quite different in their properties from common air, and he calls them inflammable air and fixed air. Inflammable air, hydrogen gas, is evolved when iron, zinc, or tin are dissolved in dilute sulfuric or muriatic acid. Iron yielded about 1/22nd part of its weight of inflammable air, zinc about 1/23rd or 1/24th of its weight, and tin about 1/44th of its weight. The properties of the inflammable air were the same, whichever of the 3 metals was used to procure it, and whether they were dissolved in sulfuric or muriatic acids. When the sulfuric acid was concentrated, iron and zinc dissolved in it with difficulty and only by the assistance of heat. The air given out was not inflammable, but consisted of sulfurous acid. These facts induced Mr. Cavendish to conclude that the inflammable air evolved in the first case was the unaltered phlogiston of the metals, while the sulfurous acid evolved in the second case was a compound of the same phlogiston and a portion of the acid, which deprived it of its inflammability. This opinion was very different from that of Stahl, who considered combustible bodies as compounds of phlogiston with acids or calces. Cavendish found the specific gravity of his inflammable air about 11 times less than that of common air. This determination is under the truth, but the error is, at least in part, owing to the quantity of water held in solution by the air, and which, as Mr. Cavendish showed, amount to about 1/9 of the weight of the air. He tried the combustibility of the inflammable air, when mixed with various proportions of common air, and found that it exploded with the greatest violence when mixed with rather more than its bulk of common air. Copper, he found, when dissolved in muriatic acid by the assistance of heat, yielded no inflammable air, but an air which lost its elasticity when it came in contact with water. This air, the nature of which Mr. Cavendish did not examine, was muriatic acid gas, the properties of which were afterwards investigated by Dr. Priestley. The fixed air, carbonic acid gas, on which Mr. Cavendish made his experiments, was obtained by dissolving marble in muriatic acid. He found that it might be kept over mercury for any length of time without undergoing any alteration, that it was gradually absorbed by cold water, and that 100 measures of water of the temperature 55 degrees absorbed 103.8 measures of fixed air. The whole of the air thus absorbed was separated again by exposing the water to a boiling heat, or by leaving it for some time in an open vessel. Alcohol, the specific gravity not mentioned, absorbed 2 1/4 times its bulk of this air, and olive oil about 1/3 of its bulk. The specific gravity of fixed air he found 1.57, that of common air being 1. Fixed air is incapable of supporting combustion, and common air, when mixed with it, supports combustion a much shorter time than when pure. A small wax taper burnt 80 seconds in a receiver, which held 180-ounce measures, when filled with common air only. The same taper burnt 51 seconds in the same receiver when filled with a mixture of 1 volume fixed air, and 19 volumes of common air. When the fixed air was 3/40 of the whole volume, the taper burnt 23 seconds. When the fixed air was 1/10, the taper burnt 11 seconds. When it was 6/55, or 1 to 9.16 of the whole mixture, the taper would not burn at all. Mr. Cavendish was of opinion that more than one kind of fixed air was given out by marble. In other words, that the elastic fluid emitted consisted of 2 different airs, one more absorbable by water than the other. He drew his conclusion from the circumstance that after a solution of potash had been exposed to a quantity of fixed air for some time, it ceased to absorb any more. Yet, if the residual portion of air were thrown away and new fixed air substituted in its place, it began to absorb again. But Mr. Dalton has since given a satisfactory explanation of this seeming anomaly by showing that the absorbability of fixed air in water is proportional to its purity, and that when mixed with a great quantity of common air or any other gas not soluble in water, it ceases to be sensibly absorbed. Mr. Cavendish ascertained the quantity of fixed air contained in marble, carbonate of ammonia, common pearlashes, and carbonate of potash, but notwithstanding the care with which these experiments were made, they are of little value, because the proper precautions could not be taken, in that infant state of chemical science, to have these salts in a state of purity. The following were the results obtained by Mr. Cavendish. 1,000 grains of marble contained 408 grains of fixed air. 1,000 grains of carbonate of ammonia contained 533 grains of fixed air. 1,000 grains of pearlashes contained 284 grains of fixed air. 1,000 grains of carbonate of potash contained 423 grains of fixed air. Supposing the marble, carbonate of ammonia, and carbonate of potash to have been pure anhydrous simple salts, their composition would be: 1,000 grains of marble contain 440 grains of fixed air. 1,000 grains of carbonate of ammonia contain 709.6 grains of fixed air. 1,000 grains of carbonate of potash contain 314.2 grains of fixed air. Bicarbonate of potash was first obtained by Dr. Black. Mr. Cavendish formed this salt by dissolving pearlashes in water, and passing a current of carbonic acid gas through the solution till it deposited crystals. These crystals were not altered by exposure to the air, did not deliquesce, and were soluble in about 4 times their weight of cold water. Dr. McBride had already ascertained that vegetable and animal substances yield fixed air by putrefaction and fermentation. Mr. Cavendish found by experiment that sugar when dissolved in water and fermented gives about 57/100ths of its weight of fixed air, possessing exactly the properties of fixed air from marble. During the fermentation no air was absorbed, nor was any change induced on the common air, at the surface of the fermenting liquor. Apple juice fermented much faster than sugar, but the phenomena were the same, and the fixed air emitted amounted to 381/1000 of the weight of the solid extract of apples. Gravy and raw meat yielded inflammable air during their putrefaction, the former in much greater quantity than the latter. This air, as far as Mr. Cavendish's experiments went, he found the same as the inflammable air from zinc by dilute sulfuric acid, but its specific gravity was a little higher. This paper of Mr. Cavendish was the first attempt by chemists to collect the different kinds of air, and endeavour to ascertain their nature. Hence all his processes were in some measure new. They served as a model to future experimenters, and were gradually brought to their present state of simplicity and perfection. He was the first person who attempted to determine the specific gravity of airs, by comparing their weight with that of the same bulk of common air. And though his apparatus was defective, yet the principle was good, and is the very same which is still employed to accomplish the same object. Mr. Cavendish then first began the true investigation of gases, and in his first paper he determined the peculiar nature of 2 very remarkable gases, carbonic and hydrogen. 2. Mineral waters have at all times attracted the attention of the faculty in consequence of their peculiar properties and medical virtues. Some faint steps towards their investigation were taken by Boyle. Duclos attempted a chemical analysis of the mineral waters in France, and Keren made a similar investigation of the mineral waters of Sweden. Though these experiments were rude and inaccurate, they led to the knowledge of several facts respecting mineral waters which chemists were unable to explain. One of these was the existence of a considerable quantity of calcareous earth in some mineral waters, which was precipitated by boiling. Nobody could conceive in what way this insoluble substance, carbonate of lime, was held in solution, nor why it was thrown down when the water was raised to a boiling heat. It was to determine this point that Mr. Cavendish made his experiments on Rathbone Place water, which were published in the year 1767, and which may be considered as the first analysis of a mineral water that possessed tolerable accuracy. Rathbone Place water was raised by a pump, and supplied the portion of London in its immediate neighbourhood. Mr. Cavendish found that when boiled, it deposited a quantity of earthy matter, consisting chiefly of lime, but containing also a little magnesia. This he showed was held in solution by fixed air, and he proved experimentally that when an excess of this gas is present, it has the property of holding lime and magnesia in solution. Besides these earthy carbonates, the water was found to contain a little ammonia, some sulfate of lime, and some common salt. Mr. Cavendish examined, likewise, some other pump water in London, and showed that it contained lime, held in solution by carbonic acid, 3. Dr. Priestley, at a pretty early period in his chemical career, had discovered that when nitrous gas is mixed with common air over water, a diminution of bulk takes place, that there is a still greater diminution of bulk when oxygen gas is employed instead of common air, and that the diminution is always proportional to the quantity of oxygen gas present in the gas mixed with the nitrous gas. This discovery induced him to employ nitrous gas as a test of the quantity of oxygen present in common air, and various instruments were contrived to facilitate the mixture of the gases, and the measurement of the diminution of volume which took place. As the goodness of air, or its fitness to support combustion and maintain animal life, was conceived to depend upon the proportion of oxygen gas which it contained, these instruments were distinguished by the name of eudiometers. The simplest of them was contrived by Fontana, and is usually distinguished by the name of the eudiometer of Fontana. Philosophers, in examining air by means of this instrument, at various seasons, and in various places, had found considerable differences in the diminution of bulk. Hence they inferred that the proportion of oxygen varies in different places, and to this variation they ascribed the healthiness or noxiousness of particular situations. For example, Dr. Ingenhouse had found a greater proportion of oxygen in the air above the sea and on the seacoast, and to this he ascribed the healthiness of maritime situations. Mr. Cavendish examined this important point with his usual patient industry and acute discernment, and published the result in the Philosophical Transactions for 1783. He ascertained that the apparent variations were owing to inaccuracies in making the experiment, and that when the requisite precautions are taken, the proportion of oxygen in air is found constant in all places and at all seasons. This conclusion has since been confirmed by numerous observations in every part of the globe. Mr. Cavendish also analyzed common air, and found it to consist of 79.16 volumes azotic gas, 20.84 volumes oxygen gas, equaling 100.00. 4. For many years, it was the opinion of chemists that mercury is essentially liquid, and that no degree of cold is capable of congealing it. Professor Braun's accidental discovery that it may be frozen by cold, like other liquids, was at first doubted, and when it was finally established by the most conclusive experiments, it was inferred from the observations of Braun that the freezing point of mercury is several hundred degrees below zero on Fahrenheit scale. It became an object of great importance to determine the exact point of the congelation of this metal by accurate experiments. This was done at Hudson's Bay by Mr. Hutchins, who followed a set of directions given him by Mr. Cavendish, and from his experiments Mr. Cavendish, in a paper inserted in the Philosophical Transactions for 1783, deduced that the freezing point of mercury is 38.66 degrees below the zero of Fahrenheit's thermometer. 5. These experiments naturally drew the attention of Mr. Cavendish to the phenomena of freezing, to the action of freezing mixtures, and the congelation of acids. He employed Mr. M'Nab, who was settled in the neighborhood of Hudson's Bay, to make the requisite experiments, and he published 2 very curious and important papers on these subjects in the Philosophical Transactions for 1786 and 1788. He explains the phenomena of congelation exactly according to the theory of Dr. Black, but rejecting the hypothesis that heat is a substance sui generis, and thinking it more probable, with Sir Isaac Newton, that it is owing to the rapid internal motion of the particles of the hot body. The latent heat of water he found to be 150 degrees. The observations on the congelation of nitric and sulfuric acids are highly interesting. He showed that their freezing points vary considerably, according to the strength of each, and drew up tables indicating the freezing points of acids of various degrees of strength. 6. But the most splendid and valuable of Mr. Cavendish's chemical experiments were published in 2 papers entitled Experiments on Air in the Transactions of the Royal Society for 1784 and 1785. The object of these experiments was to determine what happened during the phlogistication of air, as it was at that time termed, that is, the change which air underwent when metals were calcined in contact with it, when sulfur or phosphorus was burned in it, and in several similar processes. He showed, in the first place, that there was no reason for supposing that carbonic acid was formed, except when some animal or vegetable substance was present, that when hydrogen gas was burnt in contact with air or oxygen gas, it combined with that gas and formed water, that nitrous gas, by combining with the oxygen of the atmosphere, formed nitrous acid, and that when oxygen and azotic gas are mixed in the requisite proportions, and electric sparks pass through the mixture, they combine and form nitric acid. The first of these opinions occasioned a controversy between Mr. Cavendish and Mr. Kirwan, who maintains that carbonic acid is always produced when air is phlogisticated. 2 papers on this subject by Kirwan and 1 by Cavendish are inserted in the Philosophical Transactions for 1784, each remarkable examples of the peculiar manner of the respective writers. All the arguments of Kirwan are founded on the experiments of others. He displays great reading and a strong memory, but does not discriminate between the merits of the chemists on whose authority he founds his opinions. Mr. Cavendish, on the other hand, never advances a single opinion, which he has not put to the test of experiment, and never suffers himself to go any further than his experiment will warrant. Whatever is not accurately determined by unacceptable trials is merely stated as a conjecture on which little stress is laid. In the first of these celebrated papers, Mr. Cavendish has drawn a comparison between the phlogistic and antiphlogistic theories of chemistry. He has shown that each of them is capable of explaining the phenomena in a satisfactory manner, though it is impossible to demonstrate the truth of either, and he has given the reasons which induced him to prefer the phlogistic theory, reasons which the French chemists were unable to refute, and which they were wise enough not to notice. There cannot be a more striking proof of the influence of fashion, even in science, and of the unwarrantable precipitation with which opinions are rejected or embraced by philosophers, than the total inattention paid by the chemical world to this admirable dissertation. Had Mr. Kirwan adopted the opinions of Mr. Cavendish, when he undertook the defense of phlogiston, instead of trusting to the vague experiments of inaccurate chemists, he would not have been obliged to yield to his French antagonists, and the antiphlogistic theory would not so speedily have gained ground. Such is an epitome of the chemical papers of Mr. Cavendish. They contain 5 notable discoveries, namely, 1. The nature and properties of hydrogen gas. 2. The solubility of bicarbonates of lime and magnesia in water. 3. The exact proportion of the constituents of common air. 4. The composition of water. 5. The composition of nitric acid. It is to him also that we are indebted for our knowledge of the freezing point of mercury, and he was likewise the first person who showed that potash has a stronger affinity for acids than soda has. His experiments on the subject are to be found in a paper on mineral waters, published in the Philosophical Transactions by Dr. Donald Munro. End of Volume 1. End of Section 36.
Section 37 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 1 of The Foundation and Progress of Scientific Chemistry in Great Britain, Part 1. While Mr. Cavendish was extending the bounds of pneumatic chemistry with the caution and precision of a Newton, Dr. Priestley, who had entered on the same career, was proceeding with a degree of rapidity quite unexampled. While from his happy talents and inventive faculties he contributed no less essentially to the progress of the science, and certainly more than any other British chemist, to its popularity. Joseph Priestley was born in 1733 at Fieldhead, about 6 miles from Leeds in Yorkshire. His father, Jonas Priestley, was a maker and dresser of woolen cloth, and his mother, the only child of Joseph Swift, a farmer in the neighbourhood. Dr. Priestley was the eldest child, and his mother, having children very fast, he was soon committed to the care of his maternal grandfather. He lost his mother when he was only 6 years of age, and was soon after taken home by his father and sent to school in the neighbourhood. His father being but poor and encumbered with a large family, his sister, Mrs. Keeley, a woman in good circumstances and without children, relieved him of all care of his eldest son by taking him and bringing him up as her own. She was a dissenter, and her house was the resort of all the dissenting clergy in the country. Young Joseph was sent to a public school in the neighbourhood, and at 16 had made considerable progress in Latin, Greek, and Hebrew. Having shown a passion for books and for learning at a very early age, his aunt conceived hopes that he would one day become a dissenting clergyman, which she considered as the first of all professions, and he entered eagerly into her views. But his health declining about this period, and something like physical symptoms having come on, he was advised to turn his thoughts to trade, and to settle as a merchant in Lisbon. This induced him to apply to the modern languages, and he learned French, Italian, and German without a master. Recovering his health, he abandoned his new scheme, and resumed his former plan of becoming a clergyman. In 1752 he was sent to the Academy of Daventry to study under Dr. Ashworth, the successor of Dr. Doddridge. He had already made some progress in mechanical philosophy and metaphysics, and dipped into Chaldee, Syriac, and Arabic. At Daventry he spent 3 years, engaged keenly in studies connected with divinity, and wrote some of his earliest theological tracts. Freedom of discussion was admitted to its full extent in this academy. The two masters espoused different sides upon most controversial subjects, and the scholars were divided into two parties, nearly equally balanced. The discussions, however, were conducted with perfect good humour on both sides, and Dr. Priestley, as he tells us himself, usually supported the heterodox opinion, but he never at any time, as he assures us, advanced arguments which he did not believe to be good, or supported an opinion which he did not consider as true. When he left the academy, he settled at Needham in Suffolk, as an assistant in a small, obscure dissenting meeting-house, where his income never exceeded £30 a year. His hearers fell off in consequence of their dislike of his theological opinions, and his income underwent a corresponding diminution. He attempted a school, but his scheme failed of success, owing to the bad opinion which his neighbours entertained of his orthodoxy. His situation would have been desperate had he not been occasionally relieved by sums out of charitable funds, procured by means of Dr. Benson and Dr. Kippis. Several vacancies occurred in his vicinity, but he was treated with contempt, and thought unworthy to fill any of them. Even the dissenting clergy in the neighbourhood thought it a degradation to associate with him, and durst not ask him to preach, not from any dislike to his theological opinions, for several of them thought as freely as he did, but because the genteeler part of their audience always absented themselves when he appeared in the pulpit. A good many years afterwards, as he informs us himself, when his reputation was very high, he preached in the same place, and multitudes flocked to hear the very same sermons, which they had formerly listened to with contempt and dislike. His friends, being aware of the disagreeable nature of his situation at Needham, were upon the alert to procure him a better. In 1758, in consequence of the interest of Mr. Gill, he was invited to appear as a candidate for a meeting-house in Sheffield, vacant by the resignation of Mr. Wadsworth. He appeared accordingly and preached, but was not approved of. Mr. Haynes, the other minister, offered to procure him a meeting-house at Nantwich in Cheshire. This situation he accepted, and to save expenses he went from Needham to London by sea. At Nantwich he continued 3 years, and spent his time much more agreeably than he had done at Needham. His opinions were not obnoxious to his hearers, and controversial discussions never introduced. Here he established a school, and found the business of teaching, contrary to his expectation, an agreeable and even interesting employment. He taught from 7 in the morning till 4 in the afternoon, and after the school was dismissed he went to the house of Mr. Tomlinson, an eminent attorney in the neighbourhood, where he taught privately till 7 in the evening. Being thus engaged 12 hours every day in teaching, he had little time for private study. It is, indeed, scarcely conceivable how, under such circumstances, he could prepare himself for Sunday. Here, however, his circumstances began to mend. At Needham it required the utmost economy to keep out of debt, but at Nantwich he was able to purchase a few books and some philosophical instruments, as a small air pump, an electrical machine, etc. These he taught his eldest scholars to keep in order and manage, and by entertaining their parents and friends with experiments, in which the scholars were generally the operators, and sometimes the lecturers too, he considerably extended the reputation of his school. It was at Nantwich that he wrote his grammar for the use of his school, a book of considerable merit, though its circulation was never extensive. This latter circumstance was probably owing to the superior reputation of Dr. Louth, who published his well-known grammar about 2 years afterwards. Being boarded in the house of Mr. Eddowes, a very sociable and sensible man, and a lover of music, Dr. Priestley was induced to play a little on the English flute, and though he never was a proficient, he informs us that it contributed more or less to his amusement for many years. He recommends the knowledge and practice of music to all studious persons, and thinks it rather an advantage for them if they have no fine ear or exquisite taste, as they will in consequence be more easily pleased, and less apt to be offended when the performances they hear are but indifferent. The Academy at Warrington was instituted while Dr. Priestley was at Needham, and he was recommended by Dr. Clarke, Dr. Benson, and Dr. Taylor as tutor in the languages, but Dr. Aikin, whose qualifications were considered as superior, was preferred before him. However, on the death of Dr. Taylor, and the advancement of Dr. Aikin to be tutor in divinity, he was invited to succeed him. This offer he accepted, though his school at Nantwich was likely to be more gainful, for the employment at Warrington was more liberal and less painful. In this situation he continued 6 years, actively employed in teaching and in literary pursuits. Here he wrote a variety of works, particularly his History of Electricity, which first brought him into notice as an experimental philosopher, and procured him celebrity. After the publication of this work, Dr. Percival of Manchester, then a student at Edinburgh, procured him the title of Doctor in Laws from that university. Here he married a daughter of Mr. Isaac Wilkinson, an ironmonger in Wales, a woman whose qualities he has highly extolled, and who died after he went to America. In the academy he spent his time very happily, but it did not flourish. A quarrel had broken out between Dr. Taylor and the trustees, in consequence of which all the friends of that gentleman were hostile to the institution. This, together with the smallness of his income, £100 a year and £15 for each boarder, which precluded him from making any provision for his family, induced him to accept an invitation to take charge of Mill Hill Chapel at Leeds, where he had a considerable acquaintance, and to which he removed in 1767. Here he engaged keenly in the study of theology, and produced a great number of works, many of them controversial. Here, too, he commenced his great chemical career, and published his first tract on air. He was led accidentally to think of pneumatic chemistry by living in the immediate vicinity of a brewery. Here, too, he published his history of the discoveries relative to light and colours, as the first part of a general history of experimental philosophy. But the expense of this book was so great, and its sale so limited, that he did not venture to prosecute the undertaking. Here, likewise, he commenced and published 3 volumes of a periodical work entitled The Theological Repository, which he continued after he settled in Birmingham. After he had been 6 years at Leeds, the Earl of Shelbourne, afterwards Marquis of Lansdowne, engaged him, on the recommendation of Dr. Price, to live with him as a kind of librarian and literary companion, at a salary of £250 a year, with a house. With his lordship he travelled through Holland, France, and a part of Germany, and spent some time in Paris. He was delighted with this excursion, and expressed himself thoroughly convinced of the great advantages to be derived from foreign travel. The men of science and politicians in Paris were unbelievers, and even professed atheists, and as Dr. Priestley chose to appear before them as a Christian, they told him that he was the first person they had met with, of whose understanding they had any opinion, who was a believer of Christianity. But upon interrogating them closely, he found that none of them had any knowledge either of the nature or principles of the Christian religion. While with Lord Shelbourne, he published the first 3 volumes of his Experiments on Air, and had collected materials for a 4th, which he published soon after settling in Birmingham. At this time also he published his attack upon Doctors Reed, Beattie, and Oswald, a book which he tells us he finished in a fortnight, but of which he afterwards in some measure disapproved. Indeed, it was impossible for any person of candour to approve of the style of that work and the way in which he treated Dr. Reed, a philosopher certainly much more deeply skilled than himself in metaphysics. After some years, Lord Shelbourne began to be weary of his associate, and on his expressing a wish to settle him in Ireland, Dr. Priestley, of his own accord, proposed a separation, to which his lordship consented, after settling on him an annuity of £150, according to a previous stipulation. This annuity he continued regularly to pay during the remainder of the life of Dr. Priestley. His income being much diminished by his separation from Lord Shelbourne, and his family increasing, he found it now difficult to support himself. At this time, Mrs. Rayner made him very considerable presents, particularly at one period a sum of £400, and she continued her contributions to him almost annually. Dr. Fothergill had proposed a subscription, in order that he might prosecute his experiments to their utmost extent, and be enabled to live without sacrificing his time to his pupils. This he accepted. It amounted at first to £40 per annum, and was afterwards much increased. Dr. Watson, Mr. Wedgwood, Mr. Galton, and 4 or 5 more were the gentlemen who joined with Dr. Fothergill in this generous subscription. Soon after, he settled in a meeting-house in Birmingham, and continued for several years engaged in theological and chemical investigations. His apparatus, by the liberality of his friends, had become excellent, and his income was so good that he could prosecute his researches to their full extent. Here he published the last 3 volumes of his Experiments on Air, and various papers on the same subject in the Philosophical Transactions. Here too he continued his theological repository, and published a variety of tracts on his peculiar opinions in religion, and upon the history of the primitive church. He now, unluckily, engaged in controversy with the established clergy of the place, and expressed his opinions on political subjects with a degree of freedom which, though it would have been of no consequence at any former period, was ill-suited to the peculiar circumstances that were introduced into this country by the French Revolution, and to the political maxims of Mr. Pitt and his administration. His answers to Mr. Burke's book on the French Revolution excited the violent indignation of that extraordinary man, who inveighed against his character repeatedly and with peculiar virulence in the House of Commons. The clergy of the Church of England, too, who began about this time to be alarmed for their establishment, of which Dr. Priestley was the open enemy, were particularly active. The press teemed with their productions against him, and the minds of their hearers seem to have been artificially excited. Indeed, some of the anecdotes told of the conduct of the clergy of Birmingham were highly unbecoming their character. Unfortunately, Dr. Priestley did not seem to be aware of the state of the nation, and of the plan of conduct laid down by Mr. Pitt and his political friends, and he was too fond of controversial discussions to yield tamely to the attacks of his antagonists. These circumstances seem in some measure to explain the disgraceful riots which took place in Birmingham in 1791, on the day of the anniversary of the French Revolution. Dr. Priestley's meeting-house and his dwelling-house were burnt, his library and apparatus destroyed, and many manuscripts, the fruits of several years of industry, were consumed in the conflagration. The houses of several of his friends shared the same fate, and his son narrowly escaped death by the care of a friend who forcibly concealed him for several days. Dr. Priestley was obliged to make his escape to London, and a seat was taken for him in the mail coach under a borrowed name. Such was the ferment against him that it was believed he would not have been safe anywhere else, and his friends would not allow him for several weeks to walk through the streets. He was invited to Hackney to succeed Dr. Price in the meeting-house of that place. He accepted the office, but such was the dread of his unpopularity that nobody would let him a house, from an apprehension that it would be burnt by the populace as soon as it was known that he inhabited it. He was obliged to get a friend to take a lease of a house in another name, and it was with the utmost difficulty that he could prevail with the landlord to allow the lease to be transferred to him. The members of the Royal Society, of which he was a fellow, declined admitting him into their company, and he was obliged to withdraw his name from the society. When we look back upon this treatment of a man of Dr. Priestley's character, after an interval of 40 years, it cannot fail to strike us with astonishment, and it must be owned, I think, that it reflects an indelible stain upon that period of the history of Great Britain. To suppose that he was in the least degree formidable to so powerful a body as the Church of England, backed as it was by the aristocracy, by the ministry, and by the opinions of the people, is perfectly ridiculous. His theological sentiments, indeed, were very different from those of an established church, but so were those of Milton, Locke, and Newton. Nay, some of the members of the church itself entertained opinions not indeed so decided or so openly expressed as those of Dr. Priestley, but certainly having the same tendency. To be satisfied of this, it is only necessary to recollect the book which Dr. Clarke published on the Trinity. Nay, some of the bishops, unless they are very much belied, entertained opinions similar to those of Dr. Clarke. The same observation applies to Dr. Lardner, Dr. Price, and many others of the dissenters. Yet the Church of England never attempted to persecute these respectable and meritorious men, nor did they consider their opinions at all likely to endanger the stability of the Church. Besides, Dr. Horsley had taken up the pen against Dr. Priestley's theological opinions, and had refuted them so completely, in the opinion of the members of the Church, that it was thought right to reward his meritorious services by a bishopric. It could hardly, therefore, be the dread of Dr. Priestley's theological opinions that induced the clergy of the Church of England to bestir themselves against him with such alacrity. Erroneous opinions, advanced and refuted, so far from being injurious, have a powerful tendency to support and strengthen the cause which they were meant to overturn. Or, if there existed any latent suspicion that the refutation of Horsley was not so complete as had been alleged, surely persecution was not the best means of supporting weak arguments, and indeed it was rather calculated to draw the attention of mankind to the theological opinions of Priestley, as has in fact been the consequence. Neither can the persecutions which Dr. Priestley was subjected to be accounted for by his political opinions, even supposing it not to be true that, in a free country like Great Britain, any man is at liberty to maintain whatever theoretic opinions of government he thinks proper, provided he be a peaceable subject, and obey rigorously all the laws of his country. Dr. Priestley was an advocate for the perfectibility of the human species, or at least its continually increasing tendency to improvement, a doctrine extremely pleasing in itself and warmly supported by Franklin and Price, but which the wild principles of Condorcet, Godwin, and Beddoes at last brought into discredit. This doctrine was taught by Priestley in the outset of his Treatise on Civil Government, first published in 1768. It is a speculation of so very agreeable a nature, so congenial to our warmest wishes, and so flattering to the prejudices of humanity, that one feels much pain at being obliged to give it up. Perhaps it may be true, and I am willing to hope so, that improvements once made are never entirely lost, unless they are superseded by something much more advantageous, and that therefore the knowledge of the human race, upon the whole, is progressive. But political establishments, at least if we are to judge from the past history of mankind, have their uniform periods of progress and decay. Nations seem incapable of profiting by experience. Every nation seems destined to run the same career, and the history may be comprehended under the following heads: poverty, liberty, industry, wealth, power, dissipation, anarchy, destruction. We have no example in history of a nation running through this career and again recovering its energy and importance. Greece ran through it more than 2,000 years ago. She has been in a state of slavery ever since. An opportunity is now at last given her of recovering her importance. Posterity will ascertain whether she will embrace it. Dr. Priestley's short Essay on the First Principles of Civil Government was published in 1768. In it he lays down as the foundation of his reasoning that it must be understood, whether it be expressed or not, that all people live in society for their mutual advantage, so that the good and happiness of the members, that is, the majority of the members, of any state, is the great standard by which everything relating to that state must be finally determined. And though it may be supposed that a body of people may be bound by a voluntary resignation of all their rights to a single person or to a few, it can never be supposed that the resignation is obligatory on their posterity, because it is manifestly contrary to the good of the whole that it should be so. From this first principle he deduces all his political maxims. Kings, senators, and nobles are merely the servants of the public, and when they abuse their power, in the people lies the right of deposing and consequently of punishing them. He examines the expediency of hereditary sovereignty, of hereditary rank and privileges, of the duration of Parliament, and of the right of voting, with an evident tendency to democratical principles, though he does not express himself very clearly on the subject. Such were his political principles in 1768, when his book was published. They excited no alarm, and drew but little attention. These principles he maintained ever after, or indeed he may be said to have become more moderate instead of violent. Though he approved of a republic in the abstract, yet, considering the prejudices and habits of the people of Great Britain, he laid it down as a principle that their present form of government was best suited to them. He thought, however, that there should be a reform in Parliament, and that parliaments should be triennial instead of septennial. He was an enemy to all violent reforms, and thought that the change ought to be brought about gradually and peaceably. When the French Revolution broke out, he took the side of the patriots, as he had done during the American War, and he wrote a refutation of Mr. Burke's extraordinary performance. Being a dissenter, it is needless to say that he was an advocate for complete religious freedom. He was ever hostile to all religious establishments, and an open enemy to the Church of England. The end of section 37. Section 38 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 1, Part 2. By all accounts, his powers of conversation were very great, and his manners in every respect very agreeable. That this must have been the case is obvious from the great number of his friends, and the zeal and ardour with which they continued to serve him, notwithstanding the obloquy under which he lay, and even the danger that might be incurred by appearing to befriend him. As for his moral character, even his worst enemies have been obliged to allow that it was unexceptionable. Many of my readers will perhaps smile when I say that he was not only a sincere but a zealous Christian, and would willingly have died a martyr to the cause. Yet I think the fact is of easy proof, and his conduct through life, and especially at his death, affords irrefragable proofs of it. His tenets, indeed, did not coincide with those of the majority of his countrymen, but though he rejected many of the doctrines, he admitted the whole of the sublime morality and the divine origin of the Christian religion, which may charitably be deemed sufficient to constitute a true Christian. Of vanity he seems to have possessed rather more than a usual share, but perhaps he was deficient in pride. His writings were exceedingly numerous, and treated of science, theology, metaphysics, and politics. Of his theological, metaphysical, and political writings, it is not our business in this work to take any notice. His scientific works treat of electricity, optics, and chemistry. As an electrician he was respectable, as an optician, a compiler, as a chemist, a discoverer. He wrote also a book on perspective, which I have never had an opportunity of perusing. It is to his chemical labours that he is chiefly indebted for the great reputation which he acquired. No man ever entered upon any undertaking with less apparent means of success than Dr. Priestley did on the chemical investigation of airs. He was unacquainted with chemistry, excepting that he had, some years before, attended an elementary course delivered by Mr. Turner of Liverpool. He was not in possession of any apparatus, nor acquainted with the method of making chemical experiments, and his circumstances were such that he could neither lay out a great deal of money on experiments, nor could he hope without a great deal of expense to make any material progress in his investigations. These circumstances, which at first sight seem so adverse, were, I believe, of considerable service to him, and contributed very much to his ultimate success. The branch of chemistry which he selected was new. An apparatus was to be invented before anything of importance could be effected, and as simplicity is essential in every apparatus, he was most likely to contrive the best, whose circumstances obliged him to attend to economical considerations. Pneumatic chemistry had been begun by Mr. Cavendish in his valuable paper on carbonic acid and hydrogen gases, published in the Philosophical Transactions for 1766. The apparatus which he employed was similar to that used about a century before by Dr. Mayo of Oxford. Dr. Priestley contrived the apparatus still used by chemists in pneumatic investigations. It is greatly superior to that of Mr. Cavendish, and indeed as convenient as can be desired. Were we indebted to him for nothing else than this apparatus, it would deservedly give him high consideration as a pneumatic chemist. His discoveries in pneumatic chemistry are so numerous that I must satisfy myself with a bare outline. To enumerate everything would be to transcribe his 3 volumes, into which he digested his discoveries. His first paper was published in 1772, and was on the method of impregnating water with carbonic acid gas. The experiments contained in it were the consequence of his residing near a brewery in Leeds. This pamphlet was immediately translated into French, and at a meeting of the College of Physicians in London, they addressed the Lords of the Treasury, pointing out the advantage that might result from water impregnated with carbonic acid gas in cases of scurvy at sea. His next essay was published in the Philosophical Transactions, and procured him the Coplyan Medal. His different volumes on air were published in succession, while he lived with Lord Shelburne, and while he was settled at Birmingham. They drew the attention of all Europe, and raised the reputation of this country to a great height. The first of his discoveries was nitrous gas, now called deutoxide of azote, which had indeed been formed by Dr. Hales, but that philosopher had not attempted to investigate its properties. Dr. Priestley ascertained its properties with much sagacity, and almost immediately applied it to the analysis of air. It contributed very much to all subsequent investigations in pneumatic chemistry, and may be said to have led to our present knowledge of the constitution of the atmosphere. The next great discovery was oxygen gas, which was made by him on the 1st of August 1774, by heating the red oxide of mercury and collecting the gaseous matter given out by it. He almost immediately detected the remarkable property which this gas has of supporting combustion better and animal life longer than the same volume of common air, and likewise the property which it has of condensing into red fumes when mixed with nitrous gas. Lavoisier likewise laid claim to the discovery of oxygen gas, but his claim is entitled to no attention whatever, as Dr. Priestley informs us that he prepared this gas in Monsieur Lavoisier's house in Paris, and showed him the method of procuring it in the year 1774, which is a considerable time before the date assigned by Lavoisier for his pretended discovery. Scheele, however, actually obtained this gas without any previous knowledge of what Priestley had done, but the book containing this discovery was not published till 3 years after Priestley's process had become known to the public. Dr. Priestley first made known sulphurous acid, fluosilicic acid, muriatic acid, and ammonia in the gaseous form, and pointed out easy methods of procuring them. He describes with exactness the most remarkable properties of each. He likewise pointed out the existence of carburetted hydrogen gas, though he made but few experiments to determine its nature. His discovery of protoxide of azote affords a beautiful example of the advantages resulting from his method of investigation, and the sagacity which enabled him to follow out any remarkable appearances which occurred. Carbonic oxide gas was discovered by him while in America, and it was brought forward by him as an incontrovertible refutation of the antiphlogistic theory. Though he was not strictly the discoverer of hydrogen gas, yet his experiments on it were highly interesting, and contributed essentially to the revolution which chemistry soon after underwent. Nothing, for example, could be more striking than the reduction of oxide of iron, and the disappearance of the hydrogen when the oxide is heated sufficiently in contact with hydrogen gas. Azotic gas was known before he began his career, but we are indebted to him for most of the properties of it yet known. To him also we owe the knowledge of the fact that an acid is formed when electric sparks are made to pass for some time through a given bulk of common air, a fact which led afterwards to Mr. Cavendish's great discovery of the composition of nitric acid. He first discovered the great increase of bulk which takes place when electric sparks are made to pass through ammoniacal gas, a fact which led Berthollet to the analysis of this gas. He merely repeated Priestley's experiment, determined the augmentation of bulk and the nature of the gases evolved by the action of the electricity. His experiments on the amelioration of atmospherical air by the vegetation of plants, on the oxygen gas given out by their leaves, and on the respiration of animals, are not less curious and interesting. Such is a short view of the most material facts for which chemistry is indebted to Dr. Priestley. As a discoverer of new substances, his name must always stand very high in the science, but as a reasoner or theorist, his position will not be so favourable. It will be observed that almost all his researches and discoveries related to gaseous bodies. He determined the different processes by means of which the different gases can be procured, the substances which yield them, and the effects which they are capable of producing on other bodies. Of the other departments of chemistry he could hardly be said to know anything. As a pneumatic chemist he stands high. As an analytical chemist he can scarcely claim any rank whatever. In his famous experiments on the formation of water by detonating mixtures of oxygen and hydrogen in a copper globe, the copper was found acted upon, and a blue liquid was obtained, the nature of which he was unable to ascertain. But Mr. Keir, whose assistance he solicited, determined it to be a solution of nitrate of copper in water. This formation of nitric acid induced him to deny that water was a compound of oxygen and hydrogen. The same acid was formed in the experiments of Mr. Cavendish, but he investigated the circumstances of the formation, and showed that it depended upon the presence of azotic gas in the gaseous mixture. Whenever azotic gas is present, nitric acid is formed, and the quantity of this acid depends upon the relative proportion of the azotic and hydrogen gases in the mixture. When no hydrogen gas is present, nothing is formed but nitric acid. When no azotic gas is present, nothing is formed but water. These facts, determined by Cavendish, invalidate the reasoning of Priestley altogether, and had he possessed the skill, like Cavendish, to determine with sufficient accuracy the proportions of the different gases in his mixtures, and the relative quantities of nitric acid formed, he would have seen the inaccuracy of his own conclusions. He was a firm believer in the existence of phlogiston, but he seems at least ultimately to have adopted the view of Scheele and many other eminent contemporary chemists, indeed the view of Cavendish himself, that hydrogen gas is phlogiston in a separate and pure state. Common air he considered as a compound of oxygen and phlogiston. Oxygen, in his opinion, was air quite free from phlogiston, or air in a simple and pure state, while azotic gas, the other constituent of common air, was air saturated with phlogiston. Hence he called oxygen dephlogisticated and azote phlogisticated air. The facts that when common air is converted into azotic gas its bulk is diminished about 1/5 part, and that azotic gas is lighter than common air or oxygen gas, though not quite unknown to him, do not seem to have drawn much of his attention. He was not accustomed to use a balance in his experiments, nor to attend much to the alterations which took place in the weight of bodies. Had he done so, most of his theoretical opinions would have fallen to the ground. When a body is allowed to burn in a given quantity of common air, it is known that the quality of the common air is deteriorated, it becomes, in his language, more phlogisticated. This, in his opinion, was owing to an affinity which existed between phlogiston and air. The presence of air is necessary to combustion, in consequence of the affinity which it has for phlogiston. It draws phlogiston out of the burning body in order to combine with it. When a given bulk of air is saturated with phlogiston, it is converted into azotic gas, or phlogisticated air, as he called it. And this air, having no longer any affinity for phlogiston, can no longer attract that principle, and consequently combustion cannot go on in such air. All combustible bodies, in his opinion, contain hydrogen. Of course, the metals contain it as a constituent. The calces of metals are those bodies deprived of phlogiston. To prove the truth of this opinion, he showed that when the oxide of iron is heated in hydrogen gas, that gas is absorbed, while the calx is reduced to the metallic state. Finery cinder, which he employed in these experiments, is, in his opinion, iron not quite free from phlogiston. Hence it still retains a quantity of hydrogen. To prove this, he mixed together finery cinder and carbonates of lime, barytes, and strontian, and exposed the mixture to a strong heat, and by this process obtained inflammable gas in abundance. In his opinion, every inflammable gas contains hydrogen in abundance. Hence, this experiment was adduced by him as a demonstration that hydrogen is a constituent of finery cinder. All these processes of reasoning, which appear so plausible as Dr. Priestley states them, vanish into nothing when his experiments are made and the weights of everything determined by means of a balance. It is then established that a burning body becomes heavier during its combustion, and that the surrounding air loses just as much weight as the burning body gains. Scheele and Lavoisier showed clearly that the loss of weight sustained by the air is owing to a quantity of oxygen absorbed from it and condensed in the burning body. Cruikshank first elucidated the nature of the inflammable gas produced by the heating of a mixture of finery cinder and carbonate of lime, or other earthy carbonate. He found that iron filings would answer better than finery cinder. The gas was found to contain no hydrogen, and to be in fact a compound of oxygen and carbon. It was shown to be derived from the carbonic acid of the earthy carbonate, which was deprived of half its oxygen by the iron filings or finery cinder. Thus altered, it no longer preserved its affinity for the lime, but made its escape in the gaseous form, constituting the gas now known by the name of carbonic oxide. Though the consequence of the Birmingham riots, which obliged Dr. Priestley to leave England and repair to America, is deeply to be lamented, as fixing an indelible disgrace upon the country, perhaps it was not in reality so injurious to Dr. Priestley as may at first sight appear. He had carried his peculiar researches nearly as far as they could go. To arrange and methodize and deduce from them the legitimate consequences required the application of a different branch of chemical science, which he had not cultivated, and which his characteristic rapidity and the time of life to which he had arrived would have rendered it almost impossible for him to acquire. In all probability, therefore, had he been allowed to prosecute his researches unmolested, his reputation, instead of an increase, might have suffered a diminution, and he might have lost that eminent situation as a man of science, which he had so long occupied. With Dr. Priestley closes this period of the history of British chemistry, for Mr. Cavendish, though he had not lost his activity, had abandoned that branch of science and turned his attention to other pursuits. The end of section 38.
Section 39 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 2. Of the Progress of Philosophical Chemistry in Sweden, Part 1. Of the Progress of Philosophical Chemistry in Sweden. Though Sweden, partly in consequence of her scanty population, and the consequent limited sale of books in that country, and partly from the propensity of her writers to imitate the French, which has prevented that originality in her poets and historians that is requisite for acquiring much eminence, though Sweden, for these reasons, has never reached a very high rank in literature, yet the case has been very different in science. She has produced men of the very first eminence, and has contributed more than her full share in almost every department of science, and none has she shown with greater luster than in the department of chemistry. Even in the latter part of the 17th century, before chemistry had, properly speaking, assumed the rank of a science, we find Keren in Sweden, whose name deserves to be mentioned with respect. Moreover, in the earlier part of the 18th century, Brandt, Scheffer, and Wallerius had distinguished themselves by their writings. Cronstedt, about the middle of the 18th century, may be said to have laid the foundation of systematic mineralogy upon chemical principles by the publication of his System of Mineralogy. But Bergman is entitled to the merit of being the first person who prosecuted chemistry in Sweden on truly philosophical principles, and raised it to that high estimation to which its importance justly entitles it. Torbern Bergman was born in Catherinburg in West Gothland on the 20th of March, 1735. His father, Barthold Bergman, was receiver of the revenues of that district, and his mother, Sarah Hägg, the daughter of a Gothenburg merchant. A receiver of the revenues was at that time, in Sweden, a post both disagreeable and hazardous. The creatures of a party which had the ascendancy in one diet, they were exposed to the persecution of the diet next following, in which an opposite party usually had the predominance. This circumstance induced Bergman to advise his son to turn his attention to the professions of law or divinity, which were at that time the most lucrative in Sweden. After having spent the usual time at school, and acquired those branches of learning commonly taught in Sweden, in the public schools and academies to which Bergman was sent, he went to the University of Uppsala in the autumn of 1752, where he was placed under the guidance of a relation, whose province it was to superintend his studies, and direct them to those pursuits that were likely to lead young Bergman to wealth and distinction. Our young student showed at once a decided predilection for mathematics, and those branches of physics which were connected with mathematics, or depended upon them. But these were precisely the branches of study which his relation was anxious to prevent his indulging in. Bergman attempted at once to indulge his own inclination, and to gratify the wishes of his relation. This obliged him to study with a degree of ardor and perseverance which has few examples. His mathematical and physical studies claimed the first share of his attention, and after having made such progress in them as would alone have been sufficient to occupy the whole time of an ordinary student, to satisfy his relation, Jonas Victorin, who was at that time a magister docens in Uppsala, he thought it requisite to study some law books besides, that he might be able to show that he had not neglected his advice, nor abandoned the views which he had held out. He was in the habit of rising to his studies every morning at 4 o'clock, and he never went to bed till 11 at night. The first year of his residence at Uppsala, he had made himself master of Wolff's Logic, of Wallerius's System of Chemistry, and of 12 books of Euclid's Elements, for he had already studied the first book of that work in the gymnasium before he went to college. He likewise perused Keil's lectures on astronomy, which at that time were considered as the best introduction to physics and astronomy. His relative disapproved of his mathematical and physical studies altogether, but not being able to put a stop to them, he interdicted the books and left his young charge merely the choice between law and divinity. Bergman got a small box made, with a drawer, into which he put his mathematical and physical books, and over this box he piled the law books which his relative had urged him to study. At the time of the daily visits of his relative, the mathematical and physical books were carefully locked up in the drawer, and the law books spread upon the table. But no sooner was his presence removed than the drawer was opened, and the mathematical studies resumed. This incessant study, this necessity under which he found himself to consult his own inclinations and those of his relatives, this double portion of labor, without time for relaxation, exercise, or amusement, proved at last injurious to young Bergman's health. He fell ill and was obliged to leave the university and return home to his father's house in a state of bad health. There constant and moderate exercise was prescribed him as the only means of restoring his health. That his time here might not be altogether lost to him, he formed the plan of making his walks subservient to the study of botany and entomology. At this time, Linnaeus, after having surmounted obstacles which would have crushed a man of ordinary energy, was in the height of his glory, and was a professor of botany and natural history in the University of Uppsala. His lectures were attended by crowds of students from every country in Europe. He was enthusiastically admired and adored by his students. This influence on the minds of his pupils was almost unbounded, and at Uppsala every student was a natural historian. Bergman had studied botany before he went to college, and he had acquired a taste for entomology from the lectures of Linnaeus himself. Both of these pursuits he continued to follow after his return home to West Gothland, and he made a collection of plants and of insects. Grasses and mosses were the plants to which he turned the most of his attention, and of which he collected the greatest number. But he felt a predilection for the study of insects, which was a field much less explored than the study of plants. Among the insects which he collected were several not to be found in the fauna suecica. Of these he sent specimens to Linnaeus at Uppsala, who was delighted with the present. All of them were till then unknown as Swedish insects, and several of them were quite new. The following were the insects at this time collected by Bergman, and sent to Uppsala, as they were named by Linnaeus: Felina, Bombyx monaca, camelina, Noxua parthenius, conspicularis, perspicularis, flavicornis, Polybia, Geometra panaria, Tortix burnamania, Lediana, Tinea harrisella, Pedella, punctella, Tenthredo, Vitellina ustulata, Ichneumon, Jaculator niger, Tipula, Tremula. When Bergman's health was re-established, he returned to Uppsala with full liberty to prosecute his studies according to his own wishes, and to devote the whole of his time to mathematics, physics, and natural history. His relations, finding it in vain to combat his predilections for these studies, thought it better to allow him to indulge them. He had made himself known to Linnaeus by the collection of insects which he had sent him from Catherineburg, and drawn along by the glory with which Linnaeus was surrounded, and the zeal with which his fellow students prosecuted such studies, he devoted a great deal of his attention to natural history. The first paper which he wrote upon the subject contained a discovery. There was a substance observed in some ponds not far from Uppsala, to which the name Coccus aquaticus was given, but its nature was unknown. Linnaeus had conjectured that it might be the ovarium of some insect, but he left the point to be determined by future observations. Bergman ascertained that it was the ovum of a species of leech, and that it contained from 10 to 12 young animals. When he stated what he had ascertained to Linnaeus, that great naturalist refused to believe it, but Bergman satisfied him the truth of his discovery by actual observation. Linnaeus, thus satisfied, wrote under the paper of Bergman, Vidi et obstupui, and sent it to the Academy of Stockholm with this flattering panegyric. It was printed in the Memoirs of that learned body for 1756, page 199, and was the first paper of Bergman's that was committed to the press. He continued to prosecute the study of natural history as an amusement, though mathematics and natural philosophy occupied by far the greatest part of his time. Various useful papers of his, connected with entomology, appeared from time to time in the memoirs of the Stockholm Academy, in particular a paper on the history of insects, which attacked fruit trees, and on the methods of guarding against their ravages, on the method of classing these insects from the forms of their larvae, a time when it would be most useful for the agriculturalist to know in order to destroy those that are hurtful. A great number of observations on this class of animals, so various in their shape and their organization, and so important for man to know, some of which he has been able to overcome, while others, defended by their small size and powerful by their vast numbers, still continue their ravages, and which offer so interesting a sight to the philosopher by their labors, their manners, and their foresight. Bergman was fond of these pursuits, and looked back upon them in after life with pleasure. Long after, he used to mention with much satisfaction that by the use of the method pointed out to him, no fewer than 7 millions of destructive insects were destroyed in a single garden, and during the course of a single summer. About the year 1757, he was appointed tutor to the only son of Count Adolf Frederick Stackelberg, a situation which he filled greatly to the satisfaction both of the father and son, as long as the young count stood in need of an instructor. He took his master's degree in 1758, choosing for the subject of his thesis an astronomical interpolation. Soon after, he was appointed magister docens in natural philosophy, a situation peculiar to the University of Upsala, and constituting a kind of assistant to the professor. For his promotion to this situation, he was obliged to M. Ferner, who saw how well qualified he was for it, and how beneficial his labors would be to the University of Upsala. In 1761, he was appointed adjunct in mathematics and physics, which, I presume, means he was raised to the rank of an associate with the professor of these branches of science. In this situation, it was his business to teach these sciences to the students of Upsala, a task for which he was exceedingly well fitted. During this period, he published various tracts on different branches of physical science, particularly on the rainbow, the crepuscula, the aurora borealis, the electrical phenomena of Iceland spar, and of the tourmaline. We find his name among the astronomers who observed the first transit of Venus over the sun in 1761, whose results deserve the greatest confidence. His observations on the electricity of the tourmaline are important. It was he that first established the true laws that regulate these curious phenomena. During the whole of this period he had been silently studying chemistry and mineralogy, though nobody suspected that he was engaged in any such pursuits. But in 1767, John Gottschalk Wallerius, who had long filled the chair of chemistry in the University of Upsala, with high reputation, resigned his chair. Bergman immediately offered himself as a candidate for the vacant professorship, and to show that he was qualified for the office, published 2 dissertations on the manufacture of alum, which probably he had previously drawn up and had lying by him. Wallerius intended to resign his chair in favor of a pupil or relation of his own, whom he had destined to succeed him. He immediately formed a party to oppose the pretensions of Bergman, and his party was so powerful and so malignant that few doubted of their success, for it was joined by all those who, despairing of equaling the industry and reputation of Bergman, set themselves to oppose and obstruct his success. Such men unhappily exist in all colleges, and the more eminent a professor is, the more he is exposed to their malignant activity. Many of those who cannot themselves rise to any eminence derive pleasure from the attempt to pull down the eminent to their own level. In these attempts, however, they seldom succeed, unless some form of want of prudence and steadiness in the individual whom they assail. Bergman's dissertations on alum were severely handled by Wallerius and his party, and such was the influence of the ex-professor that everybody thought Bergman would be crushed by him. Fortunately, Gustavus III of Sweden, at that time Crown Prince, was Chancellor of the University. He took up the cause of Bergman, influenced, it is said, by the recommendation of von Schwab, who pledged himself for his qualifications, and was so keen on the subject that he pleaded his cause in person before the Senate. Wallerius and his party were of course baffled, and Bergman got the chair. For this situation, his previous studies had fitted him in a peculiar manner. His mathematical, physical, and natural historical knowledge, so far from being useless, contributed to free him from prejudices, and to emancipate him from that spirit of routine under which chemistry had hitherto suffered. They gave to his ideas a greater degree of precision, and made his views more correct. He saw that mathematics and chemistry divided between them the whole extent of natural science, and that its bounds required to be enlarged, to enable it to embrace all the different branches of science with which it was naturally connected, or which depended upon it. He saw the necessity of banishing from chemistry all vague hypotheses and explanations, and of establishing the science on the firm basis of experiment. He was equally convinced of the necessity of reforming the nomenclature of chemistry, and of bringing it to the same degree of precision that characterized the language of the other branches of natural philosophy. His first care, after getting the chair, was to make as complete a collection as he could of mineral substances, and to arrange them in order according to the nature of their constituents, as far as they had been determined by experiment. To another cabinet he assigned the Swedish minerals, ranged in a geographical manner according to the different provinces which furnished them. When I was at Uppsala in 1812, the first of these collections still remained, greatly augmented by his nephew and successor, Alphelius. But no remains existed of the geographical collection. However, there was a very considerable collection of this kind in the apartments of the Swedish School of Mines at Stockholm, under the care of Mr. Hjelm, which I had an opportunity of inspecting. It is not improbable that Bergman's collection might have formed the nucleus of this. A geographical collection of minerals, to be of much utility, should exhibit all the different formations which exist in the kingdom. And in a country so uniform in its nature as Sweden, the minerals of one county are very nearly similar to those of other counties, with the exception of certain peculiarities derived from the mines, or from some formations which may belong exclusively to certain parts of the country, as, for example, the coal formations of the south corner of Sweden, near Helensburgh, and the porphyry rocks in Elfsdale. Bergman attempted also to make a collection of models of the apparatus employed in the different chemical manufactories, to be enabled to explain these manufactures with greater clearness to his students. I was informed by M. Ekberg, who in 1812 was Magister Docens in chemistry at Uppsala, that these models were never numerous. Nor is it likely that they should be, as Sweden cannot boast any great number of chemical manufactories, and as in Bergman's time, the processes followed in most of the chemical manufactories of Europe were kept as secret as possible. Thus it was Bergman's object to exhibit to his pupils specimens of all the different substances which the earth furnishes, with the order in which these productions are arranged on the globe, to show them the uses made of all these different productions, how practice had preceded theory, and had succeeded in solving many chemical problems of the most complicated nature. His lectures are said to have been particularly valuable. He drew around him a considerable number of pupils, who afterwards figured as chemical discoverers themselves. Of all these, Assessor Gahn of Falun was undoubtedly the most remarkable, but Hjelm, Gadelin, the Uliarts, and various other individuals likewise distinguished themselves as chemists. After his appointment to the chemical chair at Uppsala, the remainder of his life passed with very little variety. His whole time was occupied with his favorite studies, and not a year passed that he did not publish some dissertation or other upon some more or less important branch of chemistry. His reputation gradually extended itself over Europe, and he was enrolled among the number of the members of most scientific academies. Among other honorable testimonies of the esteem in which he was held, he was elected rector of the University of Uppsala. This university is not merely a literary body, but owns extensive estates, over which it possesses great authority, and having considerable control over its students, and enjoying considerable immunities and privileges, conferred in former times as an encouragement to learning, though in reality they serve only to cramp its energies, and throw barriers in the way of its progress. Constitutes, therefore, a kind of republic in the midst of Sweden, the professors being its chiefs. But while in literary establishments all the institutions ought to have for an object to maintain peace and free their members from every occupation unconnected with letters, the constitution of that university obliges its professors to attend to things very inconsistent with their usual functions. While it gives men of influence and ambition a desire to possess the power and patronage, though they may not be qualified to perform the duties of a professor. Such temptations are very injurious to the true cause of science, and it were to be wished that no literary body, in any part of the world, were possessed of such powers and privileges. When Bergman was rector, the university was divided into two great parties, the one consisting of the theological and law faculties, and the other of the scientific professors. Bergman's object was to preserve peace and agreement between these two parties, and to convince them that it was the interest of all to unite for the good of the university and the promotion of letters. The period of his magistracy is remarkable in the annals of the university for the small number of deliberations, and the little business recorded in the registers, and for the good sense and good behavior of the students. The students in Uppsala are numerous, and most of them are young men. They had been accustomed frequently to brave or elude the severity of regulations, but during Bergman's rectorship they were restrained effectually by their respect for his genius and their admiration of his character and conduct. End of section 39. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 40 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 2. Of the Progress of Philosophical Chemistry in Sweden, Part 2. When the reputation of Bergman was at its height, in the year 1776, Frederick the Great of Prussia formed the wish to attach him to the Academy of Sciences of Berlin, and made him offers of such a nature that our professor hesitated for a short time as to whether he ought not to accept them. His health had been injured by the assiduity with which he had devoted himself to the double duty of teaching and experimenting. He might look for an alleviation of his ailments, if not a complete recovery, in the milder climate of Prussia, and he would be able to devote himself entirely to his academical duties. But other considerations prevented him from acceding to this proposal, tempting as it was. The King of Sweden had been his benefactor, and it was intimated to him that his leaving the kingdom would afflict the monarch. This information induced him, without further hesitation, to refuse the proposal of the King of Prussia. He requested of the king, his master, not to make him lose the merit of his sacrifice by augmenting his income, but to this demand the King of Sweden very properly refused to accede. In the year 1771, Professor Bergman married a widow lady, Margaretha Katharina Trast, daughter of a clergyman in the neighborhood of Uppsala. By her he had 2 sons, but both of them died when infants. This lady survived her husband. The King of Sweden settled on her an annuity of 200 rix dollars on condition that she gave up the library and apparatus of her late husband to the Royal Society of Uppsala. Bergman's health had always been delicate. Indeed, he seems never to have completely recovered the effects of his first year's too intense study at Uppsala. He struggled on, however, with his ailments, and by way of relaxation was accustomed, sometimes in summer, to repair to the waters of Medevi, a celebrated mineral spring in Sweden, situated near the banks of the great inland lake, Wetter. One of these visits seems to have restored him to health for the time, but his malady returned in 1784 with redoubled violence. He was afflicted with hemorrhoids, and his daily loss of blood amounted to about 6 ounces. This constant drain soon exhausted him, and on the 8th of July, 1784, he died at the baths of Medevi, to which he had repaired in hopes of again benefiting by these waters. The different tracts which he published, as they have been enumerated by Hjelm, who gave an interesting account of Bergman to the Stockholm Academy in the year 1785, amount to 106. They have been all collected into 6 octavo volumes, entitled Opuscula Turbini Bergman Physica et Chemica. With the exception of his notes on Scheffer, his Sciagraphia, and his chapter on physical geography, which was translated into French and published in the Journal des Mines, Volume 3, No. 15, page 55. His Sciagraphia, which is an attempt to arrange minerals according to their composition, was translated into English by Dr. Withering. His notes on Scheffer were interspersed in an edition of the Chemiska Föreläsningar of that chemist, published in 1774. Which he seems to have employed as a textbook in his lectures, or, at all events, the work was published for the use of the students of chemistry at Uppsala. There was a new edition of it published after Bergman's death in the year 1796, to which are appended Bergman's tables of affinities. The most important of Bergman's chemical papers were collected by himself, and constitute the 3 first volumes of his Opuscula. The 3 last volumes of that work were published after his death. The 4th volume was published at Leipzig in 1787 by Hebenstreit, and contains the rest of his chemical papers. The 5th volume was given to the world in 1788 by the same editor. It contains 3 chemical papers, and the rest of it is made up with papers on natural history, electricity, and other branches of physics, which Bergman had published in the earlier part of his life. The same indefatigable editor published the 6th volume in 1790. It contains 3 astronomical papers, 2 chemical, and a long paper on the means of preventing any injurious effects from lightning. This was an oration delivered before the Royal Academy of Sciences of Stockholm in 1764, probably at the time of his admission into the Academy. It would serve little purpose in the present state of chemical knowledge to give a minute analysis of Bergman's papers. To judge of their value, it would be necessary to compare them, not with our present chemical knowledge, but with the state of the science when his papers were published. A very short general view of his labors will be sufficient to convey an idea of the benefits which the science derived from them. 1. His first paper, entitled On the Aryl Acid, that is, carbonic acid, was published in 1774. In it he gives the properties of this substance in considerable detail, shows that it possesses acid qualities, and that it is capable of combining with the bases and forming salts. What is very extraordinary, in giving an account of carbonate of lime and carbonate of magnesia, he never mentions the name of Dr. Black, though it is very unlikely that a controversy which had for years occupied the attention of chemists should have been unknown to him. Mr. Cavendish's name never once appears in the whole paper, though that philosopher had preceded him by 7 or 8 years. He informs us that he had made known his opinions respecting the nature of this substance to various foreign correspondents, among others Dr. Priestley, as early as the year 1770, and that Dr. Priestley had mentioned his views on the subject in a paper inserted in the Philosophical Transactions for 1772. Bergman found the specific gravity of carbonic acid gas rather higher than 1.5, that of air being 1. His result is not far from the truth. He obtained his gas by mixing calcareous spar with dilute sulfuric acid. He shows that this gas has a sour taste, that it reddens the infusion of litmus, and that it combines with bases. He gives figures of the apparatus which he used. This apparatus demands attention. Though far inferior to the contrivances of Priestley, it answered pretty well, enabling him to collect the gas and examine its properties. It is unnecessary to enter into any further details respecting this paper. Whoever will take the trouble to compare it with Cavendish's paper on the same subject will find that he had anticipated by that philosopher in a great many of his most important facts. Under these circumstances, I consider as singular his not taking any notice of Cavendish's previous labors. 2. His next paper, on the analysis of mineral waters, was first published in 1778, being the subject of a thesis supported by J.P. Scharenberg. This dissertation, which is of great length, is entitled to much praise. He lays therein the foundation of the mode of analyzing waters, such as is followed at present. He points out the use of different regions for detecting the presence of the various constituents in mineral water, and then shows how the quantity of each is to be determined. It would be doing great injustice to Bergman to compare his analysis with those of any modern experimenter. At that time, the science was not in possession of any accurate analysis of the neutral salts which exist in mineral waters. Bergman undertook these necessary analyses, without which the determination of the saline constituents of mineral waters was out of the question. His determinations were not indeed accurate, but they were so much better than those that preceded them, and Bergman's character as an experimenter stood so high that they were long referred to as a standard by chemists. The first attempt to correct them was by Keren, but Bergman's superior reputation as a chemist enabled his results still to keep their ground, till his character for accuracy was finally destroyed by the very accurate experiments which the discovery of the atomic theory rendered it necessary to make. These, when once they became generally known, were of course preferred, and Bergman's analyses were laid aside. It is a curious and humiliating fact, as it shows how much chemical reputation depends on situation or accidental circumstances, that Wenzel had, in 1766, in his book on affinity, published much more accurate analysis of all these salts than Bergman's, analyses indeed which were almost perfectly correct, and which have scarcely been surpassed by the most careful ones of the present day. Yet these admirable experiments scarcely drew the attention of chemists, while the very inferior ones of Bergman were held up as models of perfection. 3. Bergman, not satisfied with pointing out the mode of analyzing mineral waters, attempted to imitate them artificially by the chemical processes, and published 2 essays on the subject. In the first, he showed the processes by which cold mineral waters might be imitated, and in the other, the mode of imitating hot mineral waters. The attempt was valuable, and served to extend greatly the chemical knowledge of mineral waters, and of the salts which they contain, but it was made at too early a period of the analytical art to approach perfection. A similar remark applies to his analysis of sea-water. The water examined was brought by Sparman from a depth of 80 fathoms, near the latitude of the Canaries. Bergman found in it only common salt, muriate of magnesia, and sulfate of lime. His not having discovered the presence of sulfate of magnesia is a sufficient proof of the imperfection of his analytical methods. The other constituents exist in such small quantity in sea-water that they might easily have been overlooked, but the quantity of sulfate of magnesia in sea-water is considerable. 4. I shall pass over the paper on oxalic acid, which constituted the subject of a thesis supported in 1776 by John Afzelius Arfvedson. It is now known that oxalic acid was discovered by Scheele, not by Bergman. It is impossible to say how many of the numerous facts stated in this thesis were ascertained by Scheele, and how many by Afzelius. For as Afzelius was already a magister docens in chemistry, there can be little doubt that he would himself ascertain the facts which were to constitute the foundation of his thesis. It is indeed now known that Bergman himself entrusted all the details of his experiments to his pupils. He was the contriver, while his pupils executed his plans. That Scheele has nowhere laid claim to a discovery of so much importance as that of oxalic acid, and that he allowed Bergman peaceably to bear away the whole credit, constitutes one of the most remarkable facts in the history of chemistry. Moreover, while it reflects so much credit on Scheele for modesty and forbearance, it seems to bear a little hard upon the character of Bergman. When he published the essay in his first volume of his Opuscula in 1779, why did he not in a note inform the world that Scheele was the true discoverer of this acid? Why did he allow the discovery to be universally assigned to him, without ever mentioning the true state of the case? All this appeared so contrary to the character of Bergman that I was disposed to doubt the truth of the statement, that Scheele was the discoverer of oxalic acid. When I was at Falun, in the year 1812, I took an opportunity of putting the question to Assessor Gahn, who had been the intimate friend of Scheele, and the pupil, and afterward the friend of Bergman. He assured me that Scheele really was the discoverer of oxalic acid, and ascribed the omission of Bergman to inadvertence. Assessor Gahn showed me a volume of Scheele's letters to him, which he had bound up. They contained the history of all his chemical labours. I have little doubt that an account of oxalic acid would be found in these letters. If the son of Assessor Gahn, in whose possession these letters must now be, would take the trouble to inspect the volume in question, and to publish any notices respecting this acid which they may contain, he would confer an important favour on every person interested in the history of chemistry. 5. The dissertation on the manufacture of alum has been mentioned before. Bergman shows himself well acquainted with the processes followed, at least in Sweden, for making alum. He had no notion of the true constitution of alum, nor was that to be expected, as the discovery was thereby years later in being made. He thought that the reason why alum lays did not crystallize well was that they contained an excess of acid, and that the addition of potash gave them the property of crystallizing readily, merely by saturating that excess of acid. Alum is a double salt, composed of 3 integrant particles of sulfate of alumina, and 1 integrant particle of sulfate of potash, or sulfate of ammonia. In some cases, the alum contains all the requisite ingredients. This is the case with the ore at Tolfa, in the neighbourhood of Rome. It seems also to be the case with respect to some of the alum ores in Sweden, particularly at Honsäter on Konekul in West Gothland, which I visited in 1812. If any confidence can be put in the statements of the manager of those works, no alkaline salt whatever is added. At least I understood him to say so when I put the question. 6. In his dissertation on tartar emetic, he gives an interesting historical account of this salt and its uses. His notions respecting the antimonial preparations best fitted to form it are not accurate, nor indeed could they be expected to be so, till the nature and properties of the different oxides of antimony were accurately known. Antimony forms 3 oxides. Now it is the protoxide alone that is useful in medicine, and that enters into the composition of tartar emetic. The other 2 oxides are inert, or nearly so. Bergman was aware that tartar emetic is a double salt, and that its constituents are tartaric acid, potash, and oxide of antimony. But it was not possible, in 1773, when his dissertation was published, to have determined the true constituents of this salt by analysis. 7. Bergman's paper on magnesia was also a thesis defended in 1775 by Charles Norrell of West Gothland, who in all probability made the experiments described in the essay. In the introduction we have a history of the discovery of magnesia, and he mentions Dr. Black as the first person who accurately made out its peculiar chemical characters, and demonstrated that it differs from lime. This essay contains a pretty full and accurate account of the salts of magnesia, considering the state of chemistry at the time when it was published. There is no attempt to analyze any of the magnesian salts, but in his treatise on the analysis of mineral waters, he had stated the quantity of magnesia contained in 100 parts of several of them. 8. His paper on the shapes of crystals, published in 1773, contains the germ of the whole theory of crystallization afterwards developed by M. Hauy. He shows how, from a very simple primary form of a mineral, other shapes may proceed, which seem to have no connection with or resemblance to the primary form. His view of the subject, so far as it goes, is the very same afterwards adopted by Hauy, and what is very curious, Hauy and Bergman formed their theory from the very same crystalline shape of calcareous spar, from which, by mechanical divisions, the same rhombic nucleus was extracted by both. Nothing prevented Bergman from anticipating Hauy but a sufficient quantity of crystals to apply his theory to. 9. In his paper on silica, he gives us a history of the progress of chemical knowledge respecting this substance. Its nature was first accurately pointed out by Pott, though Glauber, and before him Van Helmont, were acquainted with the liquor silicus, or the combination of silica and potash, which is soluble in water. Bergman gives a detailed account of its properties, but he does not suspect it to possess acid properties. This great discovery, which has thrown a new light upon mineral bodies, and shown them all to be chemical combinations, was reserved for Mr. Smithson. 10. Bergman's experiments on the precious stones constitute the first rudiments of the method of analyzing stony bodies. His processes are very imperfect, and his apparatus but ill adapted to the purpose. We need not be surprised, therefore, that the results of his analysis are extremely wide of the truth. Yet if we study his processes, we shall find in them the rudiments of the very methods which we follow at present. The superiority of the modern analysis over those of Bergman must in a great measure be ascribed to the platinum vessels which we now employ, and to the superior purity of the substances which we use as reagents in our analysis. The methods, too, are simplified and perfected, but we must not forget that this paper of Bergman's, imperfect as it is, constitutes the commencement of the art, and that fully as much genius and invention may be requisite to contrive the first rude processes, how imperfect soever they may be, as are required to bring these processes, when once invented, to a state of comparative perfection. The great step in analyzing minerals is to render them soluble in acids. Bergman first thought of the method for accomplishing this which is still followed, namely, fusing them or heating them to redness with an alkali or alkaline carbonate. End of section 40. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 41 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 2 of The Progress of Philosophical Chemistry in Sweden, Part 3. 11. The paper on fulminating gold goes a great way to explain the nature of that curious compound. He describes the properties of this substance and the effects of alkaline and acid bodies on it. He shows that it cannot be formed without ammonia, and infers from his experiments that it is a compound of oxide of gold and ammonia. He explains the fulmination by the elastic fluid suddenly generated by the decomposition of the ammonia. 12. The papers on platinum, carbonate of iron, nickel, arsenic, and zinc do not require many remarks. They add considerably to the knowledge which chemists at that time possessed of these bodies, though the modes of analysis are not such as would be approved by a modern chemist, nor were the results obtained possessed of much precision. The essay on the analysis of metallic ores by the wet way or by solution constitutes the first attempt to establish a regular method of analyzing metallic ores. The processes are all imperfect, as might be expected from the then existing state of analytical chemistry, and the imperfect knowledge possessed of the different metallic ores. But this essay constituted a first beginning, for which the author is entitled to great praise. The subject was taken up by Klaproth, and speedily brought to a great degree of improvement by the labours of modern chemists. 14. The experiments on the way in which minerals behave before the blowpipe, which Bergman published, were made at Bergman's request by Assessor Gahn of Falun, who was then his pupil. They constitute the first results obtained by that very ingenious and amiable man. He afterwards continued the investigation, and added many improvements, simplifying the reagents and the manner of using them. But he was too indolent a man to commit the results of his investigations to writing. Berzelius, however, had the good sense to see the importance of the facts which Gahn had ascertained. He committed them to writing, and published them for the use of mineralogists. They constitute the book entitled Berzelius on the Blowpipe, which has been translated into English. 15. The object of the essay on metallic precipitates is to determine the quantity of phlogiston which each metal contains, deduced from the quantity of one metal necessary to precipitate a given weight of another. The experiments are obviously made with little accuracy. Indeed, they are not susceptible of very great precision. Lavoisier afterwards made use of the same method to determine the quantity of oxygen in the different metallic oxides, but his results were not more successful than those of Bergman. 16. Bergman's paper on iron is one of the most important in his whole works, and contributed very materially to advance the knowledge of the cause of the difference between iron and steel. He employed his pupils to collect specimens of iron from the different Swedish forges, and gave them directions how to select the proper pieces. All these specimens, to the number of 89, he subjected a chemical examination by dissolving them in dilute sulphuric acid. He measured the volume of hydrogen gas, which he obtained by dissolving a given weight of each, and noted the quantity and the nature of the undissolved residue. The general result of the whole investigation was that pure malleable iron yielded most hydrogen gas, steel less, and cast iron least of all. Pure malleable iron left the smallest quantity of insoluble matter, steel a greater quantity, and cast iron the greatest of all. From these experiments he drew conclusions with respect to the difference between iron, steel, and cast iron. Nothing more was necessary than to apply the antiphlogistic theory to these experiments, as was done soon after by the French chemists, in order to draw important conclusions respecting the nature of these bodies. Iron is a simple body, steel is a compound of iron and carbon, and cast iron of iron and still greater proportion of carbon. The defective part of the experiments of Bergman in this important paper is his method of determining the quantity of manganese in iron. In some specimens he makes the manganese amount to considerably more than a third part of the weight of the whole. Now we know that a mixture of 2 parts iron and 1 part manganese is brittle and useless. We are sure, therefore, that no malleable iron whatever can contain any such proportion of manganese. The fact is that Bergman's mode of separating manganese from iron was defective. What he considered as manganese was chiefly, and might be in many cases altogether, oxide of iron. Many years elapsed before a good process for separating iron from manganese was discovered. 17. Bergman's experiments to ascertain the cause of brittleness of cold short iron need not occupy much of our attention. He extracted from it a white powder by dissolving the cold short iron in dilute sulfuric acid. This white powder he succeeded in reducing to the state of white brittle metal by fusing it with a flux and charcoal. Klaproth soon after ascertained that this metal was a phosphuret of iron, and that the white powder was a phosphate of iron, and Scheele, with his usual sagacity, hit on a method of analyzing this phosphate, and thus demonstrating its nature. Thus Bergman's experiments led to the knowledge of the fact that cold short iron owes its brittleness to a quantity of phosphorus which it contains. It ought to be mentioned that Meyer, of Stettin, ascertained the same fact, and made it known to chemists at about the same time with Bergman. 18. The dissertation on the products of volcanoes, first published in 1777, is one of the most striking examples of the sagacity of Bergman which we possess. He takes a view of all the substances certainly known to have been thrown out of volcanoes, attempts to subject them to chemical analysis, and compares them with the basalt and greenstone or trap rocks, the origin of which constituted at that time a keen matter of dispute among geologists. He shows the identity between lavas and basalt and greenstone, and therefore infers the identity of formation. This is obviously the true mode of proceeding, and had it been adopted at an earlier period, many of those disputes respecting the nature of trap rocks, which occupied geologists for so long a period, would never have been agitated, or at least would have been speedily decided. The whole dissertation is filled with valuable matter, still well entitled to the attention of geologists. His observation on zeolites, which he considered as unconnected with volcanic products, were very natural at the time when he wrote, though the subsequent experiments of Sir James Hall and Mr. Gregory Watt, and above all an accurate attention to the scoriae from different smelting houses, have thrown a new light on the subject, and have shown the way in which zeolitic crystals might easily have been formed in melted lava, provided circumstances were favorable. In fact, we find abundant cavities in real lava from Vesuvius, filled with zeolitic crystals. 19. The last of the labors of Bergman which I shall notice here is his Essay on Elective Attractions, which was originally published in 1775, but was much augmented and improved in the third volume of his Opuscula, published in 1783. An English translation of this last edition of the essay was made by Dr. Beddoes, and was long familiar to the British chemical world. The object of this essay was to elucidate and explain the nature of chemical affinity, and to account for all the apparent anomalies that had been observed. He laid it down as a first principle, that all bodies capable of combining chemically with each other have an attraction for each other, and that this attraction is a definite and fixed force, which may be represented by a number. Now, the bodies which have the property of uniting together are chiefly the acids and alkalis or bases. Every acid has an attraction for each of the alkalis or bases, but the force of this attraction differs in each. Some bases have a strong attraction for acids, others a weak, but the attractive force of each may be expressed by numbers. Now, suppose that an acid A is united with a base M with a certain force. If we mix the compound AM with a certain quantity of the base N, which has a stronger attraction for A than M has, the consequence will be that A will leave M and unite with N. N, having a stronger attraction for A than M has, will disengage it and take its place. In consequence of this property, which Bergman considered as the foundation of the whole of the science, the strength of affinity of one body for another is determined by these decompositions and combinations. If N has a stronger affinity for A than M has, then if we mix together A, M, and N in the requisite proportions, A and N will unite together, leaving M uncombined. Or if we mix N with the compound AM, M will be disengaged. Tables, therefore, may be drawn up, exhibiting the strength of these affinities. At the top of a column is put the name of an acid or a base, and below it are put the names of all the bases or acids in the order of their affinity. The following little table will exhibit a specimen of these columns. Sulfuric acid, barytes, strontian, potash, soda, lime, magnesia. Here, sulfuric acid is the substance placed at the head of the column, and under it are the names of the bases capable of uniting with it in the order of their affinity. Barytes, which is the highest up, has the strongest affinity, and magnesia, which is lowest down, has the weakest affinity. If sulfuric acid and magnesia were combined together, all the bases whose names occur in the table above magnesia would be able to separate the sulfuric acid from it. Potash would be disengaged from sulfuric acid by barytes and strontian, but not by soda, lime, and magnesia. Such tables then exhibited to the eye the strength of affinity of all the different bodies that are capable of uniting with one and the same substance, and the order in which decompositions are effected. Bergman drew up tables of affinity according to these views in 59 columns. Each column contained the name of a particular substance, and under it was arranged all the bodies capable of uniting with it, each in the order of its affinity. Now bodies may be made to unite either by mixing them together and then exposing them to heat, or by dissolving them in water and mixing the respective solutions together. The first of these ways is usually called the dry way, and the second the moist way. The order of decompositions often varies with the mode employed. On this account, Bergman divided each of his 59 columns into two. In the first, he exhibited the order of decompositions in the moist way, in the second, in the dry. He explained also the cases of double decomposition, by means of these unvarying forces acting together or opposing each other, and gave 64 cases of such double decompositions. These views of Bergman's were immediately acceded to by the chemical world, and continued to regulate their processes till Berthollet published his Chemical Statics in 1802. He there called in question the whole doctrine of Bergman, and endeavored to establish one of the very opposite kind. I shall have occasion to return to the subject when I come to give an account of the services which Berthollet conferred upon chemistry. I have already observed that we are under obligations to Bergman, not merely for the improvements which he himself introduced into chemistry, but for the pupils whom he educated as chemists, and the discoveries which were made by these persons, whose exertions he stimulated and encouraged. Among those individuals whose chemical discoveries were chiefly made known to the world by his means was Scheele, certainly one of the most extraordinary men and most sagacious and industrious chemists that ever existed. Charles William Scheele was born on the 19th of December, 1742, at Stralsund, the capital of Swedish Pomerania, where his father was a tradesman. He received the first part of his education at a private academy in Stralsund, and was afterwards removed to a public school. At a very early period he expressed a strong desire to study pharmacy, and obtained his father's consent to make choice of this profession. He was accordingly bound an apprentice for 6 years to Mr. Bouch, an apothecary in Gothenburg, and after his time was out, he remained with him still 2 years longer. It was here that he laid the groundwork of all his future celebrity, as we are informed by Mr. Grunberg, who was his fellow apprentice, and afterwards settled as an apothecary in Stralsund. He was at that time very reserved and serious, but uncommonly diligent. He attended minutely to all the processes, reflected upon them while alone, and studied the writings of Neumann, Lemery, Kunkel, and Stahl with indefatigable industry. He likewise exercised himself a good deal in drawing and painting, and acquired some proficiency in these accomplishments without a master. Kunkel's Laboratorium was his favorite book, and he was in the habit of repeating experiments out of it secretly during the night time. On one occasion, as he was employed in making pyrophorus, his fellow apprentice was malicious enough to put a quantity of fulminating powder into the mixture. The consequence was a violent explosion, which, as it took place in the night, threw the whole family into confusion, and brought a very severe rebuke upon our young chemist. But this did not put a stop to his industry, which he pursued so constantly and judiciously that, by the time his apprenticeship was ended, there were very few chemists indeed who excelled him in knowledge and practical skill. His fellow apprentice, Mr. Grunberg, wrote to him in 1774, requesting to know by what means he had become such a proficient in chemistry, and received the following answer: "I look upon you, my dear friend, as my first instructor, and as the author of all I know on the subject in consequence of your advising me to read Newman's Chemistry. The perusal of this book first gave me a taste for experimenting myself, and I very well remember that upon mixing some oil of cloves and smoking spirit of nitre together, they took fire. However, I kept this matter secret. I have also before my eyes the unfortunate experiment which I made with pyrophorus. Such accidents only serve to increase my passion for making experiments." In 1765, Scheele went to Malmo, to the house of an apothecary called Mr. Karlström. After spending 2 years in that place, he went to Stockholm to superintend the apothecary's shop of Mr. Scharenberg. In 1773, he exchanged the situation for another at Uppsala, in the house of Mr. Luke. It was here that he accidentally formed an acquaintance with Assessor Gahn of Falun, who was at that time a student at Uppsala, and a zealous chemist. Mr. Gahn happening to be one day in the shop of Mr. Luke, that gentleman mentioned to him a circumstance which had lately occurred to him, and of which he was anxious to obtain an explanation. If a quantity of saltpetre be put into a crucible, and raised to such a temperature as shall not merely melt it, but occasion an agitation in it like boiling, and if, after a certain time, the crucible be taken out of the fire and allowed to cool, the saltpetre still continues neutral, but its properties are altered. For if distilled vinegar be poured upon it, red fumes are given out, while vinegar produces no effect upon the saltpetre before it has been thus heated. Mr. Luke wished from Gahn an explanation of the cause of this phenomenon. Gahn was unable to explain it, but promised to put the question to Professor Bergman. He did so accordingly, but Bergman was as unable to find an explanation as himself. On returning a few days after to Mr. Luke's shop, Gahn was informed that there was a young man in the shop who had given an explanation of the phenomenon. This young man was Scheele, who had informed Mr. Luke that there were 2 species of acids confounded under the name spirit of nitre, what we at present call nitric and hyponitrous acids. Nitric acid has a stronger affinity for potash than vinegar does, but hyponitrous acid has a weaker. The heat of the fire changes the nitric acid of the saltpetre to hyponitrous, hence the phenomenon. Gahn was delighted with the information, and immediately formed an acquaintance with Scheele, which soon ripened into a friendship. When he informed Bergman of Scheele's explanation, the professor was equally delighted, and expressed an eager desire to be made acquainted with Scheele. But when Gahn mentioned the circumstance to Scheele, and offered to introduce him to Bergman, our young chemist rejected the proposal with strong feelings of dislike. It seems that while Scheele was in Stockholm, he had made experiments on cream of tartar, and had succeeded in separating from it tartaric acid in a state of purity. He had also determined a number of the properties of tartaric acid, and examined several of the tartrates. He drew up an account of these results and sent it to Bergman. Bergman, seeing a paper subscribed by the name of a person who was unknown to him, laid it aside without looking at it, and forgot it altogether. Scheele was very much provoked at this contemptuous and unmerited treatment. He drew up another account of his experiments and gave it to Retzius, who sent it to the Stockholm Academy of Sciences, with some additions of his own, in whose memoirs it was published in the year 1770. It cost Assessor Gahn considerable trouble to satisfy Scheele that Bergman's conduct was merely the result of inadvertence, and that he had no intention whatever of treating him either with contempt or neglect. After much entreaty, he prevailed upon Scheele to allow him to introduce him to the professor of chemistry. The introduction took place accordingly, and ever after Bergman and Scheele continued steady friends, Bergman facilitating the researches of Scheele by every means in his power. End of section 41. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com.